Herman, could you hear us?
Yes, hello.
Hello, could you share your screen, please?
Yes.
Good morning, everyone. Welcome to the second day of this workshop, Mexican workshop on practical physics.
Check. No, I'm sharing the wrong screen. Let me. This one. Only 5. No. Let me change the. We share this one. This one. Okay. Perfect.
So our first session of today is divided into 2 online plenary talks. The first one is from Germán Sborlini. He is a postdoctoral researcher from Salamanca University. So welcome, Germán.
Thank you. Okay, thank you very much for the invitation and the opportunity to give this talk. The title of this talk is geometrical causality. Essentially, we want to discuss how to convert, let's say, Feynman integrals into something that can be implemented in a quantum computer. So let's start. The outline of the talk is the following. First, we will motivate why we need to do this. Then we will explain a bit about the loop tree duality and in particular the connection of this formalism with the causality and the geometrical interpretation. Then we will move to quantum algorithms for high energy physics, and we will discuss two approaches, Grover search algorithm and something called the Hamiltonian minimization. Finally, the conclusions. So the point is that nowadays we know that we need to confront the data extracted from the colliders with the theoretical models and their predictions. Usually we calculate cross-sections or decay production rates at colliders. And the point is that if there is something to be discovered, we know that almost for sure it is a tiny effect. So we need to match the experimental accuracy of the experiments with our theoretical predictions. Usually in the context of high energy physics, we use the Parton model, and this is our master formula here. And then we have the usual convolution with the PDFs and with the Partonic cross-section. And the point is that the Partonic cross-section in particular sometimes is ill-defined. It contains singularities or objects that are not well-defined, mathematically speaking. So we introduce something called a regularization. In this case, usually we use something called dimensional regularization. And the idea is that we change the number of space-time dimensions. Of all the ingredients, in the previous formula, we have the Parton distribution. There are some problems, let's say, to extract them from data, but there are some paths to solve them. And then we have the Partonic cross-section, that is this ingredient that requires this regularization. And essentially, the traditional approach consists in dividing the cross-section in several pieces, regularizing each piece independently, and then canceling all the problems. The problems manifest in epsilon poles. So we usually have this loop that are quantum fluctuation of the vacuum, plus the real emission, and plus something that cancels the epsilon poles, the singularities. In this case, the counter terms, ultraviolet counter terms. When we put everything together, this is fine. The point is that when we want to increase the precision, we want to calculate these loop corrections with a high precision. We want to include higher orders. And this is complicated. This is a bottleneck. Also, these real corrections involve very complicated phase-space integrals. So this is something very difficult to calculate. And if we try to compute everything independently, the difficulty is even higher. in particular because of this, that the cancellation of the poles take place after integration. So we have to integrate very complicated expressions, and then everything is going to cancel and we will get a number. And the idea is, so the problem that we are having is mainly related with these loop integrals. And the point is that they live in a space that is different from the space of the real correction. So we cannot combine everything simultaneously. And how to do this? Well, a method that we have been exploring is the loop tree duality. Essentially, we have the loop that have the particle encoded by virtual internal momenta that are defined in Minkowski spacetime. We apply this loop tree duality, this machinery, and we end up with something that is called the dual amplitude, that have on-shell cut momenta, and that is defined in the Euclidean spacetime. And the real radiation is also defined in the Euclidean spacetime. So we are going in the right direction. And also, when we have a finite loop integrals, everything can be numerically integrated. And sometimes we need to add some local contour terms, but the structure is very, very similar to the phase space one. So by using the loop tree duality, we have like a method, a strategy to infer how to combine the real and the virtual in a single object. The point is that since the formalism was first proposed in 2008, it has been evolving. And we developed 2 years ago with our collaborators in IFIC Valencia and collaborators in Culiacán, in Sinaloa University, a strategy that is based on the iterate application of Cauchy residue theorem. And the idea is that every time that we apply, when we have a multi-loop and we apply this Cauchy theorem several times, we open all the loops into trees, and we end up with something that is a tree-level object. So that has the same structure that we have in the real emission contributions. And basically, the master formula for this iteration is the following. We start, we have loops, and we start to put them on shell by calculating the residue, and we do it in an iterative way. So we remove one loop, then another, and so on. And what happens when we do this on some, let's say, families of topologies, like this one that is called the maximal loop topology? We end up with something that involves sums of objects that have a very well-defined symmetry. In this case, it's like we are moving, which is the particle that is left off shell inside this object that is well-defined. This is called the dual amplitude. And we have this formula that, of course, if we open this formula, we have a lot of terms, but it can be written in a very compact way. And this object here, the maximal loop topology, turns out to be the building block for more complicated objects. So if we have more complicated topologies, we can reduce to convolutions with this object. And the important thing is that any one or two loop amplitude can be described as these MLT topologies. But there is something more. When we take all these terms that appear in the previous formula, right, all these things, and we add them together, we can combine them in an even more compact formula, that is this one here, where we have this lambda. The lambda are known as causal propagators, and essentially they have a graphical interpretation. This graphical interpretation tells us that we can think about energy flowing from one vertex to the other, right? So we have this diagram in the left and this diagram in the right, and we see that all the lines that are being cut by this dashed line here are carrying momenta or energy in the same direction. This is consistently oriented. So we can map this kind of cuts or partitions of the diagrams into terms containing these lambdas. And this is how we can establish a geometrical link, in some sense, between this very compact representation and the diagrams. And the good question is why we need this causal representation. And the point is that since these lambdas that appear in the denominator have same sign combinations of positive objects, because look at these definitions, these Qi0 are positive objects, are the square root of some combination of internal momenta. We reduce the number of singularities, even spurious singularities, that might appear at the integrand level. So if we take some random examples, we can see that here, for instance, in this case, we check the integrand of some amplitude, and we plot the behavior of this integrand close to some diversion, some zero of the denominator in the Feynman representation. But the point is that this zero is associated to something that is spurious, something called unphysical threshold or unphysical instability. So if we recast this expression into something with a causal representation, we see that there is no singularity, no instability. And the same if we take something more complicated, like this. This is a representation of the integrand of some more complicated topology. Again, we are not using the causal representation here, and we see these white lines that are like infinities, spurious infinities that appear when we evaluate, because numerically there are some terms that are like 1/0. So, yes, there is any question or? Okay. So the point is that, as I was mentioning before, there is a connection between the geometrical representation of these Feynman graphs and the causal representation, this representation in terms of lambdas. So essentially, we take this diagram that is a bit more complicated, and the thresholds that can take place, the physical thresholds, corresponds to one lambda. For each threshold, we have one lambda. And the point is that when we are working at multi-loop level, these thresholds can be entangled. There is a diagram that might have several thresholds. When there is a particular, or there are some particular combination of external momenta, you can have some thresholds. So essentially, these thresholds at the diagram level are codified into binary partitions. For instance, look at this lambda 1. This line here is dividing, separating this diagram into pieces that are connected through binary connected partitions. The same with this lambda. And you can see that the pattern repeats in the other contributions. So essentially, we can map this graph here in terms of connected binary partitions into this 1/λ1, λ2, 1/λ2, λ3, and so on. So by exploring several examples, we realize that essentially there is this kind of cluster formula, and we have to detect which are the allowed combinations of causal propagators. So the point is that there are some strategies that our group, for instance, has been developing. One is has been developed by William Torres Bobadilla, and is an algebraic reconstruction. He uses something called the maximal connected diagrams, and then start to apply algebraic connections to derive a causal representation. But also there is a geometrical construction that is the topic I have been working on. And the idea is that the diagrams are made of vertices and multi-edges or edges. These are objects that connect two given vertices. So in a diagram, you can have particles connecting two vertices, and you can combine all of them into a single option that are these multi-edges. These multi-edges define a basis of momentum. And then this can be codified into something called the vertex matrix. This is a geometrical object. And all the causal structure is contained in this vertex matrix. And the point is that the binary connected partitions in the end are the ones that indicate which are the lambdas that can take place, the thresholds that can take place. So the recipe for obtaining this causal representation based on geometry is the following. First, we need to generate the causal propagators. So we have to detect all the possible connected binary partitions. Then we have to calculate something called the order of the diagram. And this order of the diagram is something that quantifies the topological complexity of a given diagram. And there is this formula that essentially tells us that it is the number of vertices minus 1. This is something derived only from geometry. So each term here of the causal representation will have products of k lambdas. So this number is very important. And then something called the geometrical or geometry compatibility rules that essentially tell us which are the lambdas that can be put together, the thresholds that can manifest simultaneously. And for this, you have to put combinations of k causal propagators or lambdas that cuts all the edges at least one, that when you represent them in terms of cuts of the diagram, they do not intersect each other. And then that the orientation of these partitions, when you put the lambdas in the diagram, when you split the diagram, is consistent. In the sense that if you have one of these lines, for instance, the red line, all the lines that are cutting the red line are carrying the momentum, the energy in the same direction. The point is that when we have complex topologies, there are lots of causal configuration. And it takes a lot of time to test everything. So can we use some technique to identify these causal terms? Yes. We can, for instance, explore quantum search algorithms. And our first approach is based on something called the Grover's algorithm. So the idea of Grover's algorithm is the following. We have some selected states, the so-called winning states. And we want to make an uniform superposition of all the possible states that we have in the system and achieve some kind of a speed up compared to the classical methods to identify or to select these selected or winning states. So if we have a total of n states and R of them are winning states, we have n minus R orthogonal or loser states, if you want. So we have to prepare these states. We have to identify this angle that is, well, some kind of mixing angle that tells us the difference between the winning and the non-winning components. And then we have to use some strategy that is called amplitude amplification. That is, this is something that is then generalized to develop algorithms beyond the Grover's search algorithm. And the idea is that we have an oracle or marker, this UW, that change sign when the state belongs to the subspace of winning or the non-winning or orthogonal space. And then we have a diffuser operator that in some sense implements the opposite direction. So the point is that the combination of these two operators applied t times leads to this formula, and by modifying this t, you can modify this angle. So you can enhance, for instance, the value of the signage of the angle. And in this way, you achieve an amplification of the winning states. So the idea is that this method amplifies a component that you want to amplify because it fulfills some conditions, and reduce the weight of the others. So if you measure, you will find a peak in all the configurations that fulfill the condition. So how to connect this thing with the causality and the geometry? Well, essentially that we want to identify configurations of sub-configurations of the graphs where the momenta is oriented. The moment of the lines is oriented. And it turns out that this implies that the diagram is acyclical, that there are no loops inside. So for instance, if you look at this green diagram, this, in the green box, you see that here there are no loops. But instead in this one, in the red, you have a loop, well, two loops in fact, here and here. So these configurations with loops are non-causal because you cannot divide the diagram in such a way that you end up with connected binary partitions compatible with the thresholds. So it's something very complicated to prove. It has a lot of geometry, but well, essentially in these papers we discuss more in detail. What? Yes, sorry. Okay. So an example, a fast example, well, or how this thing works essentially in practice, right? So the direction of each edge is codified within a qubit. This qubit can be 0 or 1. So if you take a topology and you identify the orientation, some kind of initial orientation, then you have combinations of zeros and one that tells you if you have to reverse or not the momenta flow of each intermal line. So if you have n edges, in the end you have this capital N that is 2 to the n, because this is the combination of all the possible orientations. You apply the algorithm, the Grover's algorithm, you define these winning and orthogonal states, the superposition of all the states, you define these operators, and then you define the amplification operation. And we can implement this thing in a quantum circuit. For instance, in the simplest case, that is a triangle, essentially, something with 3 vertices and 1 loop, we have this circuit, right? And well, here we have inside this thing that there are some logical gates. We are codifying the diffuser and the oracle. And the point is that, as I was mentioning before, when you measure, you see a peak here, an amplification of the states that are consistent with diagrams without cycles. And the point is that there is a connection between diagrams without the cycle and the causal representation. So at this level, in this example, the quantum algorithm manages to identify all the causal contributions that in this case are these 3, right? And if we look at the circuit, we have used some kind of trick for some topologies. The point is that the Grover's algorithm performs very well when the number of solutions is small or is very big compared with the total, because you can work with a complementary problem, right? So essentially, when the number of solutions is roughly 1/2, you have a problem. And the solution that we find is to add an additional qubit that allows us to increase the number of total states without increasing the number of solutions. So the ratio solution over states is smaller, and the algorithm performs better. So for those interested in the details of what is each part of this algorithm, well, you have here this Hadamard operator that is for preparing the initial state. You have some qubit where you are going to store some information. You have something here that are the logical representation of the marker or the oracle. The diffuser here, that is something implemented in undefined in Qiskit. So you can come here again then if you want to take a look at the circuit. The point is that for this example, we have been playing with not only with the simulator, that there we find very good results and with very good performance. And in fact, adding an extra qubit allows us to identify more efficiently which are the solutions. The point is that when we implemented these things into some real devices, real quantum computers, that are these purple and yellow bars, the result is totally wrong, totally wrong. And the point is that these circuits have something called quantum death. The death when you think about operations that have to be performed on the states. And if you have a lot of operations, then you have noise, and this noise turns out to be something that destroys essentially what you want to measure. It's a very noisy measure. The efficiency is very bad, and in the end, you can the operations that you are trying to implement are not working. So this is the problem of using circuits in principle that have very that are very depth, that have a lot of operations, and as in this case, that make use of a lot of qubits. So good, we managed to implement this, but using these binary selection rules, the binary clauses, the selection rules, this requires a lot of qubits. So we have to use a computer with a lot of qubits. And having a lot of qubits is a problem because all of the qubits have to be stable. You cannot implement something that with the qubits that are behaving randomly. And right now, the technology is in some sense limited. So we cannot have thousands of stable qubits and implement very deep circuits. So right now we are very limited. But on the other hand, the classical computers are very evolved, very optimized. So we can try to combine both worlds, the quantum and the classical. And this is essentially what we have done in the second approach, that is based on something called minimization algorithms and the use of variational quantum eigensolvers. So what we have to do here? Well, we need to return to the geometry and try to define a Hamiltonian. I will explain why Hamiltonian. So if we take a diagram like this one, that is called the Mercedes-Benz diagram, we have some equations that define the momenta of the internal particles. We can codify this thing into something called the vertex matrix, and from the vertex matrix, or even from the diagram itself, we can obtain something called the adjacency matrix. The adjacency matrix, as well as the vertex matrix, contains all the information telling us how the vertex are connected by the edges. If one edge goes from one vertex to the other, or the opposite. So everything is codified here with these zeros and ones. And these adjacency matrices have very useful properties. For instance, if we multiply the adjacency matrix 3 times, and this thing is different from 0, we take the trace of a to the 3, and this is different from 0. This means that there are triangles. That is, if you have these diagrams, there are loops with 3 sides, with 3 edges. If you multiply this thing to the power 4, 5, so on, you will be able to see if there are boxes, pentagons, hexagons, whatever. So there is a connection in some sense in taking the trace of powers of these things, and this trace is equal to 0. This means that there are no triangles, boxes, or so on. So essentially, we find an object that, in some sense, when we have a topology without triangles or without boxes, it is equal to 0. So based on that, we built the Hamiltonian. A Hamiltonian whose ground state corresponds to a cyclic graph. So the first approach was simply to penalize the cycles using projectors. And this is something called the loop Hamiltonian. So if we know which are the loops, we can penalize them. So every time that we have a configuration with loops, the expected value of the Hamiltonian in this configuration is going to be different from 0. So it is an excited state. Other method that is better because it can be automatized. You don't need to know which are the loops or possible subloops, is to promote this adjacency matrix to an operator and trace over all possible cycles and vertices here. So you create this operator, and in the end, you have something like this, where the Hamiltonian is built by adding traces over the vertex space of powers of the adjacency matrix. So by minimizing these things, we will have the cyclic graph. One cyclic graph is something that has essentially 0 energy. If you have an excited state, it contains loops. And then, well, this BQI. The BQI is essentially the method that we have been using to find the solutions of this problem. In the quantum part, the idea is that we will have to evaluate the Hamiltonian. If we want to find the minimum of the Hamiltonian, we have to evaluate the Hamiltonian in a lot of states. So in this part, we create an ansatz that is a parameterized circuit where we can modify the circuit, the parameters, and then we can apply the Hamiltonian to measure the energy. And there is a classical part where we are going to modify these parameters. So essentially, this BQI will have an interaction between the quantum and the classical part. And this is essentially the pipeline. We have the Hamiltonian representation. We have how to encode the operators in these Pauli matrices. It is like a circuit with spins. Then we implement here in yellow the quantum part. We make the measurements, and then based on the results of these measurements, we adjust the parameters. And then we have to update the parameters and return. So essentially, we are doing like a feedback, a cycle, and then we modify the parameters, we return, and we repeat this thing till we identify the minimum. So in an example, sorry?
8 minutes left.
8?
Yes.
Perfect, yes. So with this example, essentially I'm finishing, because here we have this paper with Clemente, Kripa, Janssen, with the DESI team, in which we have been testing this strategy. So imagine that we have this diagram, this Chewy loop 5-point amplitude. So we can first write the Hamiltonian, that when we apply this idea of the trace of the adjacency matrix, whatever, we end up in objects like this with the identities and seed operators. And then we can compute something called the reduced Hamiltonian. This is a technicality where we are fixing the state of one of the qubits. to reduce the space. And then we look for the ground state. The output of the VQI is something like this, where we have some states that are contributing to the ground state. In this case, this ground state or approximate ground state turns out to have a very, very low energy, something essentially compatible with zero. And we have the contribution of these states here, 0100, 0101, 0111, right? These are the ones with higher probability. So the idea is that we are not going to take all the states, but we are going to implement a iterative or multi-run VQI strategy. So in the first step, we take these three states. We build something called the penalization terms that are essentially projecting over these states. It is like running this algorithm several times, and in each run, you collect some solutions. So you run once, you collect 10 solutions. You run other time, you collect 10 different solutions. And it is important, 10 different solutions. And this is why we need to put the penalization terms and penalize the solutions that we already found. Otherwise, the algorithm will not converge. So essentially, we run this thing several times, and we obtain these states. And at a certain point, we have a state with energy higher than zero, in this case, 4, right? And when we reach the solution, the algorithm finishes, it converges. Well, essentially, the idea is that it is not warranted in principle that when the algorithm converges or we reach a value of Hamiltonian with energy larger than 1, for instance, a certain threshold, that is, this is going to have collected all the possible states. No. In fact, we are working on some kind of optimized strategy to identify all the possible minima of a complex minimization problem. This is something that's still that is a problem of this kind of algorithms and has not been solved. So in our examples, I mean, in the paper, we show that for very simple topologies, this algorithm, this naive algorithm works, performs very well. But when you go to more complex topologies where you have more solutions, it is not able to identify all the solutions. So the algorithm converges before collecting all the possible causal solutions or acyclic solutions. Well, so the conclusions. The Lux duality is very important because we can rewrite the Feynman integrals and work instead of Minkowski space in Euclidean space. The nested residue, this idea of iterating the calculation of the residues, leads to something that is manifestly causal. When you add all the terms together, you have an expression that only involves lambdas in the denominator. This has a very important and strong physical and conceptual motivation because we are applying constraints that are exploiting the causality of the process. So we are removing terms that are spurious and that might introduce instabilities. So on the other side, we realize that we can use geometrical rules to detect these entangled thresholds, that we can use quantum algorithms to speed up the selection of these diagrams that have a causal flux configuration. And we are using this technology to explore some new tools for precision fit, to break the precision frontier. This is a project that is called Quantum Theodas, that essentially is a Marie Curie project that I'm running here in Salamanca. And finally, we have compared essentially the Grover and VQI approaches. And in particular, VQI seems a promising candidate to obtain the causal representations in real quantum devices. So thank you very much.
Very much. Is there any question? This one.
Hi, Germán. You explain things so well that you make them look almost easy. So
Thank you. Thank you very much.
I have some questions. So one very
Yeah.
short one. Is there any issue if you have Majorana fermions in the loop?
Well, in principle, this is something that goes at that works at a more abstract level. I mean, independently, if you have a Majorana or Fermi or whatever, the key point, if we go to the beginning, is this thing. Essentially, that you can write the propagator, or at least the denominator of this propagator, in this way, right? I think, as far as I know, that almost independently of the kind of particle that you have inside the loop, you can always write a numerator divided a denominator, and this denominator contains this structure, essentially q squared minus mass squared, or something like that. If you have something that cannot be cast in this way, then you cannot apply this algorithm, at least without any modification.
Yeah, I see. It will be possible to cut in this way, but then causality will not tell you anything about what is the right way to interpret the fermion flux. So maybe this was important for you, no? The causality.
Yes, yes. I mean, this formalism will use the causality to simplify the structure of the denominators. So if you have something that maybe alters that, I expect it to appear in the numerator. So it's like, I like to think about this as having a topology and then dressing this topology with the fields. So essentially, this is something that works at the level of the topology. You can then dress the topology or the diagram, but still these properties are going to be fulfilled.
Okay, thank you. And then if I can ask something else.
You're welcome.
You have a very recent paper on 5
Yeah.
So
Yes.
when I see this, it's amazing. So, for instance, can you check the Kinoshita et al. Results for electron G-2? And I think you mentioned higher order computations of alpha S or things like that. So can you comment on this?
Okay, well, right now, I mean, we have in that paper of 5 loops, we have essentially developed some factorization formula that allow us to express the, let's say, the most complicated topologies in terms of simpler one. However, the point is that implementing these things explicitly for a given theory is still a bit far from our technology. I mean, in principle, we identify some terms, we identify the structures, all the possible structures, but still you need to write the expressions explicitly. Essentially, in that paper, what we have been doing is like this formalism. It was not about the causal representation. It was a step before arriving to causality. And the idea was to exploit these factorization formulas that when you have more complicated topologies, I think I have it in the backup. I'm not sure if I have it in, oh, sorry. Yes, I have it in the backup. Okay, but again, I can go to backup. Backup, look, something like this. Something like this diagram here you can find some formulas to reduce this diagram to products of objects that are simpler. So essentially in that paper of 5 loops, we have been exploring how to simplify the structure of generic 5-loop diagrams, but still we have not implemented this for a concrete calculation. I'm very how do you say, optimistic about having a simplification, a huge simplification in the calculations, but still this is something that with our technology is a bit far.
We have time.
Sorry?
The chair allows me to ask you something else. So
Yeah.
at some point, besides doing this research, going to higher loops and all that, maybe you would like that people use this as an alternative of traditional computation.
Yes.
That you would need to implement it in loop tools, whatever. So are you working on this, or because you're numerically more stable? So
Yes. Yes. I mean, we are trying to develop some methods, some frameworks, but still this is something that I mean, since this is an alternative method, it's not so easy to convince people to use it, to implement this. There is a group in Zurich, for instance, that is trying to develop their own technology for doing the causal loop tree duality. In our case, William Torres in Munich has been developing a code called LOTI that allow us to calculate the causal representations for something more or less complicated, but still trying to implement this technology to more automatize or more standard frameworks is difficult. I mean, we are trying to improve our implementations and make them more automatic, but still there is a lot of work to do.
All right. So we have no more questions. So thanks again to the speaker.
Okay, thanks.
Actually, thank you, Dad. We cannot hear you.
Hello. Hello. Good morning.
All right. Could you share your screen, please?
Okay. Can you see my screen?
Yes, we can. So,
Okay. May I start?
yeah.
So, good morning. My name is Maciej Rybczyński. I work at Jan Kochanowski University in Kielce, which is a town in Poland. I will talk about fluctuations and correlations as observed in multi-particle production processes. Let me first thank the organizers for giving me this opportunity. So I will start with a brief discussion of some news on fluctuations and correlations observed in Na61 SHINE experiment at the CERN SPS. And then I will try to briefly explain you some simple model which will allow us to better understand the observed multiplicity fluctuations in collisions of relativistic ions. And I will finish with brief discussion of some intriguing properties of multiplicity distributions. So let me start with those news from Na61 SHINE at CERN on fluctuations and correlations. The first main question is why we do some analysis connected with measurement of fluctuations and correlation. There are two main reasons. One of them is that those measurements may serve as a signature of the so-called onset of deconfinement, where close to the phase transition between hadron gas and quark-gluon plasma, the equation of state of strongly interacting matter changes rapidly, which can impact energy dependence of fluctuations. And the second reason is that fluctuations and correlations can help to locate the so-called critical point of strongly interacting matter, which is in analogy to critical opalescence observed in boiling water, the enlarged fluctuations close to the critical point. And for strongly interacting matter, maximum of critical point signal is expected when freeze-out happens near this critical point. So Na61 SHINE is an experiment located in the node area of CERN SPS at H2 beamline. By the way, SHINE stands for SPS Heavy Ion and Neutrino Experiment. And within Na61 SHINE facility, we are interested in two kinds of measurements. The first one is for cosmic rays and neutrinos, and the second is the so-called strong interaction program, which I will briefly discuss during this talk. So Na61 SHINE is a unique multi-purpose facility which may be very useful for the measurements connected with fluctuations and correlations, since it is equipped, if I may say this way, with large acceptance. Na61 detector covers the full forward hemisphere down to transverse momenta equal to 0. In Na61 SHINE detector, particle identification can be done in different ways. First, by DDX measurements in the time projection chambers, and also there are time of flights detectors, which may be additional helpful for particle identification. Na61 uses different ion and hadron beams, including beryllium, argon, xenon, lead, and concerning hadrons, there are used pions, kaons, and proton beams. As Na61 is a fixed target experiment, it uses various targets, including even liquid hydrogen. In order to get some more information on these fluctuations and correlations and the presence or not this critical point, Na61 SHINE explores the phase diagram of strongly interacting matter by performing the so-called two-dimensional scan in collision energy and system sites. As you see in this plot, Na61 have already collected data for six different beam momenta, starting from 13 GeV in the laboratory frame up to 150 GeV, and there is a various systems collided, including proton-proton, proton-lead, beryllium-beryllium, argon-scandium, xenon-lanthanum, up to lead collisions. So using this two-dimensional scan, there are possibilities to careful and true check of the possible presence of phenomena connected with the presence of critical point. So concerning news on fluctuations and correlations from Na61 experiments, Na61 collects data on flow phenomena, which is connected with the onset of deconfinement. Also, HBT analysis is performed as a possible signature of the presence of critical point. In the case of HBT analysis, the shape of correlation function is described by the so-called Levi source. I will discuss it later. And of course, Na61 Shine performs many analyses connected with multiplicity fluctuations. You should remember that near the critical point of strong interaction matter, the correlation length of produced particles tends to infinity, and fluctuations measures, which are proportional to average n squared or even average n to the fourth power, are very sensitive to the value of particle correlation length. Let me start with brief discussion of the recent results on directed and elliptic flow observed in lead-lead collisions at smallest energies available at CERN SPS. So here in this plot on the upper left corner, you see the PT dependence of V1 coefficients. There is a clear mass dependence of V1, since you can easily distinguish V1 calculated using pi minuses and protons. These results comes from the mid-central collisions of the centrality between 15 and 35% for rapidity covering forward hemisphere. What we may say more is that when we plot dV1 over dy, there is a changing of sign of this variable at different collision centrality. Here you see dV1 over dy as a function of centrality. Na61 can cover the whole almost whole centrality range. Concerning elliptic flow, for elliptic flow, V2 coefficient calculated for pi minuses and proton, it is different as you see from this plot, but it does not show any energy dependence. And also, what I may say that V1 measured at 13, the lowest possible energy at SPS, namely 30 GeV, differs from the V1 measured at 30 or 40 GeV in the region where V1 directed flow it changes sign. Concerning HBT correlations, of course, we know that Bose-Einstein correlations are sensitive to special extension of particle source. Usually, correlation function assumes Gaussian source, but it can be generalized to the so-called Levi-shaped source, which is described by this simple formula. Concerning technicalities, this correlation function is calculated as a ratio of pairs of pions from the same event divided by the pairs of pions from mixed events. And what is important for this Levi-shaped correlation function is the presence of this alpha coefficients, which is the measure of which may be the signature, which value may be a signature of the presence of critical point, where this alpha should be close to 0.5. If alpha is smaller than 2, this coefficient alpha is smaller than 2, then we may say that we see something like anomalous diffusion. For alpha equal 2, we can say that there is a kind of Gaussian sources. Some technical issues can be found in this paper I'm just mentioning here. So let me show how is the first on the upper plot you see the transverse mass dependence of this R scale parameter, which simply speaking describes the length of homogeneity. And from hydro calculations, we can expect that this R should depends like 1 over square root of transverse mass for Gaussian sources. And we see that clearly this parameter decrease its value with transverse mass, which is a sign of, which may be the sign of transverse flow. Concerning this alpha parameter, which sometimes is called as Levi stability index, of course, it describes the shape of special correlations. And it seems to us that for the current measurements, the measured value of alpha coefficients does not indicate the presence of critical point, at least in collisions of beryllium and argon-scandium, what you can see from this plot, from the bottom plot on this slide. What we see is the alpha the alpha between unity and the value of two, which is a sign of which is interpreted as a sign of anomalous diffusion present in the observed collisions. Concerning multiplicity fluctuations in the Na61 experiment, usually they are used the so-called intensive quantities, which are independent of the volume of the system, at least in case of ideal Boltzmann grand canonical ensemble. So technically speaking, there are many intensive quantities which can be calculated from the data, which includes scaled variance of multiplicity distribution, scaled skewness, scaled kurtosis. In those moments, kappa I stands for ith order of cumulant of the distribution. And of course, there are two reference values for those intensive quantities. The first one is unity, because for Poisson distribution, for produced charged particles, we expect scaled variance equal to 1. And of course, all intensive quantities should be 0 if there is no fluctuations. And we may remember that experimentally, we are only able to narrow centrality of the registered events and consider events from a given centrality class. Thus, intensive quantities may contain also fluctuations of the system size. Concerning distributions of net charge, which is a difference between positively and negatively charged particles, the reference distribution is Stellan distribution and not Poisson, and the used variable to describe this kind of fluctuation is the one plotted here. This is kappa 3 divided by kappa 1, simply speaking. Very interesting observation was done nowadays. If you look at the ratio of average number of positively charged kaons divided by the average number of positively charged pions, plotted as a function of the center of mass energy, you may see this well-known plot, which is called Horn plot. The collection of data from many different experiments, including Na61, but the current interesting observation is that when you look at the results calculated from beryllium collisions, which is very light system, these results, namely this kaon to pion ratio, is very close to the results obtained from reading of proton-proton data. But when we do similar analysis for argon-scandium collision, argon and scand are a little bit heavier than beryllium, but not so much. There is a quite rapid change between those two systems in terms of the ratio of K1 to pions. And what is also interesting, there is a similar change which is visible when we plot kappa 2 over kappa 1, which is scale variance of multiplicity distribution here for negatively charged hadrons. When you see these blue points stands for describes results obtained in proton-proton data, and the other are for beryllium, and argon-scandium. So beryllium looks quite similar as in proton-proton, but for argon-scandium, these are very central, 1% most central beryllium and argon-scandium collisions. There is a visible change in behavior as a function of center of mass energy between beryllium and argon-scandium, and the possible phenomena which can be responsible for such effect, which are considered now percolation and the so-called ADS QCD correspondence. This may also be a first sign of the so-called onset of fireball. But the main question is, what is the energy dependence of higher order moments of multiplicity distribution? Here you see the multiplicity and net charge fluctuations observed in proton-proton, beryllium, and argon-scandium collisions. What we see in this plot is that in case of H minuses, which means negatively charged hadrons, only the scaled variance of multiplicity distribution shows significant differences between heavier and lighter systems, what is seen in this upper left plot. In case of net electric charge, the bottom plots, the scale skewness and scale kurtosis indicate somehow non-monotonic behavior as a function of center of mass energy. And it seems to me that currently analysis is focused on reducing the considerable systematic uncertainties which cannot up to now definitely allow us to make right predictions. The next interesting quantity which is extensively measured in Na61 experiments is proton and charge particle intermittency, up to now in argon-scandium and lead-lead collisions at many, in fact all available energies. This charge and proton intermittency is calculated for particles located in certain bins in px, py plane, and charge intermittency is in Na61 experiment expressed by the value of factorial moments of the Earth order as a function of the number of cells which are used for the analysis. Here on the plots, you see these second factorial moments as a function of m squared, since usually the m describes the number of cells in either px and py direction. So what we can say that why these factorial moments? If the system freezes out in the vicinity of the critical point, the second factorial moment should reveal a power law dependence as a function of number of cells, which is up to now not observed in this analysis, but as far as I know, there is a work on more advanced methodology ongoing in the Na61 SHINE experiment. besides ongoing analysis, nowadays, NA61 Shine is undergoing a substantial upgrade of the detector, which includes construction of a new vertex detector, especially for possibility of observation of decay of D0 and anti-D0 mesons. The new trigger and data acquisition system is also installed. There is a replacement of the TPC readout electronics just to increase the data rate up to 1 kilohertz. There is upgrade of new, in fact, there are installed new time of flight detectors and projectile spectator detector, which is used in NA61 experiment as a centrality detector is undergoing a substantial upgrade as well. The main goal of those upgrades is to perform the first ever open CHAN measurements at CERN SPS. There are many open questions which needs answer. First is, what is the mechanism of open CHAN production? How does the onset of deconfinement impact open CHAN production? How does the formation of quark-gluon plasma impact J-psi production? And to answer this question, the mean number of CHAN quark parts produced in the full phase space in nucleus-nucleus collision has to be known. We expect NA61 Shine to be ready in 2027 for the next measurements, and in such a case, there will be possible the energy scan with light and medium mass ions to further study of diagram of strongly interacting matter. The measurements of heavy hadron resonances in large statistics in proton-proton interaction will be also available. There will be possible measurements with anti-proton beams, measurements of hadron emission from long baseline neutrino facility at Fermilab and Hyper Kamiokande replica targets will be also possible, and data for flux prediction in neutrino experiments using very low energy beams will be available. All details I will discussing can be found in this CERN SPSC report. So to conclude this part, one can say that two-dimensional scan in system size and energy is already completed, revealing some unexpected dependencies, like an onset of fireball, which of course delivered new exciting results. However, so far there is no convincing indication of the presence of critical point. And detector upgrade, which is almost done, allows to perform open CHAN measurements, which in fact starting this year. Nowadays, the first ongoing measurements of open CHAN production at SPS in collisions of lead-lead nuclei at the top SPS energy. Okay, so now let me move to some other issues I would like to raise today. Namely, I would like to briefly discuss some simple model which allows us to better understand some observed results on multiplicity fluctuations in collisions of relativistic ions. Some details on this analysis may be found in this paper. So the main motivation of this kind of analysis is to understand the interesting results which were discussed previously. Here on the left, you see the interesting results on multiplicity fluctuations. This is the scaled variance of charged particle multiplicity distribution as a function of number of projectile participants obtained at fixed number of projectile participants. Here is for negatively, positively, and all charged particles. And as you see, there are no models available on the market which can describe this kind of non-monotonic behavior. NA49 was a predecessor of NA61 SHINE experiment at CERN, but currently, here on the right, you see the collection of the results on scaled variance of negatively charged multiplicity distribution as a function of system size, which is also not possible to be described by the used model. So the question is, what kind of mechanism of multiparticle production can be responsible for such non-monotonic behavior of multiplicity fluctuations observed in data? We assume that, of course, collisions of relativistic ions leads to a production of hot quark gluon plasma, which cools and at some temperature transits to hadron gas of that temperature. The hot quark gluon plasma system during the transition is effectively quenched by the cold physical vacuum. The so-called self-organized criticality is the appropriate mechanism which leads to the universal scale-free behavior. Self-organized criticality is a property of non-equilibrium dynamical systems that have a critical point as an attractor. And the remarkable feature of an active matter, of this kind of active matter, is the propensity to self-organize, which one striking instance of this ability is to generate the spatial structures of the so-called cluster phase, where the cluster, broadly distributed in size, constantly move and evolve through particle exchange. Thus, we can define such a cluster as a quasi-neutral gas of charge and neutral particles, which exhibit collective behavior. The characteristic space scale of this shielding is the so-called Debye length, which is defined here, where n is the density of charged particles, and we can, if we take pion radius and some parameters you see here, we have the volume. We have the volume in which there is something like 143 charged particles, which corresponds at center of mass energy of the order of 7 GeV, which is the top SPS energy, to the number of projectile participants of the order of 1820. Multiplicity distribution in a cluster is given by negative binomial distribution, while the rest, treated as a superposition of elementary collision, is described by binomial distribution. Variance of multiplicity distribution in a cluster depends on mean multiplicity in such a way. And here in this plot, you can see a collection of various experimental measurements where scaled variance of multiplicity distribution depends on average multiplicity in this simple manner. Results which are available within this model, here you see on the left average number of charged particles, and on the right scaled variance of all charge multiplicity distribution of particles produced in lead-lead collisions, plotted as a function of number of nucleons from projectile nucleus which participate in collisions. These are these NA49 data, as you see, nicely described by this model of dynamic cluster formation, and the same for all charge particles. In the dynamical clusterization model, in fact, the only difference between negatively and all charged particles is the experimental acceptance manifested by the fraction of accepted particles. So we may use similar consideration to obtain the values of scaled variance of negatively charged particle particles multiplicity distribution produced in proton-proton and the most central beryllium-beryllium, argon-scandium, and lead-lead collisions and emitted in forward hemisphere. Here are the results from Na61 SHINE experiment, which are also nicely described by this kind of model of dynamical clusterization. So what we can say, it is shown that the observed non-monotonic behavior of the scaled variance of multiplicity distribution as a function of collision centrality, which is not observed in a widely used string hadronic models, can be fully explained by the correlations between produced particles, which promotes cluster formation. And this ability to generate spatial structures sign the propensity of self-organize of hadronic matter. Multiplicity clustering provide new insights on the non-monotonic behavior of multiplicity fluctuations. You may find more details in this paper. Let me finish this since I have not so many time. Yes. Let me finish with brief discussion of some quite intriguing properties of multiplicity distribution recently observed in the data. Of course, multiplicity distribution of charged particles produced in both E plus, E minus, proton-proton, and even centrality selected lead-lead collisions exhibit peculiarly enhanced void probability and oscillatory behavior of the so-called modified combinants. The sets of combinants, which are described here by C with index J, provides a similar measure of fluctuation as the set of cumulant factorial moments K, which I already discussed in the first part of this talk. But while cumulants are best suited to study the densely populated region of phase space, combinants are better suited to the study of sparsely populated regions because calculations of combinants required only the finite number of probabilities. The dynamics of multi-particle production processes is hidden, in fact, in the way in which the consecutive measured multiplicities are connected each other. In the most simple case, one assumes that the multiplicity is directly influenced only by the neighboring multiplicities, n plus minus 1, in the way dictated by this simple recurrence relation, where this beta coefficients is higher than 0 for negative binomial distribution, is smaller than 0 for binomial distribution, and beta equals 0 for Poisson distribution. However, we propose a quite more general form of such recurrence relation. When you look at this one, we here introduce some coefficients C, which define the corresponding multiplicity distribution in this way. These coefficients contain the memory of particle of n plus 1 about the other previously produced particles. Of course, these coefficients can be directly calculated from the experimentally measured multiplicity distribution when we simply reverse this formula. And the set of these combinants provides a very similar measure of fluctuations as the set of cumulant factorial moments. By the way, the combinants can be expressed by cumulant moments and vice versa. There is a question: what can be expressed via the combinants? Here are some results showing, here on the left you see multiplicity distribution of charged particles produced in E plus E minus collision from Aleph experiment. This is distribution which can be simply described by, but the calculated combinance from the multiplicity distribution shows quite unexpected oscillating behavior with the for the very broad range of ranks of these CJs. Here are other results which comes from proton-proton collisions at here are 7 TeV from Alice experiments. These particles are this multiplicity distribution was produced from particles populating pseudo-rapidity range from -3 to 3. And on the right, you see the corresponding set of modified combinants emerging from the observed multiplicity distribution. What is also interesting, there is a significant increase of the value of probability of zeroth bin observed in the data in proton-proton collision. And here is the charge particle multiplicity distribution measured in semi-peripheral dead collisions by NA49 experiment at square root of S17 GeV, here fitted by negative binomial distribution. This multiplicity distribution comes from the collisions at fixed number of 30 projectile participants. As you see, we can nicely describe this multiplicity distribution by a single negative binomial fit. But when we calculate the modified combinants from data as well as from the fit, we see unexpected oscillating behavior of the calculated modified combinants. This is the unexpected feature, and the question is, what is the source of this feature? What we can say at the end, the modified combinants deduced from the measured multiplicity distribution of charged particles, together with the already measured void probabilities, could provide some additional information on the dynamics of the particle production. Of course, detailed analysis of the modified combinants derived from the experimental multiplicity distribution reveals many differences between various processes. In E plus, E minus annihilation, modified combinants oscillate with the period of 2, with amplitude increasing as a power law. On the other hand, in proton-proton collisions, modified combinants oscillates with approximately 10 times larger period of E plus, E minus collisions with decaying amplitudes. Up to now, we still investigate the CJ dependence of the moments derived from the centrality selected nucleus-nucleus collisions. You may find many details, additional details on this interesting feature in this plot. So that's all what I would like to say to you, and please enjoy the football match, because Mexico and Poland already started the first match on the FIFA World Cup. So thank you very much.
So is there any question? Well, meanwhile, you mentioned that the rich physics program of NA61, it is related with the constraint of the neutrino flux from Fermilab and also from PPK, I guess.
Mm-hmm.
For the next neutrino programs at Fermilab, like Dune, what are your plans?
I am not aware of the plans up to now, so sorry, I cannot definitely answer on this question.
Okay. Any other question? Okay, here is one.
Hi, thank you very much for the talk. It's just a very naive question. Multiplicity. Can you hear me well? Okay.
I cannot say I hear you well, but maybe I can understand your question if I will be closer to my.
Okay, I will try to speak louder.
Okay, now it's better. Okay.
Okay, regarding the charge multiplicity, it's the multiplicity of the particles that the detector is able to see, or are all the charged particles that are naturally produced on the collision?
Mm-hmm.
So these are the charged particles that the detector is able to see, or all the charged particles that were produced? This is the question. I don't know if you... You cannot hear me right. Well. No.
So sorry.
Okay. So my question was regarding the charge multiplicity.
Yeah.
This
Which slide?
of all the particles that the detector is able to see, or are all the particles that are produced in the collision?
Uh-huh. I don't know whether I properly understood your question, but this is regarding the acceptance of the detector.
Okay. And is there any way to match these two multiplicities, or we just deal with the acceptance?
No, the point is that in fact, if you would like to express, let's say, multiplicity fluctuation in terms of standard cumulant moments, you should know the whole multiplicity distribution. But in fact, any experiment can allow us to measure only a fraction of the produced particles due to the limited acceptance. And the question is how much those moments calculated from this narrower multiplicity distribution when producing reality can express the observed fluctuation. So instead of these cumulant moments, we can use, for example, these combinants, which simply speaking does not depend on the whole multiplicity distribution, but only depends on the multiplicities which are smaller than the rank of the combinant.
Okay.
It's quite hard to hear you. I don't know whether this is only my problem, but sorry. I'm trying to be as close as possible to my laptop, but I cannot really properly understand.
Can you hear me?
Your question.
Sorry, one more question. Can you hear me?
Yeah.
Okay. I asked about, you speak about multiplicities and momentum, but don't you think we can use the Bjorken approach and kind of try to see the behavior of the density, something like that?
Hello?
Sorry, can you hear, could I repeat the question?
Poorly. If hello?
Sorry, hear me? Can I repeat the question?
Now I hear you better.
Okay, so in the beginning of the presentation, you speak about the multiplicity, the momentum, etc., and you try to speak some kind of behavior of the physics of the collisions. So why don't you use something like Bjorken approach to try to explain something like that, or like a phase, or why do you use that kind of approach?
We cannot hear you.
Hello?
We cannot hear you. Are you?
Oh, and now? And now?
Oh, we can. Yes, we can.
I don't know what is the issue, but maybe I will stop sharing my screen, and then will be better to hear me.
Okay.
Who is better? Hello?
Yes, we can hear you. Yes, we can hear you.
Okay, so what was the question? Maybe.
Sorry. So the question was, in the beginning of the presentation, you speak about multiplicity, density probability, the momentum, etc. So to have like the key ingredients to try to do something like the Bjorken approach. So why do you try to do something with the probability density?
Okay, maybe you can discuss that later.
Yeah, I think so. Maybe we can connect after this talk. I don't know. Maybe we can share your.
Once again, Mr. Zubczynski.
Thank you.
So before the coffee break, I have an announcement. You must use your face mask outside within the installations of this Carolina building, please. You have 20 minutes for coffee.
Okay, good morning. Let's continue with the next session of the morning. So the first stop will be the quark propagator in the light cone gauge by Alfonso Aldair. So please go ahead.
Hello, everyone. Thanks for having me. I'm going to present the quark propagator in the light cone gauge. This is a work that we're doing in collaboration with Adnan Bashir, Luis Fernandez, Gustavo Paredes, and Angel Salvador. One way to understand physics of hadrons is by solving the Schwinger-Dyson equations. These equations are the equation of motion corresponding to the Green's function in QCD. The Schwinger-Dyson equations have been solved in covariant gauge. And in this work, we are going to work with the light cone gauge. The main advantage of this light cone approach is that we automatically get rid of all ghost and non-physical degrees of freedom. So these diagrams do not appear in this light cone gauge. For the light cone coordinates, we take a 4-vector in Minkowski space and we transform as A0 goes to A plus and A3 goes to A minus, where we define A plus as A0 plus A3 and A minus A0 minus A3. The scalar product is defined this way. In this work, we use the metric convention plus minus, and when we perform a transformation of a space, a big rotation, we get the metric plus plus. In the right, we have a diagram for the light cone in red, and in blue we have the light front. The light front is a plane that is tangent to this light cone. In this light cone, we have two vectors, n mu and n mu star, and are defined by 1, 0, 0, 1, and n mu star is defined by 1, 0, 0, minus 1, where eta is a parameter to fix, and this is a convention that we are using. In this light cone gauge, we define the Lagrangian by the representation of the gluonic field tensor is for F. For A, we have the gluonic field, and for C, we have the fermionic field. And for the index of color and index of flavor, J. And D is the covariant derivative, where it's defined this way. The R is the matrix of color. And the main difference between this Lagrangian and the covariant gauge Lagrangian, it comes from this second term. We have a 4-vector n that is a like vector, which means that n squared equals to 0. And chi is a parameter, a gauge fixing parameter. From this Lagrangian, we can derive the Feynman rules at 3 level for the quark propagator and quark gluon vertex. We have the same rules as in covariant gauge. The main difference comes from the gluon propagator, which depends on this n vector. And we have to be careful here because this gluon propagator at 3 level is non-transverse, which means that if we contract with the 4 momentum, K mu is not equal to 0. But for the corrections, we see that the gluon propagator is in fact transverse. So this is the representation, diagrammatic representation for the Schwinger-Dyson equations. And on the left side, we have the fully dressed quark propagator inverse equals to the bare quark propagator inverse minus this figure that is called the self-energy, where the field bubbles represent all the possible interaction that we can have in this part for the quark, also for the gluon, all the possible contributions for the gluon, and all the possible contributions for the quark gluon vertex. These equations present Poincare invariants. They form a set of infinitely many functional differential equations, and they work very well for studying non-perturbative phenomena. This is the representation, mathematical representation for the Schwinger-Dyson equations. The self-energy is defined by this form, where CF is the constant of color, G is the running coupling, and they depend on the momentum and the ultraviolet cutoff. And with K, the difference between P minus Q. And for this case, the most general decomposition for the self-energy of the quark can be written as a sum of 4 dressing functions, A, B, C, and D. And the main difference between this LightCon gauge and the covariant gauge is that we have 2 extra structures, dressing functions C and D, that do not appear in covariant gauge. And this is a manifestation that Lorentz invariance is hidden, or we're kind of missing Lorentz invariance. After renormalization of the Schwinger-Dyson, we have this equation where C2, Cm, and C pi stands for the renormalization constants. And the fully dressed quark propagator can be written as a sum of 4 dressing functions that are related to the 4 previous dressing functions, A hat, B hat, C hat, and D hat, by these relations. And we define a function beta that is on the denominator of the quark propagator. The renormalization conditions at 3 levels, we have the at the renormalization point mu squared. For A, it goes to 1, and for B, it goes to the mass of the part C. And expect that for C and D and D, but we don't see that in this case as we will see later. But we're expecting this because at 3 level they did not appear in the quark propagator. That's what we're expecting, but here we have to be careful because one loop calculation suggests that we need to choose a renormalization direction. So here are the one loop solutions. If we only take the leading log approximation, we have these 4 functions in terms of integrals, and these constants is dot products between the 4 vectors n and the momentum. And for the integrals at leading logs, we see that they depend on p squared, but also depend on the parallel component of p. We see this for A and C, and kappa stands for the constant and this alpha. And we can see a decomposition for p squared for the parallel component and the transverse component by using these n and n star vectors. And here we have the numerical results that we have for p transverse equal to 0. For A and B, we have a complete real functions, and for imaginary part, they are 0. And in blue, we have the numerical results. In orange, the analytical results come from one loop analysis. And we see a very good behavior for A and B.
at the renormalization point, mu square. Here we are using mu equals to 19 GeVs. And here are the factors that we are taking. And for C and D, we have a very similar result for C and D. They kind of seem like they are symmetric. And after 1000 GeVs, we can see that there's a difference between numerical results and analytical results. And this might be a numerical error. And C and D, this is their functions. For the conclusions, we see that the tracing functions A and C and D, they depend not only on P squared, but depend on the direction that we're choosing for P1, P2, P3, and P4. And this is because the Lorentz symmetry heights, it is not easy to prove that there's Lorentz symmetry for this light cone gauge. And also, one way to improve the results is by making the tree-level Bloor propagator at least at tree level to be transverse. As I have said, it is not transverse at tree level, but it is transverse at the corrections. And if we want to solve for non-perturbative regimen, we must propose an interaction model that take into account all of these previous situations. And that's it for my part. Thank you.
All right, so we have time for questions. Also, people connected can open their mic.
Hi, thanks for the presentation. I probably missed it, but I didn't understand why you need to do this numerical evaluation. Is needed for further calculations? Because
Okay.
you already have the analytical, right?
Okay. The numerical results are for this whole equation. And the analytical results, they are for leading log approximation. Yeah. So that's the comparison that we're doing.
Okay, more questions?
Thank you. Maybe I miss it, so I'm sorry for that. But at the end, I saw a quark mass and a value for the mu scale that were a bit odd to me. Maybe I saw it incorrectly. Yes. So this quark mass for light quark mass, according to me, doesn't match to this value of mu. Can you comment on this?
I'm not sure if I understand.
Yeah, this value of this 4 MeV mass, MQ 4 MeV. No, yeah, you see, yeah, this one should be the value at the quark mass scale for the light quark.
Yeah.
But then mu is not 19 GeV. It is the light quark mass. So maybe I'm misunderstanding this. That this is my question.
No, the mu is the renormalization point that we are choosing. And the MQ is the seed quark that we are.
I am. That's the seed, and then you evolve it.
Yep.
Okay, you evolve it from mu equals MQ up to this value of mu.
Yeah.
Is that right? Okay, then it's
Exactly.
perfect. Thank you.
Right, we have time for one more question. I think there is one in the chat. Let me see. It's not. So one last question in the audience? No? Let's start the speaker. So our next speaker will be Saxabul Arias Antis. that will talk about jet fragmentation properties with using CMS open data.
Hello. Hi, everyone. I am Saxabul. You can call me Zach. And I am going to talk about this paper, Jet Fragmentation Properties with CMS Open Data. Okay. In 2014, CERN launched this initiative called Open Data Portal, where you have access free to more than 2 petabytes of high energy physics data. Among the data that they share are software documentation and real data from many experiments, also simulated data, but the amount of information that they share is less. There are different experiments that collaborate in this proposal, like ALICE, ATLAS, CMS, and LHCb. Okay, the following analysis that I am going to talk about will regard to jets, so let's define it in our context. For us, a jet is a collimated bunch of particles originated from the hadronization of hard scattered partons produced in hadronic collisions. That is, 2 hadrons collide and a hard scattered parton, maybe a quark or a gluon, originates the jet because of, the generation of new particles that happens there. Okay, even though a jet is a collimated bunch of particles, not any collimated bunch of particles is a jet. As a matter of fact, we have to restrict jets to study them. In this sense, we consider jets with radius of 0.5 and a high jet energy. This is because we didn't use corrections or any kind of unfoldings with the data because it's not available. So we use this range where the CMS, that is the detector efficiency, is accurate or is high. In that sense, we also made thresholds with particle charged energies, for example, charged hadrons or charged leptons. And the data samples that we are going to consider are CMS open data from 2011, and the center of mass energy is 7 teraelectronvolts. Okay, the data samples of these open data are going to be jets, BTAC, minimum bias, and multi-jet. And also we did a simulation with PTIA 8, okay, to compare and to study these data. Okay, our objective is to study and explore the data sets and look for difference or even difference in the results. That is, we are going to compare our simulation with the open data, real data. Okay, in that sense, we are going to define our fragmentation function as follows. For example, we are going to consider the fraction of the energy that some type of particles carry from the total jet energy. In this sense, for example, Z will be the fraction of the maybe charged hadron energy in the jet, and will be considered also lepton energy within the jet. Using Z, we are going to define a fragmentation function that will be our main tool to study these properties of the jets. And it will be as follows. It will be a function of the Z, that is this fraction of the particle energy within the jet and the jet energy. The jet energy is here because we are going to work with different ranges of energy from 120 gigaelectron volts to 1 teraelectron volt. Sorry. And we will define it as follows. Number of NG, NGs, will stand for the number of the total jets in the event. That is, we will normally say to one of results. And this number of charged particles will be considered as leptons or as hadrons. And the segmentations, the x-axis will be in terms of fragmentation function. Okay, the results are the following. Here we have a graph of fragmentation function in terms of the jet energy in the range of 200 to 300 gigaelectron volts. Open market is done for the closed market will stand for the other. In the x-axis we have the fragmentation function, the C function, that is the fraction of the energy that each type of particle will carry from the jet. That is, C will range from 0, for example, there is no leptons, to 1, where maybe all the energy of the jet will be carried by leptons. In that sense, in the y-axis, we have the fragmentation function results. And we have a good agreement in terms of charged hadrons and a peak in almost 0.5, 0.6, where it reached its maximum. In terms of the leptons, we have that the agreement is not as good as in the case of hadrons, where we start with a good, let's say, agreement, and at the end, where the C function is greater, we have more fluctuations, statistical fluctuations. Here at the bottom, we have a comparison from each type of open data to the simulation. That is, we have the radius of the open data result to the simulation, and that is why we have a difference that range from 50% to 50% above and below. Okay, and this is the case from the jet energy in 200 to 300 gigaelectron volts. From another jet energy, for example, a high energy range, that is from 900 to 1 electron volt, we have the following graph. The results are very much the same. The main difference is in terms of the electrons, where we see that the fragmentation function is harder than in the previous case. And this behavior is not defined or simulated by PPI. That is, we have bad agreement in this sense. Another way to study these graphs is not by the range itself, but taking the mean. For example, if we take the mean of all these distributions, we have the following graph, that is the C mean. This graph of C mean will take the mean of the value of Z of different range of energy, depending on the range that we are talking about. For example, we showed two ranges from 200 to 200, and the other was from 900 to 1 GeV, and so on. And these will be the two following means. We have the cases of leptons and charged hadrons. All the analysis that we did was taking jets with radius of 0.5 and in the central region, because of the performance of the detector is better in that region. And also the energies of the particles inside the jet will consider it as we mentioned before. The main advantage that we can see here is that we can study the evolution of fragmentation function as the jet energy increases. That is, for example, we can see a tendency that is almost like an asymptotic tendency in both cases, from leptons and for charged hadrons. In this sense, we can see also that from hadrons, the agreement is pretty good from the case of simulation, that is correct markers and the open data sample. And also the case of the leptons is a little bit worse. And another interesting behavior is that the C mean is greater from the case of charged hadrons than from the case of leptons. Okay, the conclusions of this work are different. We could analyze open data to characterize those. This is interesting because we did not include corrections of any type. That is, we just took the data and perform analysis. Also, we studied permutation functions from charged hadrons and leptons. From the lepton case, permutation function became harder from the high energy range. That is, it increases a little bit. From the hadrons, permutation functions decreases at low and high energy. That is, we have the peak at the center, or almost the center. Our simulation does not describe the permutation function in RC range. And this is more evident when we consider leptons. Okay, that could give us some insight about what we can do about the simulations. Another interesting fact was that we characterized the relation of fragmentation functions in terms of the jet energy. That is, when it increases jet energy, we have different behaviors of the fragmentation function and the C. The most considerable disagreements were in the case of leptons, where it was also really difficult to match the behavior of open data to the simulation. And the C value is larger for hadrons than for leptons. Okay, and at the end, we can say that the results shows the capability to perform analysis using CMS open data, even though we don't have these corrections like unfoldings and statistical uncertainty. That's it. Thank you for your attention. And if you have any questions, the other two authors are over there.
Yeah, thank you for the talk. So, one question. You can calculate some thermodynamic properties. Now you have the partition function, so you can calculate
Some what?
thermodynamic properties, something like energy, density, something. Sorry, do you know calculate some thermodynamic properties?
No, nothing like that.
Okay, and why do you use some? This partition function is like very microcanonical behavior, right? Because only depends on the number of participants.
Yeah, what's in terms of the energy of the participants?
Okay, so you cannot go. Why don't you use something more complex? Something depends of the.
Okay, the simplicity of this analysis was because we just wanted to do an exploratory analysis, not something as formal.
Okay, thank you.
Thank you. We have time for more questions.
A question in the page number 4, you put there some requirements for some variables, but that variables, that the requirements are found based on any maximization of some function like a figure of merit or based of previous works.
We took an insight on previous works. The cut on the jet energy is different from paper to paper. We also, let's say, did the analysis by ourselves. So yeah, it was a combination.
So my question is for the open data. The jets, do they have any corrections or, I mean, are they raw? I mean, how, especially if they have or not, the jet energy scale properly calibrated?
Okay, as far as I understand, in open data, the only correction that JETs fulfill is that they are originated at the interaction vertex, at the center of the interaction.
But there is no jet energy scale applied to them.
No, no, there is nothing. Okay, it's more complex. But we have information about the cinematic.
Yeah, my question is, which kind of corrections should you include in order to have a better agreement, for example, for leptons?
Okay, the efficiency of the detector is the most important and the first one that I would do that I cannot.
Thank you.
Yeah.
Thank you. I think we ran out of time, so let's thank the speaker again.
Thank you.
So the next one would be Adriana Perez Martinez, who will talk about scalar and gauge sectors in the 3 Higgs double model under the S3 symmetry.
Hi, everybody. My name is Adriana Perez Martinez, and I'm going to present the talk with the name Scalar and Gauge Sector in the 3 Higgs doublet model. I want to thank to the organizers to let me the opportunity to present my work in this workshop. And this is a work in collaboration with the Dr. Miriam Mondragon Ceballos and Dr. Melina Gomez-Bo, and it's based on this in this work published. So the outline of the talk is going to be, well, I'm going to present the motivation, what is the 3 Higgs doublet model under the symmetry S3, the Higgs bases, the Higgs couplings that we have in this model, the Higgs one loop self-energy, the numerical analysis that we developed in the Higgs potential, and the summary. So a motivation. Studies has been started in the 70s, hoping to find a global symmetry that explains the mass of the missing parameters, and we have this some reference. And in addition, S3 is the smallest flavor symmetry suggested by the data. And previous works on in the quartz and the neutrino sectors have been developed, given they reproduce the CKM matrix and the max matrix to the quartz and the neutrinos sector, and they develop and they obtain a really good result. So the one was then the flavor. Don't impose any symmetry on their district. For the model, we will have 54 real parameters in the potential, and when we impose this symmetry, we reduce the number of parameters that we have. And also, this is a low energy model, and so it means that it's a testable model. So here we have the Lagrangian on the Higgs sector. The first two terms are related to the kinetic term and the potential Higgs. In the equation number 2, I present what is this Higgs potential. The first two terms are related, or are the square terms, and the less 8 parameter, well, the less 8 terms, represent the quartic terms from the Higgs potential. Here I present what are these three Higgs doublet model under the symmetry SU2. So as you can see, we are going to have 12 degrees of freedom. 3 of them are going to be to give mass to the gauge bosons, and we have 9 remainder. So we are going to have 3 neutral scalars, 2 pseudo scalars, and 4 charged Higgs bosons. We work in the normal minimum, and we have this configuration for this vacuum expectation that we are going to develop in this work, and they need to satisfy this condition. When we obtain the condition of the minimum, we obtain these two conditions. The first one is with the vacuum expectation value of V1 squared is going to be equal to 3 times to the V2 squared. And the second one, the parameter E from the Higgs potential is going to be equal to 0. In this work, we are going to develop the first one, and we are going to work with this condition. So we parameterize in spherical coordinates the minimum of the potential, and we wrote like well, in terms of these two angles and the vacuum expectation value, but using this condition of the minimum, we could fix one of the angles from this parameterization that we are going to have to the vacuum expectation values. So the sin of theta and the cosine of theta are in function of V3 and V2, and also the BEP that we have here. And then, as I will mention, what we are going to have this 12 times 12 matrix that we need to diagonalize in order to obtain the mass matrix from the Higgs boson from the model. So here I present what is the matrix rotation from the, in order to obtain the mass from the scalar bosons and the charged Higgs bosons. And we are going to have two different matrix rotation, one for the pseudoscalar and the charged Higgs boson, and the other from the neutral scalar boson. Here we define this angle alpha that is defined as this division. And here I present what are the expression to the mass that we are going to have to the bosons that the model is going to have. So the first three are the neutral scalar bosons that are in function of in these three function of the parameters of the BEP and the angle theta that we define in the vacuum expectation values that I present in the previous slide. And the fourth equations that I point in here I represent the pseudoscalar bosons and the charged bosons that we are going to have in the model. So one of these three neutral scalar bosons that we are going to have, that we have in the model, one of them needs to be the Higgs boson of the standard model. As I'm going to present, just H1 and H2 are going to be the candidates to be the Higgs boson of the standard model. So here we have sorry, well, you couldn't see, but I show you the Higgs basis from the model. And so in this basis, one of the doublets has the complete vacuum expectation value that we call phi BEP, and the other two are perpendicular to this doublet. So the relation that they give this Higgs basis with the doublet from the SU that we have is using the transpose of the matrix that diagonalize the pseudoscalar and the charged bosons. And here I present how do we define the doublets in the Higgs basis. Here, H1, H2 plus minus and A1 and A2 are the physical states. Meanwhile, these H tilde and H1 and H2 tilde are intermediate states, but we could relate it with the physical state, developing a rotation, as I could, as I show in this equation. And as you could see, well, we are going to work with two scenarios. One, when sin alpha minus theta is equal to 1. So in this case, it means that H tilde is equal to H2. And the other scenario is going to be when cos alpha minus theta going to be equal to 1. So in this case, H1 is going to be H tilde. That is going to be our standard model Higgs boson. So after this electroweak symmetry breaking, it remains a residual symmetry theta C2 that it comes from the global S3 symmetry that we impose over the model. And under this symmetry, this residual symmetry, we have some different charges that we are going to assign, that they are going to have the different Higgs bosons that we have in the model, and results that H0 is solved under this symmetry as the pseudoscalar A1 and the charged Higgs boson H1. And the other ones remain even under this symmetry. So this is going to impose some restriction for the trilinear couplings. Yes, for the trilinear couplings that we are going to have with the gauge bosons and the trilinear subcoupling that these scalar particles are going to have on the model. So related to H0 is solved under this residual symmetry is going to be the couple for the gauge bosons, and the trilinear coupling, the trilinear subcoupling for this scalar is going to be equal to 0. And as I mentioned, we are going to have this alignment limit when one of these two Higgs bosons are going to be related with the standard model Higgs boson. So we have here the kinetic term. These are the kinetic terms, and we could develop and obtain what are the couplings with the gauge bosons, and we obtain that some of them are, at least, well, most of the trilinear and some quartics are proportional to the cos of alpha minus theta or proportional to sino alpha minus theta. So it means that when we take these two scenarios, the ones that were related with the standard Higgs boson are going to have the couplings with the gauge boson. Meanwhile, the other is going to be equal to 0. And the neutral scalar H0, the couplings with the linear couplings with the gauge boson are going to be 0. But we are going to have some of them that are allowed by this residual symmetry that has the model. Here I present some of the explicit expression from these trilinear couplings that we have to the gauge boson, to the different scalars from the model, H1, H2, and as I mentioned, H0 has these trilinear couplings equal to 0 with the gauge bosons. Also, here I present one of the expression from the trilinear subcoupling for the neutral Higgs bosons that we have on the model, and one example for the quartic couplings that we have. However, in this case, I present a reduction in the scenario A, which means that sin of alpha minus theta is equal to 1. And in this case, we could reduce the relation of the angles in this equation number 31. And in that precise scenario, we obtain that the trilinear couplings and the quartic couplings that are related with the, or that we want to relate with the Higgs boson of the model reduce exactly as the standard model, as the couplings of the standard model. The other one remains, well, have a reduction, but we are going to have a terminal Higgs coupling with the other neutral Higgs boson that we are going to have. But remember that in this scenario, this neutral scalar doesn't have any coupling, well, terminal coupling with the gauge bosons. And also we obtain that we reduce this scalar coupling instead of the mass. So here we have a boundary to the masses that the scalars are going to have in the model. And here we take like a uncertainty, or we are going to have like a little we are not going to have the exact scenario or the exact limit, and we are going to have a little amount of quantity to have a deviation from this exact limit. And we obtain this relation that we could reduce the parameter, or well, obtain boundaries to the parameters that we have in the model using the experimental boundaries that exist in actual, but nowadays. So here I present some expression to the one self copy to the one loop self energy. What I want to emphasize is that here I present the expression to the scalar, to the neutral scalar bosons, but related to the residual symmetry that we have, even in this one loop self-energy, it still reminds this symmetry that we have. So here I just want to present the numerical analysis that we developed in those 2011 for stability and in this range, to represent the value of the standard model boson. Here, well, we have the values for the masses to in this case for H0, H1, and H2. This is the scenario A, so this green line represents this construction that, well, these conditions that we impose by hand. And these are the possible values for the masses when they satisfy unitarity and stability, the alignment in the maroon plots, and the green ones are when we impose that they take this value. This is for the scenario A, this is for the scenario B, how the pink dots remains, but the maroon and the green ones change related to the different alignment that we are going to have. Well, this is related with the precision. This is the masses that we are going to have to the pseudoscalar and the charged Higgs boson. This is for the scenario A, and this is for the scenario B. And here are the conclusions. So thank you so much. Thank you.
Well, let's do one question.
And thanks for the interesting talk. Maybe I missed it. Did you make any assumption on CP violation?
No, it's free. Also, so when I could make a restriction on the CP violation, well, I think that will be in the way that we take the minimum value, but we take it as real and different from zero.
Yeah, perhaps, my question
Or
is
in the
related to the
potential.
fact that you are going to the alignment limit in the end, so probably because of this, you are getting rid of any possible effect. Yeah, thank you.
One question. You said at the beginning that this model is testable. You can test the model. How would you test the model?
Well, with the different, well, we have these nine Higgs bosons. So in the energies that the experiment that are developed, we could make some restriction for the values of the masses that this
Yeah, and second question related to that is, can you use the data is already available to test this model?
again, so
Could you use the already available data to
Ah.
test some parameter space of this model?
yes, well, for example, even in the numerical analysis, we take that the masses from the charged Higgs boson will be greater than 80 GeVs. So we take these actual values or these current values that are in the experimental that are nowadays.
Unfortunately, we ran out of time, so let's thank the speaker again. And the last talk of the session would be the plenary one. It would be Lorenzo Diaz Cruz talking about amplitudes, a model approach to QFT and gravity.
Okay, thank you very much to the organizers for the opportunity to present my talk. I'm going to talk about amplitudes, modern approach to quantum field theory and gravity. So I organize it in two parts. The first part is more the research, and I will discuss introduction, then perturbative quantum gravity and gravitons, and the Higgs decay to gravitons, with some conclusions. I will talk in English here, and then I will switch to Spanish because this is like propaganda for the students. I want to talk about quantum field theory and amplitudes, what is quantum field theory, what is a particle, felicity methods, constructing quantum field theory, and again, conclusion. So this talk comes from a project in which I discuss scalars, because now we know that there is a fundamental scalar realized in nature. So there's the Higgs boson, and we know that the properties are in agreement with the standard model so far, but we still need to present more tests to discuss or to study further properties of the Higgs, like the self-couplings, the flavor changing couplings. In general models, we need to see if there are new scalars in nature. There are many, many candidates to the Golden model, like the previous model, is fermions, axions, synchrotron, etc. One of the critiques to the standard model or the limitations is that it doesn't include gravity. So I want to study how will the Higgs couple with gravity, or here gravity means gravitons. So in perturbative quantum gravity, one assumes that this makes sense to discuss these effects, at least in the infrared. Sometimes in the literature, one hears that there is no theory of quantum gravity. However, there is a theory of quantum gravity in the infrared. The problem is to go to the ultraviolet. And like all other fundamental forces, gravity is mediated by a particle. The graviton, which is a fluctuation of the metric, is a massless spin-2 particle. So interaction of two massive particles goes to a graviton, like interaction of two charged particles goes to a photon. So in some sense, gravity and gauge theories could say to each other, like the song of Juan Gabriel, you look a lot like me.
To extract the couplings of the graviton, we need to study Einstein field reaction, but consider as an effective field theory. This has been studied in the mid-90s by Donahue. And here one has an effective answer with an effective Lagrangian, and the effective Lagrangian is split into term for gravity and then term for matter. And the Lagrangian is organized in a number of derivatives, higher derivatives, because this effective field theory for gravity is an expansion in energy. And since the 90s, with the development of effective field theories and the application, for example, to chiral perturbation theory, we know how to deal with infinities, even though it's a non-renormalizable theory. And the coupling of scalars with gravity is the first term is this, the kinetic with the metric and the massive term. And here we also have the square root of the terminal of the metric. And this is called minimal coupling, or minimal scalar coupling to gravity. If we go to higher orders in the geometric objects, the scalar curvature of the Ricci tensor or Riemann tensor, then we talk about non-minimal coupling of scalars with the gravity. So when one does this expansion systematically, it's many terms that appear, and it's very difficult to deal with this all these interactions. So one suspects that there has to be something easier, because at the end the answers are quite simple. And we will talk about this later. But for this part, we did choose this expansion for all these terms. And the Lagrangian that we studied was this, with all these terms, coupling of the scalar with the scalar curvature, then R square, the Ricci square, and Riemann square. And we also consider the coupling of a pseudoscalar with the gravity, and the correct term is given by this expression. So what we did was to expand all the objects and identify all the interactions. And to first order, it happened that a graviton can interact with two scalars, but we don't find a coupling of one scalar with two gravitons. So we need to consider the next term, the next order. And we did this with my collaborators. I will mention them in a minute. So we have all the expression for R square, R mu, and the Riemann square. And apparently in this expression, we have interaction of a scalar with two gravitons. However, when we go to on-shell gravitons, the only contribution that remains is the square of the Riemann tensor. And similarly for the pseudoscalar coupling, we find the expansion with all the terms. So we want to understand this result. We don't have an understanding. We calculated the decay width of the Higgs to gravitons. It's using tensor methods. And in order to have a better understanding of what is happening, we also consider the decay into a three-body mode. The scalar goes to a real graviton and then a virtual graviton that goes to these states. And to discuss it in general, we just consider that actually the coupling of the scalar goes to the energy momentum tensor. And so we wrote again the right amplitude. And again, we consider all the possibilities for the coupling of the scalar with all the geometric invariants. And but we again find that the scalar three-body decays, only the Riemann square contributes. We also we started to work on the loop diagrams with gravitons. And again, we find that only the Riemann square contributes. We don't understand why this is happening. There are some power counting arguments, but we would like to have a deeper understanding of this result. And this was done with Alan Alonso, undergrad student in Honduras, Ana Avilés from the UAP, myself, and Brian Larios, a former PhD student. So we have a preprint, but we have not submitted the publication. I swear that we have it on this side. So, and for that, I jump to the second part. Okay, bueno, entonces, lo que tenemos, pues, es que la teoría cuántica de campos está en excelente acuerdo con el experimento, pero para mayor precisión se requiere un trabajo realmente heroico. Y la filosofía de Feynman, pues cállate y ponte a calcular, ¿no? A veces los estudiantes aceptan la filosofía, otras veces se rebelan y pues hay que convencerlos. Como dice el lema del escudo de Chile, ¿no? Por la razón o por la fuerza. Bueno, entonces en este método, diagramas de Feynman, cálculos tensoriales, etcétera, etcétera. Sin embargo, estos métodos tradicionales para calcular diagramas de Feynman tienen limitaciones y, por ejemplo, en pura QCD, el número de diagramas crece muy rápido con el número de diagramas, con el número de estados finales. Por ejemplo, si tenemos 2 gluones a 2 gluones, hay 4 diagramas, 2 a 3 hay 25 y 2 a 4, 220, y cada uno es una escritura tensorial impresionante. Entonces, por estos métodos no es posible calcular, entonces tenemos que encontrar algo mejor. Y la filosofía de Wilczek pues nos ayuda, dice, usualmente evito el trabajo duro, ¿sí? Y cuando las cosas se ven complicadas es señal de que debe haber una mejor manera de hacerlo. Entonces, nos vamos a qué es una teoría cuántica de campos. En realidad, yo pienso que debería llamarse más bien teoría cuántica relativista, RQT, más que quantum field. Pero es un nombre histórico, digamos, y en este momento, en este periodo de tiempo, no estoy listo para pelearme por cambiarle de nombre a la ahora, ¿qué es teoría cuántica de campos o esta teoría cuántica relativista? Pues es algo que es cuántico y es relativista. ¿Qué quiere decir que sea cuántico? Bueno, se debe parte del postulado de la mecánica cuántica, y en mecánica cuántica pues hablamos de que el estado del sistema se describe con un ket, ¿no? Un vector de estado. Y si es relativista, pues quiere decir que debe respetarse las transformaciones o deben aplicarse las transformaciones de Lorentz. Entonces, debemos estudiar cómo transforman los estados cuánticos bajo transformaciones de Lorentz. Y vamos a ver al final, digamos, de esto, que para trabajar con partículas en teoría cuántica de campos, todo lo que necesitamos es algo. No, quiero decir escritores. Bueno, si hay estudiantes de segundo, tercero de licenciatura, para que no se asusten, para cuando hablamos de espinores, es simplemente, por ejemplo, en el experimento de Stern-Gerlach, que vemos 2 haces, uno de arriba hacia abajo, un campo magnético, átomos de plata, que están en los libros de Moderna. Esos objetos que describen estos estados, espinas arriba, espinas abajo, chi más 1, 0 o chi menos 0, 1, estos son los famosos espinores, ¿no? Y son en estados de componente Z del spin y también del momento angular, ¿no? Y donde el operador de spin se escribe en términos de las matrices de Pauli, X de Z. Bueno, entonces en relatividad pues trabajamos con cuadrivectores de posición, de momento, y pedimos que bajo transformaciones de Lorentz, el X mu vaya a X prima mu dado por lambda mu nu, X nu, ¿verdad? Y esa transformación es tal que el módulo del vector sea invariante, entonces esa lambda debe cumplir esta propiedad. Entonces ahora lo que queremos, como dije antes, es ver cómo transforman los estados bajo una representación de las transformaciones de Lorentz y de traslaciones, ¿no? Donde esta representación pues cumple que la notación de un producto de dos transformaciones de Lorentz es el producto de la representación, ¿no? La regla de teoría de grupo. Bueno, entonces, un paso para entender qué vamos a trabajar es teoría cuántica de campos, es el trabajo de Wigner y lo que se llama el Little Group. Entonces, en esto lo que tenemos es que queremos conocer de qué depende el estado, cómo podemos etiquetarlo, qué etiquetas usar. Bueno, una de ellas tendría que ser el momento, ¿no? Para que respete estas relaciones. ¿Y qué otras etiquetas debo usar? Bueno, ahí me ayuda esta clasificación de Wigner para saber qué otras etiquetas usar. Y lo que este método de Wigner lo que hace es buscar aquellas transformaciones de Lorentz, el subgrupo de ellas que dejen invariante el momento. Porque cuando yo actúe con una transformación de Lorentz sobre el momento, que sea el mismo momento, voy a ver que ese momento no cambia y voy a poder identificar cuáles son esas otras etiquetas. Y eso lo pueden leer en el Weinberg de teoría cuántica de campos de Lubin. El resultado final de esta clasificación es que las partículas masivas se definen con su masa y su spin, y el Little Group es SO3. Y los casos en la naturaleza pues son spin 0, el Higgs, un medio, quarks y leptones, spin 1, WZ. Por otra parte, las partículas sin masa están etiquetadas por la helicidad. Y el Little Group es 1 por traslaciones en un plano. Sin embargo, lo que hemos visto en la naturaleza tiene transformación bajo esto, que es la helicidad. De fase, pero es un singlete del otro, y no se entiende del todo qué pasa con esas cosas que se llaman relaciones de spin continuo. Pero en la naturaleza sabemos que hay al menos dos objetos, el protón y el gluón, que tienen helicidad -1, hipotéticamente hay otro que sería el gravitón, con helicidad de +2. Bueno, ahora para trabajar ya matemáticas, un poquito atrás, no se ve el título, pero es el grupo de Lorentz y Spinore, ¿no? Y cuando tenemos SU2, el grupo SU2, que es isomórfico a SO3, usamos para spin, las representaciones las podemos etiquetar con el momento angular total y una componente, o J de lo que sea, ¿no? Isospin, lo que represente SU2. Pues puede haber representaciones con J0, un medio, 1, etc. Y los spinores son aquellos objetos que transforman bajo SU2 con spin primero. Ahora bien, en el caso de transformaciones de Lorentz hay rotaciones y bus. Los fundadores son J para rotaciones y K para bus. Directamente de J y K no se identifica cuál es el álgebra del I. Pero si hacemos estas combinaciones, JI más menos KI, uno puede identificar que el grupo de Lorentz en realidad es un producto de dos S2. Que le ponemos nombre L y R, ¿no? No, realmente no es izquierda y derecha, son dos etiquetas, puede ser A o B. Entonces, como tengo dos SU2, necesito dos etiquetas, dos índices para los tipos de spinores. Uno de ellos va a ser el psi alfa y el otro, el uso de esta notación, psi alfa punto. Bueno, ahora, ¿cómo hago para usar solamente spinores? Que es lo que prometí. Bueno, lo que se hace es contraer el momento con las matrices de Pauli para obtener un objeto que tiene índices alfa, alfa punto. Y este objeto, escritas sus componentes, está dado de esta manera. En el caso en que la partícula o el momento corresponde a no tener masa, el determinante es 0. Y entonces esta matriz se puede subir como el producto de dos vectores o dos espinores. Y, por ejemplo, si tengo el caso sin masa y estoy en un marco donde el momento va en la dirección Z, entonces el momento es E00. Si yo contraigo esto o sustituyo aquí, me doy cuenta que ese momento es 2C00. Pues fácilmente puedo identificar que los espinores son raíz de 2C, vector 1, 0, y el otro, el tilde alfa punto es 1, 0. Pues puedo ver que haciendo este producto yo obtengo esto. Y si me quiero ir a un momento arbitrario, pues juego con rotaciones, ¿no? Pero la esencia del método de licidad es esta, identificar que el mismo momento lo puedo describir con espinores. Lo mismo puedo hacer con los vectores de polarización que necesito, las funciones de onda para los estados externos en una amplitud. Esos son para el fotón, por ejemplo, dos polarizaciones más menos, los contraigo con la matriz sigma y tengo una combinación alfa punto. Si tomo este caso, pues veo que esto es de la forma 0,0 raíz de 2. Otra vez tiene determinante 0 y lo puedo poner como el producto de dos espinores. Pero como ahora necesito polarización más y menos, utilizo dos espinores. De esa manera, pues, no le gusta más. Bueno, entonces ya tengo todo en términos de espinores y puedo calcular amplitudes y luego hay una serie de fórmulas para contraer espinores que me van a dar momento. Es muy fácil verificar que esta manera de describir las polarizaciones cumple todas las propiedades de Entonces, al final de este estudio, es que es liberado la difusión de las externas de conventos en cualquier lenguaje. Un ejemplo de este método híbrido es, por ejemplo, esto está en Schwarz, Quantity Theory, es long scattering, long. Es híbrido en el sentido de que yo escribo un diagrama de Feynman, escribo la amplitud, y luego lo que hago es simplificar utilizando este método, todos los productos. Por ejemplo, para el canal S, aquí está la respuesta, y muy fácilmente, dependiendo de cómo elige uno los vectores auxiliares, los eta, para la polarización, pues se llega a una respuesta pues, muy inmediata. Y similarmente podemos ver que para esta configuración de helicidades, menos, más, el canal T da 0 y el canal U da esta expresión. De modo que al final la amplitud que tenemos está dado de esta manera, ¿no? Todos estos son productos de espinores, es la contracción de dos espinores alfa y la del cajas es de los alfa puntos. Ahora se usa 1, 2, 3 para representar los momentos. Entonces se calcula muy fácilmente el módulo al cuadrado de amplitud y llegamos a la sección eficaz con este método, ¿no? Entonces, yo creo que eso ya tenemos que aprenderlo en los cursos de teoría del campo, en la licenciatura y la maestría. Bueno, ahora, ahí traté un método híbrido. Me gustaría todavía ir más allá y ver si podemos construir la teoría cuántica de campos directamente de los objetos que estemos trabajando. Hay una pequeña nota histórica, me la voy a brincar. Entonces, pero la pregunta es, ¿podríamos trabajar en teoría cuántica de campos con amplitudes físicas que se construyan directamente con los objetos que vamos a trabajar? ¿Cómo Heisenberg quería trabajar mecánica cuántica? Bueno, entonces otra vez, para eso necesito estudiar el Lie Group y ver cómo transforman los espinores. Y como bajo el Lie Group el momento es invariante, entonces, por ejemplo, yo puedo pedir que lambda transforme con un factor, una fase, y lambda tilde con la fase a la -1, de modo tal que este producto se cancele este factor y quede como un invariante. Y puedo entonces ver que por ejemplo, las polarizaciones, estas matrices van con t a la -2 para más o t al cuadrado para menos. Luego lo que hacemos es construir cómo es una amplitud y cómo transforma bajo el Lie Group. Entonces, además utilizamos conservación de momento, P1 más P2 más P3 igual a 0 para la interacción de 3 puntos, que es nuestro primer objetivo. Entonces, hay dos soluciones. Que los productos de los espinores alfa sean de 1, 2, 2, 3 y 3, 1 sean 0, quiere decir que estos son proporcionales, o que los productos de los espinores puntos sean 0, los lambda tilde sean proporcionales. Entonces, todo lo que uno hace es checar cómo debe ser la amplitud, entonces tiene que ser una potencia de los productos espinoriales. Por ejemplo, para un caso van a ser estos productos y luego uno ve cómo transforman ambos lados y resuelve. Hay un factor -2H1 de un lado y uno ve cómo que va a aparecer cuando cambie el momento 1, está aquí y aquí. Y entonces aquí está N3 y aquí está N2, pues aquí están. Entonces lo que hago es resolver este sistema. Y simplemente con esto obtengo que la amplitud para la interacción de 3 partículas con helicidades H1, H2, H3 tiene que ser de esta forma. Y ya, terminé. No hay grupos, no hay SU3. Ya están aquí las interacciones. Por ejemplo, lo puedo aplicar para gluones, para 3 gluones, off-shell, porque si no sería 0 el vértice. Pues, por ejemplo, cuando tengo 1 menos, 2 menos, 3 más, esta es la solución. O cuando tengo más, menos, esta es la solución. O 3 menos, estas son las, o más, son la solución. Ahora, estos son antisimétricos, entonces tengo que poner un objeto antisimétrico para que sea diferente de 0. Y justamente ahí es donde aparecen los factores del grupo. Digamos que la teoría de Yang-Mills la obtuvimos por la reacción de imponer las condiciones que deben cumplir el grupo. Si consideramos partículas tensoriales como el gravitón, encontramos estas expresiones para menos, puros menos, o puros más, o 2 menos y un más. Y lo interesante es que estos resultados son el cuadrado de esto, como el cuadrado de esto. Este resultado es como el cuadrado de esto, y este es como el cuadrado. Entonces, parece ser que lo que se dice en este lenguaje es que la relatividad general es Yang-Mills al cuadrado. Entonces, pues no pudieron menos que decir que esto es Bueno, y hay más resultados en esto que le llamo joyas perturbativas, en amplitudes. Por ejemplo, hay una fórmula que me dice cuál es la amplitud cuando hay n gluones en una reacción, que hay 2 helicidades menos y el resto son más. Y esto se llama la fórmula de Parquet-Taylor. Esto es imposible de obtener con los métodos tradicionales. De hecho, hay un juego ahí entre teoría de cuerdas y teoría del campo que se ayudaron para llegar a esta fórmula. Luego hay algo que se llama relaciones de KLT, como lo que escribí antes, en que las amplitudes de gravedad se escriben como el cuadrado de amplitudes de Young para 4, 5, 6 partículas con diferentes combinatorios. Hay algo que se llama la doble copia, hay Taylor para calcular loops, hay algo que se llama la dualidad color cinemática, hay una teoría que n igual a 4 super Young-Mills, que es lo que se conoce, se considera la teoría más simple. Y un ejemplo de ese tipo de resultados es, otra vez, por ejemplo, si yo obtengo el vértice, usando teoría del campo tradicionales, obtengo el vértice para 3 partículas, 3 gluones, que está dada de esta forma, con Shell. Y uno ve que la amplitud para gravitones es el cuadrado de esto. Bueno, entonces con estos resultados me regreso a lo que empecé, mi acoplamiento de Higgs con gravitones. Si tengo un escalar y 2 gravitones, pues directamente obtengo las amplitudes, simplemente los vehículos reales a la cuarta, de este tipo o del otro. Y estos, por cierto, son el cuadrado del acoplamiento del Higgs a gluones. Pues otra vez se cumplen estas relaciones y esto coincide, debe ser, ¿no?, con este resultado que tuvimos antes utilizando toda la maquinaria sensorial. Pero esto en un renglón. Lo que acá toma páginas y páginas de índices, aquí es un renglón. Entonces, ahora creemos que entendemos un poco más por qué esa simplicidad de los resultados que obtuvimos. Y esto, contando el número de derivadas, se ve que tiene que ser Riemann. Todo lo que dije antes es para el caso sin masa. También se ha estudiado el caso con masa. Es un poco más complicado, pues porque si, por ejemplo, nos vamos a un sistema en reposo, esta matriz para una partícula masiva, esta matriz tiene esta forma, ya el determinante de 0, obviamente, b cuadrada es m cuadrada. Ahora necesito 2 espinores para trabajar, y es un poco más latoso, ¿no? Esto lo usamos, o algo parecido, para estudiar gravitino masivo en la tesis de doctorado de Brian Larios. Recientemente, bueno, para reciente, 2017. Esa es una cosa que pasa, ¿no? Cuando le digo a los estudiantes, lean este paper del 2000, dicen, es muy viejo, es nuevo, ¿no? Bueno, entonces este paper de Kahneman propone usar otra vez el Little Group para trabajar de manera sistemática el caso masivo. Y bueno, es el trabajo de progreso de cómo usar esto para todos. Bueno, conclusiones. No asustarse, no ser tan conservadores, ¿no? El lenguaje de la teoría del campo ha evolucionado con el tiempo. Si uno se va a los papers de los 60, ahí aparecen muchas corrientes. De hecho, había algo que se llamaba álgebra de corriente. Luego nos vamos a 70s, 80s, el lenguaje son lagrangiano, ¿no?, que es el que estamos acostumbrados. Y ahora el lenguaje está trabajando en estos productos, ¿no? Por ejemplo, hay teorías efectivas, lagrangianos efectivos, ahora se estudian con espinores y se encontraron propiedades geométricas con una riqueza que se entiende mejor conceptualmente. Bueno, entonces conclusión es el acoplamiento Higgs-gravitón es una arena interesante para aprender y jugar. Incluso más allá, tiene interés físico, ¿no? Por ejemplo, el decaimiento de Higgs a gravitones, o de un escalar a gravitones en el universo temprano va a dar lugar a gravitones que podrían eventualmente estudiarse y detectarse. Podemos decir que teoría del campo pues reina en muchos dominios, de LHC a las estrellas, superconductores, el universo temprano, etcétera. Amplitudes y el método de velocidad pues son como un superpoder. Hay joyas perturbativas que hacen muy interesante estudiar estos métodos. Es posible estudiar teoría cuántica de campos con el Little Loop, que es, digamos, constructible, y hay el caso masivo que se está estudiando. Todavía, digamos, mi meta final, ya antes de que es estudiar teoría cuántica de campo como con la información mínima. Si un electrón choca con un fotón, ¿qué hace el electrón? Entonces, ¿sabe el electrón de la lagrangiana? ¿Sabe de la acción? Yo creo que no. Yo creo que el electrón lo único que sabe es decir sí o no. Entonces, me gustaría conseguir una teoría del campo a partir de sí. Y, curiosamente, hay lenguajes, otra cosa que estamos estudiando, que se llaman twistores, en el cual las amplitudes son eso, unos y ceros. Entonces, pues con esto concluyo, ¿no? Invitación a los estudiantes a que aprendan estos métodos. Estamos haciendo nuestro esfuerzo aquí desde Puebla, pero para mi gusto, hay mexicanos en el mundo que están trabajando en esto. Gente muy talentosa, que son postdocs en Inglaterra, en Italia, en otros lugares. Y yo pienso que este es el futuro de la teoría cuántica. Y no podemos quedarnos muy tradicionales. Que la comunidad mexicana es conservadora, es moderna, cambio, inercia. Y bueno, entonces les agradezco su atención.
Muchas gracias. Tenemos el tiempo suficiente para preguntas.
I think I have two questions in español. I will ask what you let me, okay? So one, can you comment on the case where curvature is not negligible for the EFT?
Sorry,
The case where kappa is not small for the EFT, when you were discussing the EFT for general relativity at the very beginning.
the kappa terms.
Yes, when kappa is not small, yeah.
Yes, in the language of effective theory, only the lowest order term, we know that kappa is the Newton constant for Planck mass. But the next ones, in the language of effective theory, we have to assume that they are small. So that because if you talk with people from general relativity, they tell you that R plus R square theory is inconsistent. But because they consider a fluctuation of the order of the Planck mass. But if we consider that the R square has a small kappa, then that's consistent. It's a small correction, and you can derive corrections to the middle potential, etc.
Yeah, another question is something I know you like a lot. Maybe in the examples you discuss is of no interest, but in general, do you have extra contribution from gravitational anomaly?
I don't know if what I say will answer. We have talked only a little bit about gravitational anomaly. And we want to identify if it's also possible to write it as the square of the Yang-Mills anomaly. But we haven't gone further than that.
Very interesting. So, ahora en español.
Let's go to have a beer, Pablo.
Okay. Yeah, we continue during lunch when you can. Yeah. Otra es en la doble copia. Eso es muy bonito. Sí. Yo creo que sería interesante todo el mundo que lo lleva mucho tiempo y mejor no.
I think I have something to. This is more like the cinematic, right? Let's stop here.
Vale. Cuando hablabas de, digamos, de la aproximación del lagrangiano, amplitudes, todo lo que estabas discutiendo, al final método de helicidad, en principio también podría entrar ahí la aproximación de S-matrix, ¿no?
¿Principio más que?
De matriz S. Eso, o sea, tenías una slide donde ponías las distintas aproximaciones, ¿no? De lagrangiano, de método de amplitud de helicidad, etcétera. Entonces, en principio, también volviendo a ideas de lo que mencionabas de la álgebra de corrientes, ahí estaría matriz S, que también fue popular hace muchos años y ahora se sigue usando, ¿no? Entonces,
Sí, de hecho esto es como un renacimiento del programa de la matriz S.
Será en español porque es como para estudiantes. Si el Higgs se acopla con el gravitón, ¿qué implicaciones tiene para el principio de equivalencia? Entonces, si la masa, o sea, porque el Higgs de alguna forma le da masa inercial a las partículas, y por otra parte tenemos la masa gravitacional. Si el Higgs se acopla al gravitón, ¿hay alguna implicación sobre el principio de equivalencia o no sé?
In this diagram, we have the interaction of two particles that interact with the graviton. And we use the couplings of that are derived. In principle, you have the gravitational and the other mass. Inertia. Okay, this will be the inertia. But when you derive the Newton potential, then using this, you prove that that mass is the gravitational mass. So in a sense, the equivalence principle is incorporated in the formula. Something that strikes me about related to your comment is that the graviton couples to the matter to the energy momentum tension. In some sense, the Higgs couples with matter through the trace of the energy momentum tension. So that suggests that maybe there is something between the graviton and the Higgs. But that's hypothetical.
¿Alguna otra pregunta? ¿Algún estudiante que se anime a preguntar? No, entonces agradecemos al orador, por favor. Don't know if there's any announcement by the organizers or we can just go for lunch.
Yael Irante, ¿cómo escucha el audio en la sala? ¿Puedes hablar, Yael? No te escucho, Yael.
Hola, hola.
Ah, ok, bien, ya te escucho. Un poco bajo, ¿eh?
¿Me
Tengo
escucha,
todo el volumen.
¿Se escucha bien o no se escucha bien, doctor?
Se escucha un poco bajo. No sé si pueden subir el volumen de alguna manera. Tal vez si le suben el volumen a la computadora que está en la consola, tal vez eso ayuda.
Sí, ya hace rato le había subido al máximo. No sé si se haya modificado.
Sí, me cuesta un poco de trabajo y tengo todo el volumen. ¿Puedes probar con el otro micrófono? Tal vez se le está bajando la pila.
¿Me escucha, doctor?
Sí, sí te escucho, pero sigo escuchándote un poco bajo. Y tengo al máximo mi volumen.
Ahí me escucha mejor, doctor. ¿No?
Un poco, bueno, ligeramente. No sé si ya incrementaste el nivel de tu voz
Sí, está al máximo en la aplicación de Zoom.
en la aplicación. Y de la consola no se podrá subir un poquito, ¿no anda por ahí alguno de los compañeros que nos han apoyado?
Modificando desde la consola, doctor. A ver si- No, ya tiene todo.
Sí, ya es todo el volumen que se puede obtener del micrófono, doctor.
Doctor,
No
nosotros,
te
nosotros lo
no,
escuchamos.
me cuesta trabajo escucharte, ya. Le subieron a la computadora y a la consola se puede.
Me comenta que la consola solo es para el volumen externo de aquí de la sala, no para el del Zoom. El de allá sí.
¿Puedes hablar otra vez?
El volumen de la consola solamente es para el volumen de la sala.
Bueno, ahí ya te escuché un poco mejor. No sé si ya llegó Jonathan Reyes, que iba a ser el moderador.
Sí, sí, ya llegó.
Ah, ok, muy bien. Entonces, por favor, díganle a las personas que van a hablar que hablen fuerte, ¿no? Creo que tú aumentaste el volumen de tu voz y ya se escucha un poquito mejor, pero por alguna razón bajó la ganancia del micro. No sé si te vas a las opciones de Zoom de la computadora que está en la consola, si te da oportunidad de subirle manualmente el nivel.
Es lo que hemos intentado, pero ya está en el máximo en Zoom.
Ya. Ah, ok, ya está en el máximo. Ok, bueno. Así ya se escucha un poco mejor. Sí, sí cuesta un poquito, pero bueno. Este, díganle por favor a Jonathan que les avise a las personas que van a hablar que hablen fuerte.
Él es el presentador.
Okay, good afternoon. In the next section, we have Pablo Roy from Simvestab, who is going to talk about radiative corrections in semi-electronic code case and reliable new physics tests. Please go ahead.
Thank you very much. Okay, so thanks a lot for the organizers. They have done a great job to gather us together again. That was really very much needed. So I'll be discussing this topic, these radiative corrections in tau decays that are not purely leptonic. Okay, you see, this is lepton side, and here it is U bar, and this that can be D or S quark with some given weights, no, by the Cabio angle. So I'll be discussing interesting things that can be done with this, especially the new physics test that one can perform, right? So the most of the talk will be about these radiative corrections and applications for one meson channels, okay? So it is the tau decay either into a pion or into a chaos. And it is very interesting to perform this kind of comparison. I will explain later. So this bulk of the talk is based on the work that Gerardo, who is sitting somewhere there, has done also with Marco Arroyo and Gabriel, Nacho Roself, and myself. We were also around, right? They are extremely good people, quite young. And we are very glad that they are having some funding for the near future. Gerardo is coming with us with the formerly called Cátedras, and Marco is also with Lorenzo for some time. So I am particularly glad of this because they have been doing a great job, and I'm sure they will continue to do this. Okay, and in current times it's difficult. Okay. And this part of the talk is based on this JHEP and PRDL. Okay. So I'll start motivating why this is interesting. Then the main target is this ratio. I will explain why. So I will devote some time for the numerator and denominator of this ratio, then the ratio itself, results, applications, and conclusions. Why is this interesting? You see it pictorially very easily here, right? So it is decay of a tau, either into a pion or a kaon and a neutrino, over the decay that is obtained just by crossing symmetry, okay? So final state here is initial state here, and then lepton line here is converted into this lepton line here. Everything should be the same if lepton universality holds, right? So if it is the same strength for taus and for muons, and this is precisely what you are testing, that is a prediction that stems from gauge symmetry. Okay, so it is extremely important. Right, so then motivation. As you know, lepton universality, I have just said, is a pillar of the standard model. So violations of it are telling something really interesting or possible new physics behind it. A few anomalies have been observed in semileptonic B-meson decays, mostly in B-meson decays, but in other parts as well. And this, I forgot to update this. This will be covered by Mick, I think, Thursday, right? Okay. All right. So then, another thing I wanted to say, this is important that I don't forget to say, is that when I gave this talk last week, first half of the talk was the same that I'm going to discuss here, and I had the same time, so I had plenty of time. And what about the second half of the talk? The second half of my talk will be given by Juanma, I think Thursday, okay? And I got a lot of questions for Juan Mas talk. Okay, for the part of the talk I'm not giving here. So if I don't get any questions, I'm fine. But I wouldn't understand if Juanma doesn't get a lot of questions. What he will be explaining is really very interesting. So please take note. Please take note of this. Okay, so this is the ratio I told you about. Okay, and then this is precisely testing lepton universality, as I have explained. Besides this, there is this factor that it is the leading order result, which is given just in terms of masses that are very precisely known. Okay. Besides this, what is left? The radiative correction. That's why they are very important, because if you don't get this precise enough, then you are not improving your understanding of this probe of lepton universality, right? So this is our target. This was computed long ago, and these were the results, and there are both phenomenological and theoretical reasons to improve what was done in the mid-90s. Okay, I will explain this. Right, so using the old results for the radiative corrections in this observable, here P, it's either pi or K, okay, here and here, either pi or K, like here. When you take this ratio with the old radiative corrections, the HFLAB report that was published last year, okay, obtain these results for the ratios that are 1. Sigma for pions and 1.9 sigma for kaons away from lepton universality. Okay, that is the previous result. You will see that with our improvements, we get closer to universality. Okay. Now, what about other probes of the very same property? It's the very same properties, G tau over G mu. You can do it just leptonically. Okay. You take tau to electron and neutrinos versus muon, well, I mean, muon decay, muon to electron and neutrinos. So the part concerning the GE coupling is the same, so it cancels out in the ratio, and you are again probing GT over G mu, G tau over G mu. And in this case, the agreement with lepton universality is wonderful, less than 1 sigma. Right. Now, more interestingly, there was for more than 20 years, since LEP times, a deviation in this ratio, tau over mu, also in tau over E, from the LEP experiments, as I said. And this was tantalizing because it is a high energy probe, relatively high energy, because it is W decays. Here, Ws are virtual. Here, these are real Ws. Okay, so people were paying attention to this deviation. But thanks to the wonderful work done by the LHC, CMS, and Atlas collaboration, now this has vanished completely. You see, the new results by CMS and Atlas are in extremely good agreement with universality, both for tau to mu, that is what I'm talking about, and also for tau to E, that I'm not covering. So after this, you need to re-examine this and see if something is going on here or not. Okay. Yeah. So after this pheno motivation, what about theory? So from the theory point of view, it was clear that the old evaluation had some flaws. Okay. For instance, something as simple as this. You may imagine you're radiating the photon, and perhaps there is some hadronization involved where you are radiating the photon. So with this same hadronization, you can either have a real photon or close the loop somehow and have a virtual photon. It is evident that the hadronics part is exactly the same, okay? But they were not doing this. Okay, so there are other things. For instance, the errors, it's impossible that you get the errors they are quoting unless you are doing something that is extremely well controlled theoretically, like APT. But this is not the case in tau decays. In tau decays, resonance dynamics is important. It is impossible to have the error they quoted. And for instance, they were splitting artificially the loop integrals, and then the separation scale was in the results. This is completely unphysical, so there were several reasons, as I said, and others to revisit their analysis. So as a result, we will improve existing evaluations of this. Also for tau decays into either pion and kaon, our radiative corrections can be used directly. And we have performed some CKM unitarity tests in tau to kaon and in the ratio tau to kaon over tau to pion. Finally, some constraints on possible non-standard interaction using these decays, extending work done previously by Chirigliano's group and by ourselves also. Okay, so let's go to pion or kaon decay. Yeah, so this is the cleanest scenario in this respect. This is just chiral perturbation theory up to order E square P square, which is very precise. Everything was settled in this type of evaluations by Marciano and Sirling long ago. These are extremely well-known papers. Here, I am quoting results from Cirigliano and Rosei, our co-author in this paper, who still have the most precise evaluation for these PyL2 or KL2 decays, including radiative corrections. So that's the decay. This is the leading order result, again, given in terms of things that are known with great accuracy. Then you have the short distance electroweak correction. This also is perfectly controlled. Then there are corrections, radiative corrections, that are evaluated as if the pions or kaons were point-like with unit charge. This is perfectly defined. You can compute it and there's no ambiguity. So the first line has basically no uncertainty. Okay? Then errors come in the second line, particularly in the blue coefficients. The blue coefficients are not fixed by the theory. Okay, you need to go to the experiment to fix them. Fortunately, once you apply the EFT machinery, it is not 5, the coefficients that are bringing you uncertainty. It is only 2 combinations of them, right? And what do you do to control the uncertainty here? You need to take into account something that makes sense both at low and high energies. For this, these precise limits are perfect and fine. The chiral and the parton both behaviors with anything that makes sense, basically. But to be more specific and do things slightly more formally, it is a Lorentz expansion of QCD. Okay, if you do this for a given set of green point, endpoint green functions and related 4 factors, you can do things under control, right? And this is what we did. Okay, we did it in the tau decays, and similarly it was done here in this computation, and this was giving the main uncertainty in this particular case. Okay. Now things get dirtier, okay, because this is tau decays, and here you cannot just tend with KPT. You need to supplement this with explicit degrees of freedom that are the resonances, and this brings in additional uncertainties. Okay. The structure is pretty much analogous to the previous case. So things that are extremely well known here, also here, and this part can be computed without any error. Then again, uncertainties come in the second line. Here in the second line, I have split them. This I didn't do before. Why? Because here I'm splitting real and virtual corrections, and the real correction turned out to be negligible in pion and kaon decays. Okay, so that's why I wasn't splitting them before. But now this is not negligible, so I am separating them for convenience. Okay, so the real part of the computation, this we computed long ago. This was in my thesis with Thieu Guo. And for the virtual part, there was no satisfactory computation which was complying with every known property. So this is the novelty of our work here. Okay, so as I said, you have here one example of radiation involving an hadronic blob. Okay, there's some hadron physics here involved. So you see very clearly that you can either close the loop with the photon or just detach it from here or move it from here up to there and detach it there. I mean, there are several combinations. The point is that you get the virtual corrections and the real corrections, detaching the photon somewhere, with the same hadron input. And this is something we are doing correctly, and they weren't, right? So there are 3 structures, 1 in the vector current, 2 in the axial vector current, and once you use all symmetries, all hadron information is encoded in these 4 factors, 1 vector and 2 axial. This is the LU computation. Marco and Gerardo are masters doing this. And then, well, for the 4 factors, what did we do? we obtained these four factors in a scheme that is accounting for every known property for 2 and 3 point green functions. Okay, and it complies with the known chiral and U3 limit, with the Parton one, and it is written in terms of few parameters because these vector and axial vector resonance masses are effectively resumming the infinite tower of interactions that you have in the Lorentz limit. And I mean, from other observables, we know how the correspondence works. So we have quite good control on these parameters. Okay, very good. Yeah. Okay, so this is the information going here. Now I'm moving to the corrections that are, say, easy, no? The structurally independent part. This is with when you see the pions and kaons from very far, no, with very low energies, if you wish. This is completely specified, and the computation check the results by the old evaluation. But I have to emphasize that our writing is more convenient. Okay, it's identical, but it is better to write it in the way we did. Okay. This is a dominating correction. It's of the order of 1% or a bit more. Okay. Then we go to real photon structure-dependent contributions, and here, as I advance to you, in the pion or kaon decays, this is negligible. Okay, really negligible. 10 to the -8, 10 to the -5, but not for the taus. For the taus is of the order of 0.15, 0.18%. Okay, it is certainly one order of magnitude smaller than this one. But you will see in the next slide that there is a cancellation working extremely fine for the pion case and not that much for the kaon case, which makes that in the end, this contribution is indeed important, especially for the pion case. Okay, you will see it in a moment. Keep these numbers in mind. So 1.7%, 0.15, 0.18%. Now, as I told you, when you go to the remaining part to the big virtual correction, this turns out to be on the ballpark of -1%. So this -1% is basically canceling very, very finely here and not that much here, this contribution. So then this becomes basically the result. Okay. Yeah, and here you obtain this by noting that this is a ratio. So when you split the corrections, it is numerator minus denominator, if you wish, for the corrections. And these corrections individually turn out to be of similar size and different signs. So then in the end, they are adding up. This is how you get this -1 here and basically the same here. And then I'm sure you have noticed our errors are very large. Okay, but this is not bad. Okay, I will try to convince you of this. And in fact, in the last part of my talk, we improve another result, and there we reduce the error. I mean, reducing or enlarging the error doesn't have to do with improving the evaluation. The important thing is that your uncertainty interval is reliable because you are going to use this for new physics tests. Okay, so it is not reducing the error. If you can, fine, but if not, it is better to keep it reliable. Okay, so for KPT, I don't need to insist. The errors are small and controlled. But now what about taus? This is the most difficult thing here. So we have two sources of uncertainty. And the good point is that one of them is more difficult to evaluate than the other, but luckily for us, the one where this is very, very well specified is the dominant one. So then we can say, okay, this is for sure our error. So what are these two sources of errors? One is, as you may imagine, are the four factors. Okay, I told you, we do something that is quite accurate for 2 and 3 point green functions. But you can tell me, okay, and why don't you do it for 4 point green functions as well? Okay, because it's pretty complicated. If you do this, it's a nightmare. Instead of doing this, we have experience from simpler settings showing that if you compare something that works just for 2 point functions to something that works for 2 and 3 point green functions, then this gives you a reliable estimation of the error. Because in these simplified cases, we also know how things are for the thing that is complete up to 4 points. Okay, these are very few cases, much simpler than this. Okay, when we do this, the errors are basically half or less than our final error. And this is good because I told you, okay, this is less control. Here, everything is crystal clear, if you wish, okay? Because here, you just use the mu dependence that you get from the loops. You know this extremely well, you know the coefficient. So you only need to vary the mu scale in the interval that corresponds according to the physics of the process. That is this one. This we learned from Marciano and Sirling 30 years ago, okay? So this is a conservative estimate, and it is also perfectly defined. So this gives this error, and this is why we can say what we will do and what others will do are reliable new physics tests, okay? This is the summary, okay? So this basically cancels with this one here, and then you get this number with this error. And for the kaons, so this basically 0.8 is added to this one to get this number. Uncertainties not quoted are negligible, right? And this is a reminder of everything that was improvable in earlier evaluations. Okay, so I'm coming to the applications. First one, it is of interest just to know the radiative correction that applies to tau, to pion, or a kaon. Written in this way, it is this factor here, and here it is written. Okay, this is something that can be used for several applications. The most interesting thing is this lepton universality test I was telling you from the very beginning. These are the factors. You get this ratio of decay widths of branching ratios just from the PDG. These are masses also from the PDG. This is our improvement, these radiative corrections, and then you just test this ratio. And these are the results. If you see sigmas, it is pretty clear that the improvement in the pion case is sizable. It was 1.6 sigma, and now it is 0.9 sigma. As expected from other cleaner probes, we get closer to lepton universality. Then if you go to kaons, you barely see our improvement, but you understand why. Because this number is completely dominated by statistical uncertainty. So with improved measurements, it is very likely that then our improved computation will show up, and that this ratio will be closer to unitarity. Okay, but for this we need Belchu people, our colleagues that are working very hard at Simvestab and other institutions in Mexico to do this. They will do as soon as possible. All right, so then another application is the CKM unitarity test in this ratio, tau to kaon over tau to pion. This is the formula. You see all formulas are one line. It's very nice. This you get from the PDG. This is now there is some hadronic information needed, unlike before. But this is extremely precisely obtained from the lattice, okay? And then you use our radiative corrections and masses that are very precise. In this way, you obtain BUS over BUD. You don't obtain directly BUS. You obtain BUS over BUD. And the number that you get is in excellent agreement with the one from kaon decays, though our uncertainty is twice, basically. Again, we will be very much benefited from improved measurements in tau to kaons, right? Okay. For this, obviously, for the unitarity test, you need to take a BUD from somewhere, and we take it, obviously, from the best world measurement by Hardy and Tauner from super allowed beta decays of Fermi time, right? Yeah, okay, this is just to insist on the fact that we are conservative, no need to go through it. All right, so another application is the CKM unitarity test just using tau to kaon, okay? Now this is the formula. And here, lattice is just slightly less precise than before, but still quite accurate, okay? And then you get radiative corrections, our result, everything, and then this value of BUS. As it always happens, tau decays into strange particles like kaon pion, and all that, are below what you expect according to kaon decays, KL3 decays, and all that. So this you see in our results, where our number is smaller. And depending on what you compare with, we are competitive with this thing that uses all Keon data, or we are not if you go to the KL3 case. So again, it's like that. Right. Okay, final application. Training non-standard interaction. Okay. This is something pretty new, and in fact we were the first to do this for TAUS, okay, in a paper with Stella, with Michelle, and with Gabriel, okay, and this is something we have been working, and it's interesting. All right, so this is the result that you get, and let me point to you to some things that are not straightforward, okay? Here you see BUD tilde, you don't see BUD, okay, or BUS, no, depending on the channel. So what's the tilde? The tilde is that you need to get if you G Fermi from somewhere, okay? Namely mu and decay. But and then you may wish to get GF BUD again from somewhere like super low Fermi decays. But when you do this, it may be that there was already new physics there. So your G Fermi may be polluted by new physics, and your G Fermi times BUD may be polluted by new physics. So what you need to do is to define something that takes out this new physics, and this is the tilde thing, okay? So the new physics contributions that may come in this product are already here. And this you notice immediately because this is TAUS, and here you see electrons. Why electrons? Because you are getting GF BUD from the Fermi beta decays, okay? And this is electrons, okay? Also, this is vector current, and you see this is vector current, this is left plus right, well, minus left minus right, okay? But this is why this appears here, okay? Then, in addition to this is axial current, so axial current is left minus right, and this is why you get this, but now this is purely tau, this is not something that contamination coming from somewhere else. This is what you get in this process. So this explains these coefficients here. And in addition to this, you know that the divergence of an axial current gives you a pseudo-scalar current with proportionality factors that are masses. And this is what you see in this last term here. Okay, so you understand where everything comes from. The rest is indeed straightforward. Okay, the rest are the measurement, this you get from the lattice, the decay constant, masses, you know everything. So if you do these tests, you get these numbers. Don't worry about the numbers. Just we can check that they are in agreement with earlier evaluation by us and by other people, with slightly more reliable errors because here it is not that important, the relative corrections. But more than these numbers, what can tell you something is the new physics scale that is probed by these numbers. And this is between 3 and 40 eV in these two cases, okay, 3 and 40 eV. This, in general, is not competitive with chaos. But when you take the overall pictures, in some directions of parameter space, it is indeed complementing chaos. So, I mean, it is the most we can do, and it is already interesting. Okay. Good. So with this, I come to the conclusions of this part. I told you the most important thing is this one. And we have done something that is useful. Okay, you already see it in the Pion case. We reduce the uncertainty below 1 sigma. And for Keons, you will see it with improved data. Our CKM unitarity test here is competitive with Keons and same trend of slight deviation from unitarity. And here it is not that much. Here we really need improved measurements. And here, as I told you, depending on where you look at, it complements a bit Keons. And this has been received very well by the community. And particularly, it has been used in the very recent HFLAG. Okay, this is to be published in PRD soon. Okay, so from now on, our radiative corrections will be used until lattice can do this better. Okay, this will happen at some point, as with everything that you do in hadron physics. Okay, this is the fate, but for the moment, we are happy. This moment will come. Okay, so this is also to insist how important lattice is. Lattice in Mexico is not as developed as is mass, and lattice is great. Okay, so this is reliable new physics test for present and future experiments. I hope I have convinced you about this. This is just a technical slide discussing that it is really a coincidence that our central values are so close, because in the end, you need to compare things that you don't know, even if they are physical in the old evaluation, but in the end, central values are very close. But of course, one cannot forget that the physical thing is the confidence interval. Central value is immaterial. It is this with the uncertainty attached. Okay, so with this, I come to the last part of the talk, that is the shortest one. Now it is more complicated. So it's basically the same thing, but now with two mesons, okay? This, for the PyPy case, was done by Alex in his thesis, because this was interesting for a mu, okay? I will tell something about this in a moment. But of course, once we are doing this, doing the whole stuff is important. And this is what he's finishing already with now Rafael Escribano, who was advising me in my postdoc in Barcelona, and now is doing this also with Alex. And this will appear soon, covering all other modes, but PyEta. PyEta and PyEta Pram not. If you want, you can ask me why. In case you don't know, maybe you know why. Okay, so I don't need to say anything about this after Carlos' talk. So he explained everything about this. You know the interest, you know everything. So I skip this. Also, he emphasized very much this. So we are only seeing the top of the iceberg. No, the much will come and it will be very interesting. All right. So, and about this also, he emphasized, I mean, the standard model error is saturated by this uncertainty. So here we have to invest to improve it if we want to keep the pace with the experiment, right? Also, he was saying very nicely what we need. Yeah, we need this. We access it through measurements of E plus E minus through hadrons. And he was extremely clear on all this. And also, I was very glad that he covered, okay, and we can do it in a different way. We can just go from S channel to T channel if you wish, and then use lepton universality and replace one mu on lambda by an electron line. And then mu on electron scattering is basically proving the same. Okay, so this is explained very nice. But now it is the new point. So it is known for long that you can do another thing, okay? It is not only lattice, not only plus E minus two hadrons, not only mu on electron scattering. You can use tau data, yeah? And this is something that, of course, in Mexico is known, right? This was started more than 20 years ago by the Orsay group, but it is one of the places where Mexico has done a contribution of big impact, right? This was done by Gabriel with Genaro, who is here, with Paco and Alain, and then later on, the Gabriel and Genaro collaborated with Orsay, the Orsay group and Chinese people to do this very important work. The idea is very simple, and you can see it at a glance from here. So this is what you need, one way of writing it, and then important things are two pions if you want. But what if we turn from neutral current to charge current? Okay, instead of E plus E minus, we have here tau neutrino, yeah, and here instead of two charge pions, we have one neutral and one charge. So by an isospin rotation, you can relate the two things. This was historically important because for some years, tau data was the cleanest, the most precise way of extracting the dispersive integral. Then bifactories came, and one of their many successes was the very accurate evaluation of this type of things, okay? And for a while, people think, okay, let's forget about taus, okay? But there was some trend always showing when using tau data. So I mean, in the first paper, in these papers here, in our paper now, of course, in every paper using tau data, you see this. If you do the isospin rotation, you can, if you want, compare E plus E minus two hadrons from E plus E minus data to the same with tau data, or tau branching ratios with tau data, or with rotated E plus E minus data. Here, everything is converted to tau branching ratio. Okay? When you do this, you see that systematically E plus E minus sits on the left of taus. And to improve agreement with the standard model, you would need to move to the right. You would need to move this, that is the standard evaluation, the standard model evaluation, data-driven, to the right. So you see, okay, yeah, let's forget about taus, but let's not forget this has always been and will be closer to the standard model. Okay, so that was our motivation for Alex doing the update of this study. Particularly, he updated a paper by Chirigliano and collaborators. And here, this is the result that he got at this order. And then at this order, he got this other one. But this other one has an unreliably large error. I mean, we wanted to be sure that we were conservative, but you have so many contributions that in the end, the error is too large. But this is reliable. And you see, it is in extreme agreement with Lattice. When he did this, BMW was about to come. So he did this paper. Then it was BMW. And now there are two other lattice evaluations with competitive precision with BMW in a given window. And not everywhere, only BMW has the required precision. But in a given window that is very good for the lattice, three collaborations are agreeing together. I mean, BMW and two others. Yeah? So now people start saying, okay, perhaps there is some issue with the plus and minus data. And maybe we shouldn't throw away tau data. Okay. Right. So yeah, I'm just finishing. So this is what Alex already did, and what is about to appear is the radiative corrections for the remaining modes, and something we didn't evaluate for the two pions. Now he has evaluated. So what's the motivation? Here, Mario, Vincenzo, Alberto, and Emily had the very nice idea of using again crossing symmetry. You see, it's always the same. So this is kaon to pion lepton neutrino, KL3, and this is tau to kaon pion neutrino. Okay, so you do crossing symmetry and relate both. And they said, okay, since kaons are so well measured, let's take for a moment hadron input from kaons and use it in taus and see what happens. Obviously, they knew what was going to happen. If you remember my numbers from the first part of my talk, this brings you closer to CKM unitarity, and this reduces your error. Okay, but they didn't do one thing. They computed the model-independent corrections for these two meson case. For the one kaon case, they use the old corrections that I showed you how to improve in the first part, so you can just use ours and it's improved. But for two mesons, they didn't compute the model-dependent correction. They just estimated this. They, of course, estimated this well because they are very smart people, and they were very conservative. So 100% error over the typical alpha over pi size of these corrections. So this resulted in these numbers. So these are for the first line. I mean, what was important for them are the k pi corrections. So they got minus 0.2 with 0.2 error, so 100% error, and minus 0.15 with 0.20% error, more than 100% error, because they didn't compute this. Now Alex has computed this. And as a result, he has obtained numbers that are in agreement within the errors. I have lost the pointer. They are in agreement within the errors with these results. But the uncertainty is the interval. The uncertainty is prime. It's basically 4, and here it is 0.12, basically. Same here. So the result that is soon to be published will enable most precise tests in these two meson cases, particularly, of course, again, CKM unitarity in tau to kaon pi. Okay, so this is the main outcome of this analysis. Okay, so with this, I think I'm done. I hope I said everything. Thank you very much.
Okay, thank you, Pablo. So questions?
You have to ask one malo.
You know I have to ask. No, for the first part, when you introduce the new physics contribution, in principle, it should be similar to B2 tau nu, right? Of course, you are in another energy region. So in principle, you have a charged Higgs contribution, and you have bounds in that region. Have you compared your contributions to your restrictions here with the other ones? Could you mention a little bit on that?
You are absolutely right, Genaro. So in fact, the motivation for our first study with Stella, Gabriel, and Michelle was precisely this one that you are mentioning. So in tau to pi eta, you remember I said something about tau to pi eta? That's special, okay? So in tau to pi eta, there was a study by the Orsay group pointing out that Bell would be able to improve the limits from B to tau nu on charged Higgs. All right, so this was the motivation for our analysis. Then this is really neatly shown in this particular mode because this mode has enhanced sensitivity to the scalar contributions. So in general, it doesn't happen, but in this case, it happened. So yeah, we did this and we have the most precise restriction on this type of new physics, but from this other paper. Here, in fact, for the decay mode that is involved, you are sensitive to pseudoscalar, to pseudoscalar from the second doublet or whatever, you are sensitive. And yes, we have compared bounds, but in general, you are not as brilliant on this tau to pi eta. It is around 5 TeV for a weekly couple thing. But yeah, that is really, really very interesting. Thank you.
And the other question is in the picture that you have for the BMW contributions and your result. I didn't get it. You were saying that the OP6 is less reliable than the OP4. I would say, I understand the error bars, but I would say that the central value is pointed out to something interesting.
Yeah, thank you again. Let me explain me better. So at some points you have to do things that you know that are over conservative if you want, but you need to do these things because it's like the recipe. So if you do this, you get this error. But what's the source of this error? The source of this error is the lack of phenomenological analysis that are including these constraints, because there are many things that have not been computed yet. When this is done, this error will be reduced to a half or something like that. That is what you expect. But the problem is not with the theory, is not with the convergent, is with the things that we have analyzed within this theory at this order. And this is something that could be seen in the early KPT papers at next to leading order. At some point it was happening this thing, but of course there was a lot of work done, a lot of measurements, and now the errors are the size they should be because this is a well-converging theory. Here, it doesn't converge so well, of course, but the error will be reduced to basically a half or between 2/3 and a half, but this will happen. This is not happening yet.
Very nice talk. I wanted to know your opinion about the lattice results that are coming on this new. What's your take on? I mean, you think that what do you think is the source of the tension between the standard model and the lattice?
Yeah, thank you for the question. In fact, I was to ask you something about this in your talk, but then with the sound problem, we discussed other things. So this is my view. Okay, there are 3 evaluations on the lattice, and they can only be compared in a window that basically covers 1/3 of the whole HBP leading order contribution. So in 1/3 of the thing, you can compare it. Inside this region, the agreement is very good. And if you can also translate the dispersive evaluation to the lattice language for this given window. If you do this, you explain half of the difference. So half of this difference is explained from this window that is 1/3 of everything. But you don't know the rest. So everything you can do are guesses because there is only one lattice evaluation. And then, I mean, the mu(G)-2 collaboration is very strict, as you perfectly know. So the theory initiative has a rule for that. And the rule is, unless you have 2 evaluations that are doing the same with comparative errors, systematics, everything that you can really compare them, then is as if you didn't have any evaluation. So BMW for the moment still is alone because only in this limited window you can compare. So then everything are guesses. On the contrary, on the dispersive, you have two complete evaluations that agree very well. And for regions, you have more. In some regions, you have 6 or 7 of them that are in pretty nice agreement. So for the moment, even if we think maybe Lattice is right, we cannot say it. We shouldn't say it. So this is what I would say.
Yeah, thank you very much. Yeah, thank you.
Okay, more questions?
First, thank you very much for the talk. I was wondering on the very first part of your talk, you are comparing tau decay versus Pioncer and Kayon. So experimentally, you expect to see some hadronization effects on the measurement, and what will be the modifications on that?
If I expect to see what kind of effects on the measurement, sorry?
Yeah, hadronization effects.
Hadronization effects. Yes, and they are very different, but this to some extent is controlled. I mean, in these measurements, the sources of systematics here and here are completely different, but they are independently accounted for. So, but yes, you are right. I mean, it's not the same. What is the same is the hadronization. The hadronization, yes, it cancels, but this type of experimental effects are not the same, but they are taken into account. You are right.
Okay. And the other question I have is regarding the recent LACB results on the BDK. So in some way you can relate this result because they are measuring ratios between muon and electrons, and you here have a tau to muon. So it will be good to do some analysis on this way, or?
Yes, I mean, Mick will tell us about this Thursday. So what I would say is just the fact that there is always a window. So it may be that we don't have any new physics in everything I'm discussing here. I mean, it seems to be the case, but for some cases it's more clear than in others, but it seems to be the case. And it is perfectly possible that there still is an anomaly in B physics. Because if you look, for instance, in SMEF, there are independent operators for general flavor symmetry doing these kind of things. So it is possible. You don't in fact need fine tuning. You can have it. So that is why it is so important, if this clears up, to see what is the thing in Beson, as he will explain.
Okay.
Yeah.
Thank you.
I was wondering, do people understand what could be the source of the discrepancy between E plus, E minus and tau data?
Okay, yeah, people don't understand this. That is the key question. And you see, the problem here, Genaro can also tell you, this is a long story. They were always telling, okay, you need to rotate this data so that it can be used in this way. And then for this, there are hadronic effects. You control them to some extent, but there is model dependence. So then it is better not to use this data. But this is not the absolute truth. So how do you measure this? You measure this mostly in B factories. B factories are tuned to the upsilon-4s, right? So how do you measure these low mass states? Because initial state radiation. You are measuring a photon, then you know the energy of the photon, and this allows you to get to lower energies for this. And when you hear photon, you hear initial state radiation. I mean, that's Monte Carlos, okay? And the Monte Carlos have a part that is structure independent, that I have been discussing, and they have a part that is structure dependent. Okay, so there can be that these errors are affecting our business. And in fact, now people are starting to revise things here. And for instance, in the charge asymmetry or forward backward asymmetry in E plus E minus to plus minus, they have already discovered that what was done analytically or in the Monte Carlos was not complete. This is a simple case, but this has already been discovered very recently this year. So things like that may be happening in more difficult contexts. So, I mean, it is not understood. I mean, we need to work on that. Lattice is also working in both sides, here, and even doing radiative corrections here. This will come at some point, but it's not completely understood.
Thank you.
Okay, thank you, Pablo. Thank you.
Okay.
Hello, everyone. Okay. I am Hector Novales, and I'm going to talk to you about this work, which deals with Lorentz violation effects on electromagnetic moments of fermions. This work was carried out together with these people. In fact, Javier and Monica are right there. So, yeah. Let's start. Okay, let me talk to you first about field theories. The two main ingredients defined in field theories are the dynamic variables and the symmetries. If you try to think of an analogy with respect, just imagine a big house that you want to build, and you could say that the dynamic variables are like the bricks and all the materials that you are going to use to build this theory. And in the case of the dynamic variables, in the case of field theories, are the fields that you use to build them. For instance, in the standard model, we have the voltage bosons, the Q-stage bosons, the Dirac-Steiner, and scalar. So, so on the other hand, we have the symmetries. The symmetries play the role of some planes to construct this building, and because they are the criterion to define the Lagrangian terms in a given theory. So, for instance, in the standard model, we have the gauge symmetry of the standard model gauge group. We have also Lorentz symmetry, which implies the CPT symmetry, which is a discrete symmetry, and we have other global symmetries. So most extensions of the standard model are defined by changing these two elements. Some adds some new fields to the theory, other adds some new symmetries, and so we have the extensions. Okay. Electrodynamics quantum electrodynamics describes the interaction between the Dirac field and the electromagnetic field. We all know the corresponding Lagrangian. And if we inject more energy if we can see smaller distances in space, we are able to see not only electrodynamics, but the whole standard model. This is our current-based theory, and yet it has some problems, as you can see. For instance, we know that neutrinos are massive, and there is dark energy, dark matter. So we expect that at very high energies, some fundamental description to emerge, which could be perhaps defined at the Planck scale. This is a possibility. And of course, this fundamental description will have its own dynamic variables and symmetries. Perhaps, and this is a possibility explored or more extensively by the group of Indiana University, in particular by Alan Kosteletsky, this Lorentz violation could be defined in this new formulation. So when we, through some spontaneous symmetry breaking, fall into the standard model, and then through the electroweak symmetry breaking, get to the electrodynamics, perhaps we could observe some effects of the Lorentz violating theory at the level of low energies. Okay. So let me talk to you about observer and particle transformations. Okay. To understand the concept, let's imagine this situation. Imagine that we are here on the Earth. So we consider the gravitational field, and we define this frame, and we put a box within which we put some particle which is subjected to the interaction of gravitation. So the corresponding Lagrangian is this, as we all know, and we are going to find two kinds of Lorentz transformation. One of them is called the observer Lorentz transformation. So this transformation is just a change of reference frame. In this case, I'm trying to illustrate this by showing you this new frame, which is rotated with respect to the original one. And as you know, any change of reference should not change physics. This is only a change of description, so physics is not changed. And while the coordinates used to describe the system are different, the particle within the box shouldn't feel any difference. For the particle, the gravitational interaction points towards some directions, so towards the same directions as before, and with the same intensity. So, of course, if you apply this observer Lorentz transformation, both the gravitational field and the rest of the elements here are transformed, and the Lagrangian remains invariant. So the other kind of transformation is very similar to what we call what's the name? Active transformation, active Lorentz transformation. We call it particle transformation, and it is different. In this case, you modify the physical system, you move it, you apply a boost or perhaps make some rotation. And in this case, I'm illustrating this by rotating the box and not the gravitational field of the frame of reference, just the box with the particle in it. And as you can see, the particle should feel a difference respecting the direction of the gravitational field if you rotate it. So evidently, the physics is not invariant. There is some preferred direction in space. And if you apply this transformation, since the gravitational field does not change, this yields an non-invariant Lagrangian. So this is the concept behind the particle Lorentz transformation. In this case, this is not a strictly correct example, since this complete system should also consider the Earth. So this is not indeed true. But the idea of Lorentz violation is that the properties of the space-time generate some preferred direction in space-time, and when you perform some particle Lorentz transformation, there are some Lagrangian fields which remain unchanged, and this yields a Lorentz violation. So the description, or not the only one, but the most general description of this kind of effects is the so-called standard model extension. Not a very fortunate name. In fact, standard model extension is so generic, but okay, that's the name. And this is an effective Lagrangian. That's the way in which we describe this. These effective Lagrangians have standard model symmetries, not Lorentz symmetry, obviously, but gauge symmetry group. It has the same global symmetries, and the dynamic variables are the same as those of the standard model. There are no new variables. The Lagrangian terms comprising this effective Lagrangian shall carry effects from some sort of formulation of very high energies that should be observed as small effects and can generate deviation from the standard model observables. So in general, you can write the standard model Lagrangian as a sum of two terms. The first of these is the so-called minimal SME, minimal standard model Lagrangian, standard model extension. So this term comprehends all the terms which are renormalizable in Dyson sense. That is using as a criterion the mass units in each Lagrangian term. So this is the most studied part. This other term is the non-renormalizable SME. This comprises a set of terms which are not renormalizable in this sense, and in fact, it contains formally an infinite number of Lagrangian terms. Okay, in this work, we consider the minimal SME, and this Lagrangian can be written as the sum of these two terms. The first one is the standard model, as we know it, and the other one is a Lorentz violating term. So this Lorentz violating Lagrangian comprises terms which have this structure. These factors which have some number of Lorentz indices are background fields, are like the gravitational field that I showed you before. And these, I insist, are generated by the properties of space-time, are inherited by the properties from the properties of space-time. On the other hand, we have this O with some Lorentz indices, which are contracted with this, and these are products of derivatives and fields. So these are these guys bear all the field content. So if we apply an observer Lorentz transformation on a term of this form, note that both the tensors, the background fields, and the product of dynamic variables transform as tensors because we are only changing the frames of reference, and under this change of reference frames, both transform covariantly. So in the end of the day, the terms are invariant. So as I told you before, there is invariance on the observer Lorentz transformation. If we, on the other hand, apply some particle Lorentz transformations, the history is different since these tensors remain unchanged, as I tried to illustrate before, and while the dynamic variables do change. So this produces some difference, and this factor remains. So these terms are not invariant under these Lorentz transformations. Okay, well, the standard model extension with Lorentz violations involves sectors corresponding to all the sectors of the standard model. There are some Yukawa sector, for instance, some gauge sector, and so on. We, in this work, consider the Yukawa sector of the theory of the renormalizable part of the Lorentz violating SME. And this sector includes couplings of lepton and quarks. These are shown here. This part corresponds to the leptons. This is a right singlet. This is an SU doublet. And we have also the same for quarks type U and D, and the hermetic conjugate. So we also have these coefficients, which are like some Yukawa-like couplings, but they are somewhat more difficult because they bear also some Lorentz indices, which are summed with these with the couplings. Okay, let me tell you that from the form of the Lagrangian, these couplings are antisymmetric with respect to space-time indices. So after spontaneous symmetry breaking and using the unitary gauge, we have that this Lagrangian is written in this way. Here you can see the Higgs field, and after some biunitary transformation, which replaces the H's by these Y's, we define these coefficients which appear here, and we define the mass eigenspinors. And so notice that the antisymmetry property of these coefficients is inherited by these coefficients. So these are also antisymmetric. Okay, this is the same Lagrangian. I just wrote it here again. And it has these parameters which we use to define some other parameters. So notice that these are two tensors with respect to space-time indices, just like the electromagnetic tensor. And using just that property, we define these E's and B's. which may remind you of the definitions of the electric and magnetic fields in terms of the electromagnetic tensor, in terms of the Maxwell tensor, and these can be arranged as vectors this way. And we define this because these are the parameters we are down. Later. So, can abstract and one are these two current vertex, these vertices, and these 3-point vertices. Regarding this Riemann rule, one could as well, we could also try to define some modified propagator. This has been done in some works. However, we decided to use insertions instead, since this is a way, more practical way to work, and it yields to nice results. And well, using these elements and of course the Feynman rules of the standard model, we defined some contributing Feynman diagrams. So we calculated the electromagnetic vertex at one loop using this formulation of new physics. And there are some things to say. On first place, we consider the external photon of the mass shell. So the expression of this element, this object, shall be a function of this quadrimomentum, this four momentum. And we also consider assume that the external fermions are the same. I tell you this because I emphasize this because, as you can see, both of these Feynman rules have flavor change. So flavor change is rather natural here. But instead, we just limited ourselves to this case, in which we are going to calculate then diagonal electromagnetic moments. So we calculated this, all the contributing diagrams, and found this general expression, in which I am showing you only a part. Let me explain. In the first place, we identified utilizing standard definitions, these factors, which are the magnetic form factor and the electric form factor. These numbers are Lorentz invariant. Okay, these quantities are Lorentz invariant. So on the other hand, we have these ellipses, which indicate the presence of a lot of more terms. Yes, so the parameterization used to characterize this object in the presence of Lorentz violation is extensive. It's very large. There are some, there are lots of brand new Lorentz structures allowed by this flexibilization, and but we don't write it here, but we concentrated on these guys instead. So from these guys, we define the anomalous magnetic moment contribution and the electric dipole moment contribution just by taking this on-shell condition. Regarding the contributing diagrams, we have several. We split them into two kinds. The first one of them are diagrams in which we use one insertion, at least one insertion of a 3-point vertex. Let me explain a little more. If you calculate this electromagnetic vertex using just one insertion, the contribution vanishes. There is no contribution to electromagnetic moments with just one of these insertions, okay? In any case. However, if you consider this at the second order, these contributions are generated. So we have these diagrams in which at least one of the vertices are Lorentz violating a 3-point vertex function. All of these diagrams involve some virtual Higgs boson. And we also have this. Okay. In these diagrams, the insertions, the only insertions used are 2-point insertion, 2-point in vertices. And this is some synthesized list of diagrams. Indeed, If you look at these diagrams, you can see that in these lines, these virtual lines, we have a double line, which indicates that this virtual line can be any of these fields. So you have to multiply this by 4. And we also have these diagrams. I framed here these 3 diagrams in blue because these are the most important, these produce the most important contributions when you consider the virtual line here to be a photon, right? So these are Springer type diagrams. Okay, regarding the calculation, the exact calculation, we found that we did the following. So we have the electromagnetic vertex, and this electromagnetic vertex is the sum of all the diagrams. Here we have a sum over fermion flavors, which appear here, here, and here, for instance. And these four contributions yielded diagonal electromagnetic factors. Remember that I told you that we are assuming that these external fermions coincide, are the same. On the other hand, we use the unitary gauge. So the unitary gauge has the advantage of reducing the number of diagrams significantly because there are no Wilson-Boston diagrams. And this makes it easier. However, the problem could be could arise in the cancellation of divergences, of ultraviolet divergences. The unitary gauge is somewhat problematic in this sense. However, we verified that the results are free of ultraviolet divergences, so there is no problem. Okay, we use the Passarino-Bellman reduction tensor reduction method to solve this, and we use these packages, Penn-Calgan package X, and we were able to prove that one of the identities fulfilled by the full contribution, and we extracted the electromagnetic moments, the anomalous magnetic moment and the electric magnetic moment as well. Okay. These 3 diagrams that I am showing you explicitly are the ones which, as I told you before, generate the most important contributions. Yes, this virtual particle is a photon, and the difference between the contributions, the contributions of these 3 diagrams with respect to the rest of the contributions is about 10 orders of magnitude or so. So there's a big difference, and we consider just this. We disregarded the others. So while ultraviolet divergences cancel out from this contribution, we noticed that infrared divergences remained, right? These divergences should be canceled from the cross-section, but there is some point of importance, and it is that the infrared divergences do not appear in the vector current, but they appear in the electromagnetic moments themselves. So this is contrasting with what occurs in the case of the quantum electrodynamics. This means, since the final contributions to the electromagnetic factors bear some divergences, this means that these quantities are not to consider as observables, right? They are not properties, electromagnetic properties of the fermions, but they are important because these quantities play a role when you consider some processes, some free processes, right? So this is the importance of them. We expect these divergences to cancel out from the cross-section, from some cross-section. But let me tell you, we haven't done this. This is an ongoing work, so we expect to solve it later. And well, the structure of the contributions is this, right? This is the anomalous magnetic moment contributions from Lorentz violation. We have these coefficients A tilde and A hat. These are functions on masses, and this dependence on masses appears in terms of Passarino-Bellman scalar functions. While notice that these parameters that appear here are the sort of electric and magnetic fields that we defined before, just using the antisymmetry properties of the Lorentz violating coefficients. Regarding the electric dipole moment, we have some similar history, similar story. So this is this coefficient, the tilde, is a function on masses and on Pasolini-Bellman scalar functions. And we have this, the dependence on the sort of electric and magnetic field, right? And just notice these are not literally electric and magnetic fields, just the definition is analogous. Analog. Okay. Regarding the IR divergences, the infrared divergences, these coefficients, these contributions are written in this way. So here we have the infrared divergences and the terms that are infrared finite. So we haven't done this explicitly. This is, as I told you before, a work in progress. But the idea is the same as in the standard and in the quantum electrodynamics. You consider some process like this. For instance, this could be some E plus E minus process to E plus E minus. And among all the contributing diagrams, you should consider these two. So I am assuming that this line is a photon line, and we have two insertions here and here. I didn't tell you this, but the diagrams which generate these infrared divergences are those in which the Lorentz-Violating insertions appear, in which both Lorentz-Violating insertions appear in just one propagator line. This doesn't generate such divergences. So we have here this diagram in which there are two propagator insertions and another diagram in which they appear here. So this contribution involves infrared divergences, and we should sum this at the level of cross section with these diagrams in which these final state photons are soft. So the idea is that the contribution from these diagrams should cancel the infrared divergences from these diagrams, and so yield a finite contribution, right? Okay, let me tell you about numbers. On the first place, we have the quarks. So we calculated electromagnetic moments for individual elementary particles, for elementary fermions, and there are different prescriptions to connect these contributions with the electromagnetic moments of the proton and the neutron, which are composite particles. So we use this prescription where we have the anomalous magnetic moment of the U quark and the anomalous magnetic moment of the D quark to define some contribution to the magnetic moment of the proton. So we use this measurement, which I think is the best right now, the most sensible right now. And using the error, we found some bounds on the SME. These bounds are shown in this column. As you can see, the first column of this table, the first column shows what parameters are we bound. In this case, we have, for instance, a real part of either the sort of electric field or the real part of the sort of field. The bound goes in these quantities. And for instance, the bound of the 10 is on the order 10 to the minus 10. Notice that the most restrictive bound of the 10 is of order 10 to the minus 11, right? There is an interesting point in this in this analysis, and is that if you think of a proton, of a neutron, these are composite particles which are composed exclusively of U and D quarks. That is only involve the first quark family. And you should expect that when using this quantity to get some bounds, we could get just information from this, the first family of quarks. However, since the Lorentz-Violating Lagrangian involves flavor change, we are able to get information from the second and third families as well, right? So we have here, for instance, something related to the top quark or to the C quark, right? And here is the same. Regarding the neutron, the electric dipole moments, we use the neutron dipole moment. This is a very nice bound, experimental bound, and we use this prescription. So the current constraint is of order 10 to the minus 26. So we got these bounds. In this case, we're bounding moduli of electric and magnetic sort of fields. And the most restricted bounds in this case amounts to 10 to the minus 12. And again, we got some info regarding the second and third families. Okay, let's pass to the standard model charge leptons. And we can start with the electron, with the bounds on the electron anomalous magnetic moment and mu anomalous magnetic moment. Note that these deltas are different between theory and experiment and are very nice, bounded. There are also some bounds on the anomalous magnetic moment of the tau, but they are not too restricted, so we disregarded them for this presentation. While in the paper, you can see them as well. So using these bounds, we found these numbers. Again, in this table, the first column corresponds to the quantities that we are bounding. For instance, here we have the imaginary part, the modulus of the imaginary part, either some electric or type of magnetic type field. In this case, the bound is of order 10 to the minus 10, but the best bounds were of order 10 to the minus 11, which are shown here, correspond to the case of the electron. Regarding the electric dipole moment, we have these bounds for the electron and the muon. Again, the bounds on the tau electric dipole moment are not too good, but notice that this bound is extremely convenient. And in fact, this number led us to the best of the bounds that we found in this work, which is of order 10 to the minus 14, right? So I think this is it. Yes, hi, this is it. Thank you.
Okay, thank you, Hector. Questions?
Thank you for the very interesting talk. So the Kinoshita-Lee-Noenberg theorem, the KLN theorem is very well established in a theory that doesn't violate Lorentz and all that. So you know how infrared safety is achieved. But this result doesn't exist for your theory. So what you are investigating now will be fundamental. If you get such kind of result, then everything makes sense. If you don't get it, then the theory is not well constructed. So it is, I mean, to me, it's much more interesting than any application of the theory. You are really testing the theory. So, and in this sense, I would look at the KLN work, because you want to do exactly the same thing. I mean, it's you are interested by a particular thing, but it's general. So I don't remember the details, but I will go to the KLN. You are doing exactly as you said with this radiation and all that, with the double Lorentz violating insertion, right? Yeah, you show the diagrams where the two with the real radiation and virtual radiation. Can you show them again? I don't remember the slide, but you have the diagrams showing diagrammatically the cancellation of higher divergence that you would likely have. Can you show the diagrams?
Yeah, right.
So, yeah, this one. So yeah, this is exactly, this is like KLN in QED, right?
Right,
So
right.
yeah, this is the thing, and it will be of general interest. Okay.
More questions?
Thank you.
Probably in the same direction that Pablo was mentioning. since you are free of these restrictions that we know from QED to Lorentz violation, I even could dare to say that if you see some variations, not only in the electric and dipole moment, but right to the charge, which is the implication in this one. If you see the running of the coupling, you can put some bounds in the deviation of that, which is coming from this contribution, right to the electric charge, not to the dipole moments, higher the dipole moments, because you don't have some protection. You don't have to respect gauge invariance with Lorentz violating terms. So you are free to go and check.
Yeah, right. Thank you.
Okay.
Hello. A few approaches to quantum gravity also predict like Lorentz violation. Have you thought of trying to make some connection or try to associate to those works, because maybe there's something in there?
Right, this is an effective field theory, so there must be a connection. The difference is that an effective field theory doesn't regard any particular formulation. In fact, the main motivation behind this type of models in its origin was that in some formulation of string theory or quantum gravity or non-computative theories yield some effects of Lorentz violation, and one can integrate out some heavy modes and find these kind of terms. But yes, there must be a connection. The difference that this says nothing about which is the formulation, because it's completely general, model independent. Thank you.
More question?
Hi, thank you. I wanted to ask two questions actually. The first one is regarding these divergences terms, the infrared. The reason you said that you are just ignoring those terms is because they are not observable quantities. And I wanted to ask if this is the main reason that we are hitting those variables, because to me it seems like we are just hitting those under the carpet when the limit as epsilon tends to 0. Well, your entire interval goes to infinity. And the second part of the question is actually more technical. I also use package X, and when you have those divergence terms, in the manual of package X, you need to make sure that you add the gamma Euler constant and the logarithm of 4 pi. I wanted to ask if you are doing that.
Okay, right. Regarding the first question, the divergences should cancel. Since this is an ongoing work, we are going to do it or try to prove it. On the other hand, notice that this is just an estimation. So we disregarded these terms just as some to get an estimation of the effects. However, a complete calculation, of course, requires this cancellation to be proved to see exactly what happens, right? Regarding the second one, yes, we consider these terms, the Euler-Mascheroni constant, and yes, we did it.
Okay, more questions?
Hi, I want to know about I wonder if you have studied if the terms you discard are important or they are not really relevant. For example, for the cross section or some pneumatic variable.
I'm having some troubles to hear you because of the
Sorry.
Thank you.
I want to know about the terms you discard when you talk about the electromagnetic form factors.
Right.
You say you discard a lot of terms. So I wonder if you have studied if they are really relevant for the cross section or I don't know, maybe they are important, but I wonder if you have studied if they are really relevant, or we can only discard.
Well, we haven't worked at the cross-level section to do it, but the difference is huge, about 10 order of magnitude. And the reason behind that is that there is an electron inside the loop. If you put some Higgs or some W boson or Z boson, it should be suppressed by some mass of these particles. So this creates some suppression with respect to these diagrams. So I would not expect them to be so important.
Okay, thank you.
More questions?
Just to clarify one question back there. Yes, working with package X, we have the infrared pole and the Mascheroni constant and the 4-pi logarithm. They are enclosed in that definition of delta infrared. So yes, in this work, it is considered such issue that package X does not use. But in the manual, it explains that at the end, we must consider it. Okay, yes, we consider it.
Thank you, thank you.
On the expression, moment, and that is
Yeah, right. Yeah.
Okay, more questions? Okay, thank you, Lector. Now it's time to coffee break, and we'll be back at 4 p.m. Thank you.
Ah, pero no tengo el programa. Bueno, ¿sí tienes el programa a mano? Me te va a faltar a ti para disculpa. Ah, Ángel, ok, vale, gracias. Ok. Ángel,
Hola.
Ángel,
Yeah, yeah,
you can hear me, right?
yeah, I can.
Okay, I'm very glad to greet you. I'm eager to listen to your talk. As everyone, please share your screen and start whenever you wish.
Okay, let me know if you can see my slides now.
You can.
Yeah, you can.
Yes, go ahead, please.
Okay, yeah. First of all, I want to thank to the organizers to give me the opportunity to share a little bit of my research. And yeah, today I'm gonna talk about this pion and kaon time-like electromagnetic form factors. And yeah, this work has been done in collaboration with Professor Adnan Bashir. And also this talk is gonna be partially based on the on this paper that we published last year together with Elio Sanchez Alepuz and Professor Reinhard Koffer. Let me put the full screen. Okay. Okay, so yeah, so the main motivation of why do we want to investigate hadronic form factors is because, well, since the 60s, they were already, yeah, when in the 60s, when the proton form factor was first described, they were recognized as fundamental tools to explore the internal structure of hadrons. And in addition, they encode fundamental information about charge, magnetic moment, and charge radius, for example. And yeah, they are also close to interrelated with hadron spectroscopy, as we will see in the following slides. So they are that important that nowadays most of research facilities have programs in order to investigate them, such as the JLab in the US, also MAMI, ELSA and FAIR in Germany, and BEST3 in China. And yeah, in addition, in the near future, the experiment PANDA will measure, in particular, this proton time-like form factors to an unprecedented precision. So yeah, also the hadronic form factors, they represent a benchmark for theoretical and phenomenological predictions. They have an interpretation also as Melin moments of generalized parton distribution functions. So probably Melanie is gonna talk also a little bit in this direction in his talk. And yeah, also the form factors, they are very important because they appear as input for very important calculation, just as the anomalous moment of the muon, which well, is also currently a very hot topic. And we have also a contribution in that direction together with Kefani Raya, Professor Adnan, and also with Pablo. And yeah, well, the truth is that there are just very few calculations of hadronic form factors on the time-like regime, and most of the results that we can find in literature are using vector meson dominance models. So deep understanding of time-like form factors, it's a very timely subject to investigate. So the formalism that we employ here to investigate the hadronic form factors, or in particular the meson form factors, the Dyson-Schwinger equations together with the Reda-Salpeter equations. And yeah, of course, I'm not going to enter into too many details on the formalism, but if you have any question, we can discuss it. So yeah, first of all, the Dyson-Schwinger equations, they are equations of motion for quantum field theory. They describe the fundamental elements of the theory, such as propagators and vertices. They also are the exact equations which can be derived from the path integral formalism. And yeah, they composed an infinite set of integral equations. So on the left bottom figure of the slide, you can see the diagrammatical representation of the quark propagator, well, the Dyson-Schwinger equation for the quark propagator, which probably you already saw it on the Alfonso's talk. He already talked a little bit of these kind of equations. So yeah, the quark propagator, the Dyson-Schwinger equation for the quark propagator includes a gluon, which is fully dressed, and also a quark gluon vertex, which is also fully dressed, and the quark propagator appears again inside of the same equation. Okay, so on the here at this point is worth to mention that also the gluon propagator and the quark gluon vertex, they follow their own Dyson-Schwinger equations, and which elements of these equations follow further Dyson-Schwinger equations. So when if we want to substitute all the ingredients into this equation, here is where we end up with an infinite set of integral equations. Okay, so on the other hand, the solutions of the Bethe-Salpeter equations, they encode information about the meson that we are investigating, such as the mass, the decay constant, and the decay width, for example. And also, if we couple this kind of equations to an external field, we can have access to form factors. For instance, if we couple the system to a photon, then we can extract electromagnetic form factors. So the situation with this equation also, it's that also includes an infinite set of diagrams. So on the right side of the slide, you can see also the diagrammatical representation of the homogeneous Bethe-Salpeter equations, which will include the amplitude of the meson that we are investigating. Also depends on the product of two quark propagators, which can be obtained by solving the Dyson-Schwinger equation. And this block K, which is the interaction kernel, which includes all possible ways that the quark and the anti-quark can interact, and also the gluons. Okay, so yeah, here is where we have an infinite set of diagrams in this interaction kernel. Okay, so well, see, this is a picture only the thing that I was saying before about the gluon propagator and also quark gluon vertex, they follow their own Dyson-Schwinger equations. So yeah, since we have an infinite set of a set of infinite equations, we need to truncate the system at some point. So one of the simplest truncations that preserves chiral symmetry is the so-called rainbow ladder truncation. Basically, in this truncation, one collects all the corrections of the gluon propagator and also the quark gluon vertex into an effective coupling that here I called alpha. So basically, now the system of equation will look like the picture on the top. So basically now instead of having the full interaction kernel into the Bethe-Salpeter equation, now we have only a gluon exchange between the quark and the anti-quark. And in the quark Dyson-Schwinger equation, now instead of having the gluon and also the quark gluon fully dressed, we have collected all this information into this effective coupling alpha. But now we need a model to describe this coupling alpha. And for this case, we employed the model by Maris and Tandy, which includes a Gaussian that basically has enough strength to dynamical chiral symmetry to take place, and also an ultraviolet part, which basically reproduce the behavior of the quark propagator at large momenta. And in general, it has seen a lot of success on the description of hadron spectroscopy. Yeah, nevertheless, this truncation has quite important problems. One of the problems that I'm going to talk today is that the solutions of the Bethe-Salpeter equations employing this truncation are stable bond states, and they do not include a decay mechanism to allow hadrons to decay. And we know that most hadrons are resonances and they do decay. Okay, so here on the left, I'm showing a typical calculation of the electromagnetic pion form factor using this rainbow ladder truncation. for a space-like momentum and time-like momenta. For space-like momentum, I mean when photon momentum square is positive, and time-like momenta when the photon momentum square is negative, okay? So the green points represent the experimental data, and also the purple ones are experimental data, and the blue line is, it's our result using this rainbow ladder truncation, okay, together with the Maristandi model that I just mentioned before. So in one part we can see, well, for space-like momenta, we can see that our results, they describe very well the experimental data. So at this point, there's no problem. But if the problem is when we move to the time-like side, here we see that the main feature of the experimental data is that describes this bump behavior, which is close to the, well, which is located at the mass of the row. And yeah, this is it because the pion form factor includes all the resonance information about the row meson. Okay, so but yeah, our solution, instead of having this bump behavior at the position of the row mass, develops, or our solution develops this pole. Okay, so as long as our solution, sorry, as long as our truncation does not include the decay mechanism, so we are unable to describe the correct behavior of the form factor at the time-like regime. So this is the main objective that we want to explore, and by using a more sophisticated truncation into the system of equations. Okay, so in order to solve this problem, we employ a bejoined rainbow ladder truncation, which basically takes into account the mesonic cloud effect. And this by including explicit mesons as degrees of freedom.
4 minutes, questions included.
Okay. So in this truncation, besides in the interaction kernel, besides the rainbow ladder truncation, which is the gluon exchange, we have a mesonic exchange in different channels, and also in the quark DSC, besides the gluon loop, we have a meson loop contribution. Okay, so here I'm gonna move to some of the results. I'm gonna continue with the electromagnetic pion form factor. So here we know the pion is composed of up and down quark, and also we already saw that the pion form factor for space-like is already well reproduced in the rainbow ladder truncation. So employing this beyond rainbow ladder truncation still works very good. So here on the right, we can see a plot of experimental data compared with our results using this beyond rainbow ladder truncation, and it works really nice. So the interesting part is when we explore when we move to the time-like side. So we observe that when employing this beyond rainbow ladder truncation, we can describe very well at least at qualitative level the behavior of the form factor. So yeah, again, the green points are the experimental data, and the red curve and also the purple curve are our results using this beyond rainbow ladder truncation, and the calculations have been done in the isospin symmetric limit, and also the difference between the two, or between our two solutions, that we have used two different set of parameters in the Maristandi interaction. Okay, so but basically we can observe that indeed employing this beyond rainbow ladder truncation, we solve the problem that we had before, that instead of having the correct behavior, we had a pole on the real axis, but now we follow, at least at the qualitative level, the experimental results. And we can do the same to the kaon form factor. In this case, the kaon is a bound state of quarks up and strange. And in this case, the kaon form factor not only encodes the information about the raw resonance, but also includes the information about the phi meson resonance. And yeah, in this case, in order to describe correctly the time-like kaon form factor, one needs to include kaon cloud effects. Okay, so, and yeah, here I'm showing some of the results that we got for the kaon form factor for the time-like side. Again, the green points are experimental data from CMD3, and also the purple results are using this beyond rainbow ladder truncation. And this main bump that you can see in the picture will corresponds to the phi resonance, which is well more or less located at the position that it should be and has at least the correct qualitative behavior that we observe in the experimental data, and also as also includes well, it's not seen clearly here, but if we make a zoom in into this plot, we can observe that also the raw resonance it's included as it should be. Okay, well, this is basically the same plot, but with different Maristandi parameters, and yeah, from these results that we have gotten, basically one can extract the pole position. And yeah, the important thing that I want to emphasize is that using only rainbow light truncation, one cannot describe the decay width, but using this Bayesian rainbow light truncation, we can do it. Okay, so this is here basically I'm collecting the results, the pole positions that we have got. And yeah, this one main source of, well, one important source of error that we can potentially have in these results that we are using isospin symmetry limit. So, but at this point, we are exploring how to implement the isospin breaking effects into this formalism. Okay, so as conclusions, so these are some of the first calculations for a time lag form factor using the formalism of Bell-Salpeter and Dyson-Schwinger equations, including mesonic cloud effects. So then the time lag regime, we have a qualitative agreement, and yeah, well, this agreement with experimental data comes from the different approximations. And yeah, in the future, we want to include these isospin breaking effects to check if our results will improve. That most likely they will. So basically, this is what I wanted to share. If you have any questions, so please feel free, and thank you.
Thank you very much, Angel. You were over time.
Okay,
so
sorry.
For a quick question and answer, if any. Yes, please, quickly.
Hi, Angel. Thanks for the talk.
Yeah.
I want, if you use another effective model like Ching-Chan, will the results be different, or?
No. In this case, actually, yeah, if one employs a different model, like the Ching-Chan model, the results basically doesn't change at all. They work the same. So we checked before if there would be any potential difference between the two models, but we didn't observe any difference.
Thank you very much again, Angel. We move to the next talk by Melanie. I hope it is open here or no.
Well, good afternoon, everyone. First of all, I want to thank the organizers for giving me the opportunity to present my work here. The work I will present is in collaboration with Adnan Bashir, Roger Hernandez, and Kefani Raya. We are interested in studying the internal structure of hadrons Here in particular, pseudoscalar methods. These two an algebraic model that permits us to calculate some functions that help us with this arduous work. And some of the functions that are very important for this are the form factors. And well, to start, I will briefly mention the content. First, I will give a short introduction. After that, I will talk about the Schwinger-Dyson equations that are the equations that inspired the algebraic model. And then I will explain what the algebraic model consists of. After that, I will talk about the electromagnetic form factors through a method solved by us, like the triangle diagram, and finally the results and conclusions. And well, we already know that we can extract information about the internal structure of patterns from different pattern processes. But they are encoding the quarks and gluons. And also the hadrons that we can observe are in the non-perturbative region of QCD. So we can find two properties here, this confinement. That means that we cannot observe the quarks and gluons free in the nature, and the dynamical chiral symmetry breaking. That is the mechanism that tell us how the quarks and gluons acquire mass in a dynamical way to obtain the final mass that have the hadrons. So in this regime, we cannot use perturbative techniques since the coupling constant is bigger than 1. So we can use another techniques, and one of them that has been very successful until now are the Schwinger-Dyson equations. As Alfonso and already told you, well, the Schwinger-Dyson equations are an infinite tower of coupled integral equations that describe, that relate Green's functions of quantum field theory. Here we have the Schwinger-Dyson equation for a quark propagator, and it means that the dress quark propagator depends on itself, on a dress quark gluon vertex, and on a dress gluon propagator. Also, the most general form of the quark propagator is this one, where f is the renormalization function and m is the mass function that is here plotted. Here we can observe how the quarks acquire mass in a dynamical way, even in the chiral limit. And on the other hand, the equation that describes mesons is the Bethe-Salpeter equation, and it depends on the Bethe-Salpeter amplitude and on the quark and anti-quark dress propagators, and on a kernel of interactions between the quark and the anti-quark. This Bethe-Salpeter amplitude for a pseudoscalar meson is given by 4 structural functions. And well, as we said before, these Schwinger-Dyson equations are infinite, so in order to calculate them, we need to truncate them, or use some alternative, like is the algebraic model. This algebraic model is based on the Schwinger-Dyson equations because we take the most general form of the quark propagator and the leading amplitude of the Bethe-Salpeter amplitude. Also, we focus on the low regime of energy, so we take this mass as a constant. And the ansatz that we use for this quark propagator is this one, and for the Bethe-Salpeter amplitude is this one, where here we propose this lambda as a function of the variable of integration W, and also it depends on the masses of the quarks and mesons. And this rho is the spectral density of the Bethe-Salpeter amplitude, and whose shapes determine the specific behavior of the Bethe-Salpeter amplitude. And in an early work, we noticed that we can extract this spectral density from the Parton distribution amplitude. But due to the time, I won't be able to explain all this, but you can find the complete work from here. And well, here we also calculate a generalized Parton distribution and other functions in the line transformalism. But well, the Barton distribution amplitudes give us the probability of a quark anti-quark pair form a bound state. And as we can find several Barton distribution amplitudes in the literature, we can choose some of them in order to extract the spectral density of our pseudoscalar method and calculate the form factors. So we should in B and so distribution of the meson, and also making a Taylor expansion, we can have information about the charge radius. And for example, if we focus on a process where we can extract the form factor of a pion, for example, in electron proton scattering, and we make a zoom here, we could find this diagram where the photon emitted by the electron could be interacting with one of the quarks of the meson. Here is more explicit that we can find here a Bethe-Salpeter amplitude in the initial and the final states. And also we will have a quark photon vertex. And with this diagram and using the Feynman rules, we have that the form factors are given by this expression. So now, using our ansatz for the Bethe-Salpeter amplitude and for the quark and anti-quark propagator, we could rewrite these form factors is here, where M is have all the matricial structure of the function, and D has all the denominators. So introducing Feynman parameterization and using another techniques, we could rewrite the form factors here. And using the spectral density that we can extract from the PDAs and solving all these integrals, we could get our results. And well, first the results for pion are these. The blue line are our new results of the form factors using the algebraic model. And the light, well, the cyan band are our previous results using the overlap representation with the algebraic model. We compare these results with Schwinger-Dyson equation results, that is the dashed black line, and with some experimental data. The circles and squares are from JLab and the diamonds are from CERN. And we noticed that our results are in good agreement with all the experimental data, and also they match almost perfectly with the Schwinger-Dyson equation results. We did the same for Kayan, and we obtain again the blue line in this work. In the previous work, we have the light blue band, and we compare it again with Schwinger-Dyson equation results that are the gray band, and with some experimental data that we have available. And again, we observe that our results match almost perfectly with the Schwinger-Dyson equation results, and they are in a good agreement with the experimental data. Also, the charge radius that we obtain are very close to the PDG results. And we do the same for eta C and eta B. For eta C, we compare it with Lattice, that is the dashed black line. And the purple band are our previous results. And we can observe that our results are in good agreement with Lattice, at difference that the contact interactions that are the red line, that is the red line. And for eta B, we compare with contact interaction again, and with another previous and simpler algebraic model that we can find in the literature. And they are, the algebraic models are in good agreement. So, to conclude, the form factors are undoubtedly an excellent tool to observe the internal structure of an algorithm regarding the distribution and the data that the experiments provide us with four pions and kaons that help us greatly to verify that we are in the right path on the theory. And we have previously seen that the algebraic model has been good in describing the internal structure of pseudoscalar mesons by means of GPTs, like from wave functions, PDFs, form factors, and the like conformalism. We know that the electromagnetic form factors calculated using this triangle diagram agree with Schwinger-Dyson equations, lattice, and experimental results. And following this, we hope to proceed to the calculation of these functions for other types of mesons with the algebraic model and make new predictions with it. Thank you very much. That's all from me.
Thank you very much, Melanie. There's time for questions. Okay. Yeah, so concerning the particular values that you use for the bottom and charm quarks, how do you select these precise numbers? So this 1.65 and 1.67 and 5 something for.
For the eta C and D.
Yes, exactly these numbers that you have here. How do you pick them up?
The masses.
Yeah, the masses of the charm and bottom quark. Yes, sir.
Okay. These are parameters that I can put in the algebraic model, and we choose the better parameters to extract the form factor. So after a lot of work here, we find that those are the better parameters for the masses of the quarks.
Okay, very good. So these are the ones that best fit the data and
Yes.
the non-behavior. Okay, very good. Yeah, I wonder this because these are not precisely the values that you found on the PDG for some scale, but these are the values in your model are the best. Okay, thank you. Thank you. Other questions? Yes, please.
Hi, Melanie. Thanks for the talk. I'm not sure if you can go to slides for the PDFs. I was just before the extraction of the
For the
before the I see.
PDA?
Yeah,
Okay. Here.
those one, yeah. So I was wondering how strict is this prediction for the PDA? Is very flexible or you are very sure that that is the shape? I mean, if you change a little bit that, your results would change a lot or not?
If you change a little bit the PDA, my spectral density will change a little bit too, but the results won't be changing a lot. But we choose this Spartan distribution amplitudes from the literature because they have been proved a lot of time, I don't know. And they are the best in describe the method. So we choose this one for that. Yeah.
You have to go back and forward you have to go back and forward to check that these are the right to your predictions.
Yes, actually, the relation between the spectral density and the Barton distribution amplitude is in the work, in the previous work that we published this year. And it's very good, but it is not the work I presented here. And it's in the light conformalism is here. So you can obtain a relation in this part of this between these spectral density, Barton distribution amplitude. In the formalism.
Okay. A very quick question and answer, please. I mean, if you have questions, please ask before myself. I can.
Just came to my mind. Sorry, it just came to my mind. Can you extend your formalism to study like baryons like protons or neutrons, like protons or other charge baryons?
Okay.
How will that change?
Well, First of all, I won't be able to work with the Bethe-Salpeter equation because it's the equation that describes mesons, right? So I will need a model that describes variance, like the Padev equation in the Schrödinger-Dyson equation, and make an algebraic model based on that equation.
Thank you very much again, Melanie. Now we move to the next talk by Johan on a topic that is very close to my heart and to the whole PhINO and experimental group at Bell2 Physics at Simvestab. So still, I will be very strict on time. It doesn't matter. So I like everything, but I'm strict. Okay, so when everything is ready, you have 15 minutes, including questions. Okay. Okay. Please.
Okay, hello everyone. First of all, I want to thanks to the organizer for the chance to give this talk. And ¿cómo funciona esto? Okay. So I gonna thinking about a measurement of tau lepton mass in semi-invisible decays. This work is with the intention to propose a method that we can use to validate a study of beyond standard model physics, and like proof. We said old know that is the mass of tau lepton to validate our techniques. This work was in collaboration with Eduardo de la Cruz Burelo and is framed in the context of Bell2 collaboration. So it's precise to tell you about what Bell2 detector is. And this detector is located exactly in the interaction point in the SuperKIC-B accelerator that is located in Tsukuba, Japan. This accelerator accelerates electrons to an energy of 7 gigaelectron volts and positrons to the 4 gigaelectron volts to produce threshold energy that we can produce B mesons. So is for the reason it is called B factory. So BL2 is an upgrade of Bell detector, and right now we have the world record in integrated luminosity that is higher than LHC in fact. So I present to you what is semi-invisible decays. If we think about collisions that was produced in electron positron collider, we have X-pair particles that decays on a bunch of charged particles that we can detect. So we have in each site one particle that is impossible for us to detect. So if you look at that picture, and if you can imagine processes that are similar to that we have to look at that. So it is like so that is make a measurement related with the beyond standard model processes and all of these esoteric particles that I can tell that. So what is the interest in semi-invisible decays? It's because it's an approach to study beyond standard model particles like dark matter, supersymmetry, axion-like particles, and lepton violation decays. So two new methods help us to improve some upper limits of interest in beyond standard model particle production. So the first approximation to study semi-invisible decays is to probe our methods. To prove our method, we were interested in measuring the mass of tau using official Monte Carlo similarity data of Bell2 experiment. focus in particular in this process where electron collides with positrons and produce a pair of taus that decays on one prone decays. That is it is this. So it's the current picture of tau mass measurement. Lepton masses are fundamental parameters in the standard model, and tau mass has by far, and we can see in this, the largest uncertainty. Just as Pablo told us previously, this is important consequence for lepton universality test. So in the PDG reported mass is dominated by best tree collaboration or best tree measurement, and these take advantage of cross-section on being energy. And we have another technique that is used, is called pseudo-mass technique. This technique was developed by Argus, used also by Opal, Bell, and currently is used by Bell too. So if you look at in this picture that is extracted to the plot, the Argus paper, you can see that it is a mass distribution of tau, and in this region close to tau lepton mass, it is we have a kinematical limit, but this technique has a problem because all of these data are not involved in the study or estimation of mass. So when we look at that, we formulated the following question. How can we develop a method that allowed us located all that data in the interested region? It says more precision, and it says more statistics in the region of interest. So a partial answer to that question is the semi-invisible final techniques. This work is based on this first paper and this paper. This work is a generalization of this work, and in this work, they only work with one charged particle that we can detect and one invisible particle. This another work works with a bunch of particles that we can detect. So normalizing energy, masses, and momentum, and setting the mass of X equal to 1/2 of center energy of center of momentum, we get this expression when we apply it with the all kinematical equation. So if we set X equal to our tau, and M1, mu1, and mu2 is equal to our neutrino, the equation 1 reduced to the expression 2. If you look, that is a parabola equation, and we obtain the vertex of that parabola, we get the MH that I called MH method. And on the other hand, if we assume the mass of neutrino equal to 0 from the equation 2, we get this expression. And if we use the positive part of that equation, we obtain the Mmax method. And if we use the negative part of this equation, we obtain the Min method. So we worked with all of these sample Monte Carlo data, and it is necessary to clean our signal. To this, we use a machine learning technique that used this figure of merit that we maximized to obtain this code in this new variable BDT, and it is a technique that we've used, Boston decision trees. So, and after that, we get a MH distribution. It is the variable that we used. And we obtain this distribution that you can look in this plot. In red is we have our signal. Blue is our signal. Red is another tau decays, And in black, we have the adding of all samples. If we make a zoom in this window of mass, we can fit this distribution function and where the P1 is a bias estimator of tau mass. So first of all, by performing the fit on tau pair signal sample, we obtain the P1 estimator and looked at the difference between the mass that we use to generate Monte Carlo. It is a difference between them. So it is our fit in this model, in this technique. So we have to correct them. Correct this, and it is the value for tau lepton mass that we obtain using MH technique. The same for the Mmax distribution using the same function to fit. We get this bias. After correct them, we obtain the mass of tau lepton that I showed in this box. And finally, this is the M-mean distribution. The variable defined by this equation. We can obtain these results. And if you look, we could achieve our aim. That is redistribute all statistics in the region of mass of tau. This is increase of precision, and the results are shown in this slide. We obtain this bias that is the lower. After correct the bias, we obtain this mass to tau mass. As conclusion, the best method to measure the tau lepton mass in one-prong topology, which has not yet been implemented in Bell-2 collaboration, is M-mean method, where a value of this for tau mass is obtained. The method to carry out mass measurement in the case whose final products are classified as semi-invisible, used in this work naturally have a bias due to an impossibility of completely reconstructing inside the case. This work has validated that the semi-invisible final technique could be used to study beyond standard model processes. To pursue this ambitious work, this is the current work in progress that is based on these two papers. The first is Argus collaboration. We are interested in study tau decays on one lepton plus one alpha particle that is like a Goldstone boson, originally studied by Argus collaboration. In this other paper, they work with a three-prong decay as stack. We are interested in use this decay as stack. So currently we are in the cleaning stage, and this is that's it for me. And thank you for your attention.
Thank you very much. Questions?
Hi, Johan. Maybe it could be a naive question, but instead of using neutrinos to measure the mass of the tau lepton, could be convenient to use another decay channel where no invisible particles are present?
Yeah, because for the detectors, is not we have not way to discriminate between this is a dark matter or a supersymmetry particle because in the detector we just study missing energy, and it is the same for the detector.
Last question. Okay, so it will be mine. With 2 pions, you have larger branching ratio than with 1 pion, but maybe is it more noisy? Can you comment on that?
So it's an interesting question. So this is, I formulated myself this question too, because in the collaboration, in the collaboration, the decay used is the 3-prong. And if you look in the first, the branching ratio is lower than the 1-prong topology. But in this topology is we have 2 challenges. The first one is the impossibility to reconstruct completely that decay, because the neutrino and the tau, because tau is has a short lifetime, and we don't estimate precisely or detect precisely the tau. So it is a problem. But it's interesting to know it's interesting to look at the last decay, because the branching increased. So, but in our collaboration, the pi zeros has a problem between the Monte Carlo and that.
Okay, so thank you very much.
Thank you.
No te preocupes, no te preocupes, yo la arreglo, no te preocupes. Sí, es online. Es que ya con esto de que se desmontó el apuntador ya no. Es online. Sí.
Can you hear me?
We have some technical problem, but now we can hear you.
Hello.
In Zoom, we can hear you. Yes.
I don't know if you can hear me. Okay. So I'll share my screen. Okay. Well, thank you very much for the opportunity to present a work here. My name is Jorge Javier Urquiza, and I will talk about the magnetic effect on the cross-section of Higgs boson production to gluon fusion. This is a work I've been doing with Angel Sanchez. So basically, what I'm going to talk to you about is, is if somehow the Higgs is produced in the presence of a magnetic field, how much this will affect the gluons, well, the cross-section for the production. So the introduction, this is a little insight of why are we studying this process. Well, we know that the Higgs field is responsible for generating all the masses for the elementary particles of the Standard Model. This is through the electroweak spontaneous image breaking. And since its discovery almost 10 years ago, precisely characterizing their properties, it's a very interesting topic. It will help us to understand better these different things of nature, like the nature of the electroweak spontaneous image breaking, the Yukawa couplings, and among others. And well, for the other side, in the theoretical side, very precise calculation of this Higgs property has been done. For example, the production and the case modes by different channel has been elaborated with very high accuracy. And it turns out that the production of Higgs boson by this process called gluon fusion is a very, very relevant process. This is because it corresponds up to 87% of the cross-section of the production to the energy that we know, these energies. And well, this little insight that is very, very, very short. This research refers that the Higgs physics only produce in proton-proton collisions. that I will call the vacuum case. But recent studies show the possibility that we can detect and produce Higgs in another type of collision. For example, relativistic heavy ion collision. This is very, very interesting. These two papers say that with the data we collect from this type of collision, we can in fact see observables of the Higgs bosons. And well, one of the important things here is that in the initial stages of this type of collisions, we have a stage called gluon saturation before the QGP will form, where there's a lot of gluons. And as I said before, well, the gluons fusion is the principal process where the Higgs is produced. So we have an ideal setting for Higgs boson were produced. And well, it turns out that in this type of collisions, we know that we are external factors that can alter the properties of Higgs boson. For example, the presence of a magnetic field and the presence of the temperature. In this analysis, in this presentation, I will talk about these magnetic fields. Well, we know that in this kind of heavy ion collisions, if we understand that peripetal heavy ion collisions, we know that we create very, very intense magnetic field. This is a little sketch of how a peripetal relativistic heavy ion collisions. Peripetal means that there's no central collisions, that there's a part of the ion that collide, but there's a part of none. This thing is the reaction zone, the interaction zones, where after some time the QGP will form. But these two parts of the ions go away. And well, there are charged particles moving, so so that creates like currents, electric currents, and electric current generates this magnetic field. And well, these are charge moving incredibly fast. So these magnetic fields are incredibly strong. Well, it turns out that the intensity at the beginning of the collision of these magnetic fields and around of the mass of the pion square, that means it's around 10^18 Gauss. It's very, very intense magnetic field. But the effect of this is the lifetime of the magnetic field is very, very short. No? It's a little Fermi, so it decays exponentially very, very fast. So basically, what I'm saying is that we are able to extract information from Higgs physics from these types of collisions. So there are extra factors we have to include in our calculations. And well, we are going to see a little bit of the calculations. Well, the process I'm talking about is this process of Higgs through gluon fusion that is described at the following amplitude. As the initial stage, we have two gluons with momentum P1, P2, lowering index mu and nu, and polarization λ1 and λ2. As a resultant state, we have a Higgs. So, well, we know that there are no direct interaction at tree level in the standard model for this process. So this process is governed for radiative correction. Okay, and well, a little in order, we have two different contributions that we have two Feynman diagrams that I will show you later. Okay, but well, I'm going to calculate the cross section, and the next question is if I manage to calculate this amplitude, how I extract the cross section for the theoretical side. So basically, if I contract the amplitude with the asymptotic space of the gluons, I obtain the M element, and after we can obtain the cross section here. We have to do the square root, and then we have to sum the two-promedy over the color and the spin of the gluons, and then we have to integrate over the phase space of the resultant particle. So basically, if I manage to calculate this mu nu, we can obtain the cross section for the process. Well, these are the two Feynman diagrams that I commented before. As you can see, we have two gluons in the initial states with momentum P1 and P2, and as a final state, we have a Higgs with momentum pH. And these two contributions is managed by this loop of quarks in the middle. As you can see, the two diagrams are very look-alike. So the only thing that changed is the flux of the charge. Okay. And here, well, the presence of the magnetic fields is included by these double lines in the quark propagators because they are the only charged particles in this process. So the magnetic field correction will be induced by these quarks. Okay. As I told you, they are the only particles that are charged in the loop. So we are not going to use the vacuum propagation to describe them. We have to use a different one. In this case, is the magnetic field propagator for the fermionic case. In the configuration space, it's just this part that we all know, but they also carry this thing that is called Schwinger phase. That means we know that charged particles charge a phase when they are moving in the presence of an electromagnetic field, or more general for an electromagnetic potential. So this is the explicit form of the Schwinger phase. And then the invariant part in the propagator is given by this quantity. Here you can see that there's a separation between the components parallel and perpendicular to the magnetic field. This is something that we know. I mean, this phenomena present in the classic world. And well, this parameter S is called Schwinger proper time. Here is how I'm going to manage this. And this part, this sigma 3 over here, is has to do with the interaction between the spin and the magnetic field. Okay, here I'm going to consider that the magnetic field is along the Z direction. So basically, if I apply the Feynman rules to the both diagrams I showed you before, we have these two expressions. Basically, it's one vertex, one propagator, vertex, propagator, vertex, propagator, and then I have to take a functional trace. That means that I have to sum over all the degrees of freedom. A little more involved expression is this. We have to take the spinor trace, a color trace, and an integration over the quark loop momentum. Well, in order to calculate the cross-section, first we have to go to the momentum space. For that is just to perform like a Fourier transformations. But for that, we are going to go first to the dimensions. Here, the Schwinger phase plays an important role because in the vacuum case, this Fourier transformation is direct. It's just identifying the direct delta. But here, like Schwinger phase depend on the space points, so it's not so direct. Then we have to carry out the integration over the loop momentum. We have a different way to do that, a different of the ordinary way. Then we have to compute integrals over the Schwinger proper times that appear in fermionic fermionic propagators for the case of the magnetic field. Then we have to calculate the spinorial trace, and finally compute the cross-section with the expression that I just mentioned before. So basically, that's what we have to do. But this is just the summary, so I will present some results next. Well, first I want to told you that these integrals of the Schwinger parameters that are not direct, that are difficult to do. So in general, we take some approximation to facilitate in order to calculate these integrals. The most frequently used approximations are the weak field limit and the strong magnetic field. In this case, we compare the intensity of the magnetic field with some energy scaling in the process. In this case, will be the mass of the quarks inside the loop. And for now, I will restrict to myself to work with the weak magnetic field limit. So I'm gonna think that the intensity of the magnetic field is a lot minor than the square mass of the quarks inside the loop. And it turns out that there are another energy scales that will be relevant. And in the approximation we'll use, I said is weak magnetic field, but with low transverse momentum. It turns out that the perpendicular momentum of the gluons is important, is relevant to the calculations. So I will restrict to think this, that is at maximum of the order of the quark mass. And these approximations allow us to perform a Taylor series of the analytic expression we got, and then facilitate to obtain the cross-section. So basically, this is the cross-section as a function of the mass of the quarks, normally sized as for the Higgs mass. And this is for a collisions where pure in the perpendicular plane and where the Higgs boson is produced at rest. So basically, we have the two gluons that come here in the perpendicular plane. The magnetic field is in this direction, and the Higgs boson is produced at rest. This is what it's mean this angle. This angle is the angle between the perpendicular components of the gluons in the perpendicular plane. So we can see that this black thing, gray thing is the vacuum case. And well, this blue line is the complete case. And this red line, I said no phase because I repeat the calculation, but neglecting the Schwinger phase at the beginning just to see the effect of the Schwinger phases, the net effect. So as we can see, we are pointing against the mass of the quarks. So the top quark is over here, the bottom quark is over here, and all the light quarks are here. So the main contribution will be the top quark. That's something that we know. And as you can see, we have this intensity of the magnetic field. So in this section, it seems that the magnetic field diminishes the cross-section, and in these sides for the light quarks, it somehow begins up and then cross the vacuum cases and begins down. Well, this is this is not very clear plot. So in order to see better the effects of the magnetic field, we define the following quantity that is called system response. That basically I compare the cross-section with the magnetic field, with the vacuum one, and normalize by the vacuum one. So now we are going to analyze a head-to-head gluon fusion in the perpendicular plane. Again, in this case, the gluons goes in head-to-head in the perpendicular plane, and the Higgs is produced with different momentum only in the perpendicular plane. In this case, the red line is that the Higgs is produced at rest, and then the momentum is going upwards to this direction. As we see, this response system is negative. That means that the cross-section diminishes with the presence of the magnetic field. As we can see, there is going to negative as we are plotting to the QB intensity, and it goes the other way when are changing the momentum that it has. If we grow the perpendicular momentum of the Higgs produced, the effect is growing, is neglecting the magnetic field effect. Okay, well, now we are going to analyze the orientation of the process with respect to the magnetic field. In this case, we are going to... Okay, thank you. In this case, we are going to analyze the same process with the same variable, the same energies, the same fusion, but the only thing that is changing is the orientation to the magnetic field. This type of collision, fusion, I will call perpendicular pure because, the Higgs is producing the perpendicular plane to the magnetic field, and the gluon lives only in the perpendicular plane. This thing I call perpendicular mix because, again, the Higgs is producing the perpendicular plane, but now these gluons have perpendicular and parallel momentum to the magnetic field. And finally, the parallel mix. This is called parallel because the Higgs is produced along the direction of the magnetic field, and mix because the gluon momentum have parallel and perpendicular collisions. As you can see, the perpendicular pure is that if it's the perpendicular plane, the collision, the fusion goes this way. The perpendicular mix is just doing a 90 degrees rotation in this sense. And the parallel mix is doing a 90-degree rotation, but now in this case, okay? And we are now to compare the different things that for these three type of well, orientation with the magnetic field. In this case, we are comparing the perpendicular mix and the perpendicular pure for a collision angle of P/2. So this means that the angle between P1 and P2 is P/2. So as you can see in the perpendicular mix, the response system is grows in the positive way, and the perpendicular pures is going from the opposite way. And well, finally, the other comparison is again the perpendicular mix, the same as before, but now I'm going to compare to the parallel mix, where the Higgs is produced along the magnetic field direction. And as you can see, the parallel mix decrease more in comparison with the perpendicular pure. So as you can see, there is more, well, there will be less Higgs produced along the magnetic field that respect to in the perpendicular field. And well, basically this is the final remarks of my talk, that the methodology used, we have to allow us to compute exact analytical expression. Then for head-to-head Gluon fusion, fully contained in the perpendicular plane, the presence of the magnetic field reduces the cross-section, meanwhile the perpendicular momentum has the opposite effect. This is the first plot. Then the cross-section as a function of CV exhibits an angular dependence. It depends of the angle between the perpendicular gluons. And well, the Higgs producing along the Z-axis decreasing the presence of the magnetic field. So basically this is the thing I'm going to talk to you about, and thank you for your attention.
Thank you, Jorge. There is no time for questions. Please stop sharing your slides.
Okay.
So now Gerardo Hernandez Tomé will talk on lepton flavor and lepton number violating processes. Thank you, please.
Okay, so good afternoon, everyone. So first of all, I want to thank the organizers, especially Mario and Hector, who contacted me. I'm really happy to be here in my alma mater. Okay, so before starting, I also want to mention that most of the work presented here have been done in collaboration with these colleagues. Some of them are here, like Pablo and Genaro. Okay, so let's start. So the structure of the talk is as follows. As you can see, I have split the talk in two main points. First, we are going to discuss the motivation to study Charles Lepton flavor violation processes. Here we are going to present what are the current and future limits for this kind of transitions. And then we are going to compare with the prediction of some of the minimal massive neutrino models. We will see that these kind of transitions are very suppressed in the minimal extension of the standard model plus right-hand neutrinos, but also in the so-called type 1 seesaw, in the usual type 1 seesaw mechanism. After that, we are going to discuss the phenomenology of the low scale seesaw models. Here we are going to discuss what are the effects of genuine heavy Majorana states and compare with the case of a singlet Dirac case. After that, we also are gonna discuss a particular realization of the inverse seesaw model, and here we are going to focus on the non-unitary effects and the correlation that can exist between the search of this transition and non-unitary effects. After that, we are going to present the motivation for the study of lepton number violation transitions. Here we have focused on complementary and alternative processes to neutrino-less double beta decay. Particularly, we are going to see the lepton number violating transition on hyperonic states. Here we are going to discuss the 3-body decays and the 4-body decays. And finally, we are going to give a summary and the conclusion. Okay, so as you know, in the original formulation of the standard model, neutrinos were considered massless particles by construction. That means that the right-hand fields for neutrinos were not incorporated in the Yukawa Lagrangian. So in this minimal scenario, you have that neutrinos remain massless, and lepton number and lepton flavor are conserved quantities. However, we know that this cannot be true because we have observed neutrino oscillation. And if neutrino oscillate, at least 2 of the 3 neutrinos must have mass different from 0. A tiny mass in comparison with the rest of fermions, but different from 0. And now it is clear that if neutrino oscillate, there must be also a mixing in the leptonic sector as analogous to the quartz sector. And what you have here is for 3 flavors, this mixing can be described by the PMNS matrix that can be described in terms of 3 angles and 1 CP violating phase if neutrinos are Dirac. So according to a global fit from several collaborations, you have that the values for these parameters must be in the range presented in this table. Okay, so then neutrino oscillation has opened a new question. So we still don't know if neutrinos are Dirac or Majorana particles. And also, we don't know if there is a new underlying mechanism that explains the tiny observed masses. So, of course, one can consider just the simple extension where we just add the right-hand field for neutrinos and give their masses via the Higgs mechanism, just as occurred for the rest of fermions. Yeah, but the point here is that neutrinos are different from the rest of fermions in the way that the right-hand fields requires to give an electroweak mass are not protected by chirality. So in principle, with these fields, you can also construct Majorana mass terms that breaks lepton number in 2 units, but they are allowed by gauge symmetry. So there is no fundamental reason to prohibit them. And in fact, from a theoretical perspective, what you have here is that you open the possibility for a natural explanation for the planning mind for the planning masses, for example, in the usual type one is mechanism. But you have here that the masses for neutrinos, the physical masses is given by the quotient between the square mass of the Dirac master over the mass of the Majorana scale that is associated to these terms. So in order to have a physical masses of, for example, 0.05 electron volts and considering Yukawa couplings of order 1, you need that the new heavy scale must be very heavy. Around 10 to 14 GeVs. So this scale is very difficult to test experimentally. Okay, so, but let me back to the discussion of lepton flavor violation. So we have seen that neutrinos oscillate, and if neutrinos are massive, we can have a Charles lepton flavor violation. But the question is now, what is the rate for this transition? As already mentioned, we can consider just the simplest extension. And here you have only the contribution of light neutrino states. So here you have that the branching fraction for these processes is proportional to the 4 power of the mass of the neutrino. So if you only have the contribution of the light states, you have that this transition is strongly suppressed of the order of 10 to minus 54, which is clearly out of the range of any possible experiment. And something similar must occur for other similar transition. For example, mu to 3 electrons or Higgs to a pair of charged leptons of a different flavor. Here at this point, it is relevant to mention that not long time ago, there was a prediction for the channel of a tau into 3 muons, where the author claimed that this channel can be greater than 10 to minus 40. But I don't want to talk about the technical details of this computation, but I just want to mention that in this other reference, we proved that there was a mistake in the approximation to compute the loop integral here. And in fact, we verified that this channel is also very, very suppressed as expected. So now we can ask what happened, for example, in the usual type 1 CISO mechanism. So what you have here is that now you are going to have a contribution of the heavy states, but then you are going to have that there is also a suppression, because now the mixing of this new heavy state obey the seesaw relation, where the mixing of these heavy states with the charged lepton flavor is now given by this expression. So again, in the formula for the branching ratio, you have here the mixings, and they are again proportional to the 4 power, and you have again a suppression. So in summary, any evidence of this transition would be a smoking gun for new physics, but not only beyond the original formulation of the standard model, but beyond these 2 massive neutrino models. Yeah. Alternatively, we will see that there are some very attractive models that are called low-scale seesaw model. For example, the inverse seesaw and the linear seesaw. And what you have here is that there isn't a strong relationship between masses of mixing of the new heavy states. And then you have a richer phenomenology where the new physics can be accessible to current experiment. For example, you can have massive neutrinos with masses around the electroweak scale or the TeV scale, and sizable contribution to this kind of transition. Okay, so what about the experimental side? So far, there is no evidence of this transition. Actually, we are living in a very precision era. And we have very strong limits for transition between the two first family. You can see, for example, now the current limit for the mu gamma decay is of the order of 10 to minus 13. But the important point is, as already Carlos Sanchez mentioned in his very nice talk, most of these processes, the sensitivity for most of these processes is going to be improved by future collaboration. For example, it's surprising the sensitivity that some experiments are going to achieve, for example, for mu conversion. The current limit is of the order of 10 to minus 12, and they are expected to improve by 6 order of magnitude. So it's amazing. And now if you want to know about the sensitivity or the improvement for these processes involving the tau flavor, I recommend you to see tomorrow the poster of Marcela. Okay, so now, as already mentioned, the search of Charles-Lepton flavor violation transition can set or can test different massive neutrino scenarios. And one of these scenarios is low scale CISO model. And what we have done here in this work is to propose minimal parametrization to capture all the relevant effects of heavy Majorana neutrino states. So here the idea is, in addition to the 3 light active neutrinos, you introduce 2 heavy states in such a way that the mass of the neutrinos is given by this expression. So after the diagonalization, what you have is you are going to have 2 heavy states with these masses. And you are also have the light neutrinos remain massless, and this cannot be true as explained. This is not a realistic scenario because, as I already mentioned, light neutrinos, their masses are tiny but not 0. But this is just a simple parametrization that is useful to capture the effects of the heavy state. As we have seen, the contributions of the light states are negligible to this kind of transition. So here it is interesting, for example, to compare the effects or the genuine effects of heavy neutrinos. What you have here, for example, when this mu is the only state associated to a Majorana mass term, so it is the only parameter that breaks lepton number. And when mu is equal to 0, what you have, you can see here this very clearly in this expression. You have that these 2 states are degenerate, and actually you have that these 2 states are forming a Dirac fermion. Remember that a Dirac fermion has 4 independent components associated to 2 chiralities for particle and antiparticle, whereas a Majorana fermion, since particle and antiparticle are the same, you only have 2 free components. So you can rearrange 2 Majorana fields in order to form a Dirac fermion. So here the important point is that all the phenomenology in this minimal parametrization is described by only 5 parameters. I mean, you have the 2 masses of the heavy states, or 1 mass and the splitting between these 2 masses, and the 3 mixings of the heavy states with the Charles leptons, okay? So what you need in order to compute the Charles lepton flavor violation transition is to know how are defined the charge and the neutral current. So in this minimal parametrization, the charge, if you work in the basis where the leptons are diagonal, the charge current is described by this B matrix that is a rectangular matrix of dimension 3 times 5, whereas the neutral current is defined by the square matrix of dimension 5 times 5. So here in the Feynman-Topf gauge, you have that the Lagrangian describing these currents are given by this expression. Something interesting to remark is in this scenario, for example, the couplings of the Z boson with a pair of neutrinos in principle introduce a lepton flavor changing at 3 levels. So from these Lagrangians, you can derive the relevant Feynman rules, and then you can compute all the branching fractions. So this is what we have done. We have compute all these processes in this minimal parametrization. And here regarding transition between the two first family, since the limits for these channels are very restrictive, you can use these limits to set now limits on the parameters of the new heavy states. So for example, in these contour plots, what we have are limits for the mixings of the new heavy states. Here we are considering the case of when the two heavy states are degenerated, and we are considering, for example, here that the mass of the heavy states is 0.1 TeV for this plot and 5 TeV for this plot. And then here these dash lines, this horizontal and this vertical, are the indirect limits that come from lepton number conserving and precise processes. So now the different lines, the solid lines, stand for the limits using the current direct limits, whereas the dashed line correspond to the future sensitivity. What you can see is, for example, that now the most restricted limit comes as expected from the mu E gamma transition, but in the future, since the sensitivity for mu E conversion and mu to 3 electron is going to be much greater than mu E gamma, so these channels are going to be more restrictive than mu E gamma, okay? Now, regarding transitions between that involve the tau flavor, here we can ask what are the maximum rates consistent with the indirect and the limits that comes from the mu E transition. Something important to remark here is, for example, you can have that in this plot, we are considering these maximum rates for two cases. The upper lines here represent the case when we are considered that R is equal to 1. That means that the contribution of a singlet Dirac state, and the lower line represent the case when we are considered that this in the parameter R is much greater than 1. So you can see, for example, now that the maximum rate for the tau electron gamma channel can be of the order of 10 to minus 9, that it's close to the sensitivity expected of Bell2. And you can have here, for example, that the channel of the tau to 3 electrons and tau to electron mu are very similar, and this is because the dominant contribution here comes from the diagram with the penguin diagram with a C photon. So something important to remark here is there are some channels that require chain flavor 2 times. For example, the decay of a tau into a pair of electron and antimuon. And here, these transitions are very special because here you only have box contribution, and you have that box contribution that conserve lepton number and box contributions that can introduce lepton number vertices. So here you can see, for example, that there is a difference when you consider the contribution of a singlet Dirac state and when you consider the contribution of when the splitting is very large. I mean, when R is equal to 1, the contribution of the lepton number diagram must be vanished. And this is the difference. So you can notice the genuine effects of Majorana neutrinos. I mean, for the case when the neutrino is singlet, you have that the branching ratio can be greater around 1 order of magnitude that when you are considered the splitting between the two states. Okay, and now what happened with the decay of Higgs boson into a pair of charged lepton? Here, one of the first estimation for this transition was done by Lorenzo at Toscano 20 years ago. And here they use an effective field theory approach, and they also give an estimation for several specific scenarios. And this is a very well-known paper that has motivated other works. For example, here we compute in this minimal parametrization, these decays. And what I want to stress here is this kind of transition are much suppressed that one could expect in a naive way. Let me try to explain this in detail. So here we have in the Feynman-Topf gauge all the possible diagrams that contribute to this transition. And you have here that, for example, this and this diagram have a divergence, but when you take the sum of these two diagrams, this divergence cancel. All these diagrams are proportional to the product of 3 Yukawa coupling that in this minimal parametrization can be expressed by this simple function. So one could, and additionally, you have that the contribution, for example, of the W with 2 neutrinos, this one, and these other diagrams, they have additional suppression because they involve other coupling constants. So in principle, one might expect that the dominant contribution came from these two diagrams. And if you use this road estimate, considering Yukawa couplings of this order, you have that the branching fraction for this transition is of the order of 10 to minus 14. Sorry, 10 to minus 4. However, what happens here is, although their sum is finite of this diagram, they are divergent, so you have to consider the contribution of this diagram as a single one. And what happened is, here, for example, in this plot, you can see that when you consider this contribution, that is the blue line, you have a value where the contribution of these two diagrams cancel it exactly and then starts growing again. But here, this contribution comes with a suppression factor that is around 2 orders of magnitude, for example, that the contribution that you will have if you have a sequential Dirac neutrino that is already discarded by current experiment. So what you have here is that if you consider the constraints on the current constraints on the mixing, you have that in fact the maximum rate that would be for this channel and would be of the order of 10 to minus 8. That is far of the sensitivity of current experiment. Now, so far we have seen a minimal parametrization that has been useful to study the effects of heavy Majorana state, but it is also worthy to study a realistic scenario where you consider the the values coming from neutrino oscillation data. And here, we need to know how to quantify the non-unitarity effects. So in this reference, Schechter and Valle show that for a general seesaw scenario that introduce a number n of new sterile states, you can block diagonalize this matrix using the perturbative or block matrix diagonalization method. So here, the U matrix that connects flavor and physical state can be expressed in terms of these sub-block matrices according to these expressions. So again, in order to compute these effects, we need to know how are defined the charge and neutral currents. So using this method, you have that the charge currents can be expressed in terms of these sub-block matrices. And here the mixing of the light state is given by this expression where this B1 matrix must be identified with the PMNS matrix because this BL describes the mixing between the light states. Yeah. So you can write now this expression conveniently according to this form. So you have here that this eta matrix is a matrix that quantifies the deviation from unitarity among the mixing between the three light states. Now, but we are interested in low scale scenarios where the new physical scale can be accessible at current experiment. So particularly we focus on the inverse seesaw model. So the appealing idea of this model required to extend the neutrino sector, not only by introducing the right-hand neutrinos, but also with the presence of new singlets that here we denote with this SL. So here and in this scenario, an explanation of the active light neutrinos now is based on the presence of a small lepton number violating parameter. So now you can here use the block matrix diagonalization method as a particular case for the inverse seesaw model. And you have, for example, that the mass of the neutrinos now it's proportional to this scale mu. So when mu is very small, you have that the masses of the neutrino is also very small. So you can also quantify the non-unitary effects now using the block matrix diagonalization method. So now you can quantify the deviation from unitarity. And in order to do that, we have considered an extension of the so-called Casas-Ibarra parametrization. Here we are consider a particular case where the subblock Dirac matrix can be expressed according to this reference, and we are considering that this M and this mu matrix are diagonal. So we have performed, okay, thank you. So we have performed a scan now using, in this parameterization, we have 16 free parameters that are 3 angles and 1 CP violating phase that are associated to the parameters of the PMNS. We have the 3 light masses of the neutrino, 3 angles associated with this rotation matrix, and the 3 entries for the diagonal mu matrix and 3 entries for the diagonal M capital matrix. So if we fix the scale BM to 1 TB, whereas we allow that this scale run from 1 to 1000 electron volts, what you can see is, for example, that now you can surpass very easily the limits that comes from mu E gamma. So here, this solid line represent the current limit for this transition, and this dashed line represent the future sensitivity. So here you will have that setting this parameter to this value, you can explore by the future collaboration that this scale must be graded around to 50 electron volts, and values fewer than this, that this value will be discarded by current experiment. So now you can see here, for example, the correlation that exists between the search of these transitions and the value of the elements of this non-unitary matrix. So you can see that there is a strong correlation, for example, between the eta, the element 1, 2 of the eta matrix than that in comparison with the other elements. So here, what you can say about this plot is that now we are exploring regions where the values of these elements should be less than around 10 to minus 5. Now, let me quick explain the motivation of lepton number violating processes. So here, as I already mentioned, this transition would represent a clear test to the Majorana nature of neutrinos. So if you observe this transition, this will point out that neutrinos are Majorana ambiguously, and the most promising scenario is study this transition is neutrino less. So you have here that the half-life time for this transition is proportional to the effective Majorana mass that is defined as the sum of the mixing involved in these vertices times the mass of the neutrinos. So today, the most restricted limit comes from the CAM-LAN collaboration that has set a limit of some milli-electron volts. So here it is important to distinguish this transition with the main background that is the double beta decay with neutrinos, as you can see here. And this, in principle, this transition is allowed by a standard interaction. Okay, but, sorry, this is, yeah. But it's also interesting to explore other lepton number violating transitions complementary to neutrino-less double beta decay. And here we have focused, or we have motivated by the study of lepton number violation on hyperonic decays. This is because the collaboration BEST tree that works as a factory of these particles is going to be, and these particles decay mainly to hyperons, so they are expected to set very restricted limits for rate processes of hyperons. So for example, they are going to look for flavor changing neutral current of this transition, but they are also gonna be able to set limits for lepton number violating transition of hyperons. So actually, they had set their first limit for this channel, which is around of 10 to minus 5. Now, today, the more restricted limit comes from this hyper CP collaboration for the channel of a chip to proton muon, which is of the order of 10 to minus 8. So, but what are hyperon? Hyperonic are baryonic states that involve at least one strange quark. So for example, the sigma minus hyperon is composed of 2 down quarks and a strange quark. So these are all the kinematically allowed delta L hyperon decays, and the motivation here is that this transition, the hadronic matrix element for these processes, in principle, are simpler to compute than those on neutrino-less W beta decay. So they can shed light on the correct evaluation of the hadronic matrix elements in nuclear decays. And also, they open the possibility of studying channels that involves muon in the final state that are not allowed kinematically by the nuclear decay. So what we have done in these works is we have give an improvement to previous result. Here it is important to distinguish between the contribution of long distance effects and short distance effects. So in this previous work, the authors consider a one loop mechanism in order to give a prediction for the rate of this transition. So here, the idea is to consider that the hadronic, the relevant degrees of freedom here, you consider the hadrons as the relevant degrees of freedom, but you have to consider what are the hadronic matrix elements, for example, that describe the transition between the hyperon A with an intermediate state eta. So a first approximation is consider that in principle here these hadronic matrix elements depend of the square momentum transfer in the transition. But as a first approximation, you can consider that these hadronic matrix elements are constant. And what you have here is, if you take this approximation, you have that the behavior of the loop integral is divergent. So what they did to give an estimation was just only use a cutoff to give a prediction. But here in this new reference, what we have done is we consider the dependence of the Q square momentum in the hadronic matrix elements, and we have found that actually the prediction for this rate is around 3 orders of magnitude suppressed that in the simple approximation. We also consider the short distance effects. Here the idea is to consider an effective field theory approach, considering a 6 Fermat operator of dimension 9, and we have considered 2 particular UV completions. We consider the effects of heavy Majorana state, but also we consider the contribution of 2 Higgs, the contribution of doubly charged Higgs boson that can appear, for example, in the Higgs triplet model. And what you found is, for example, the contribution of this transition, it can be greater 3 orders of magnitude than in this scenario, but anyway, yeah, thank you. They are far away from the current sensitivity expected in Vestry. So another interesting possibility is to look at the search of lepton number violating processes that are mediated by an on-shell heavy Majorana state. And here, the idea is to consider some extension that can predict neutrinos in the range from some MeVs to 5 GeVs. So you can consider, for example, the case of meson and taus. And what you have here is that if neutrino is produced on shell, the branching ratio for this transition present a resonant effect that can be observed in these decays. So the idea basically is the same. You have the weak interaction of 2 Ws that attach to a neutrino, but you have a vertex that introduce lepton number violation. But now this is a different scenario because you have a very specific neutrino. So you are going to be the search of this transition is very sensitive to different scales of the mass of the possible new states. So if you don't observe this transition, you can set limits to the parameters of these new heavy states. So there are extensive lists of this transition that have been searched in several collaborations. Today, the most restricted limit comes from the decay of a kaon to a pion and 2 electrons. So you can hear, for example, that you can set limits which are of the order of 10 to minus 9 for this very specific region, but there are other processes, for example, the decay of a D meson that it can be extend the region, but now the limits are less. They don't have much statistics as this process. So the limits are less restrictive. Now, finally, what we have done in a recent collaboration with Genaro and Diego, we have considered this 4-body lepton number violating the case of Hyperon. Again, we are motivated because BEST3 is going to be able to set the first limit on this transition. Here, these processes have not been computed. So you can have, for example, the decay of a sigma minus into a neutron, a pion. And this is the only channel, the only hyperonic channel that opened the possibility to have, for example, a muon in the final state. And here, assuming that BEST3 can be able to look at a sensitivity around of the order of 10 to minus 8, you can set limit on these different channels. So you can see, for example, that the limits that comes from the channel of a sigma minus into a neutron, a pion, and 2 electrons can be of the same order as the one that you can have, for example, for the channel of a D into a pion and 2 muons. Unfortunately, these limits are not competitive with the more restricted ones that come from the channel with kaons. Okay, so let me conclude. So the neutrino sectors turns out a very attractive place for the search for new physics. In particular, we don't know whether the observed neutrinos are Dirac or Majorana particles, or if these sectors include additional fermion singlets, so stereo neutrinos. So these extra neutrinos, if any, would enhance Charles-Lepton flavor violating processes, for example, in the so-called low-scale CISO models that are otherwise very suppressed by the tiny masses of the observed neutrinos. Now, regarding the lepton number violating processes, this would point that neutrinos are Majorana particles unambiguously. So in this search, on this subject, complementary and alternative processes to neutrino-less double beta decay play a relevant role in diverse collaboration. Particularly, there is a search for a comprehensive list of these processes in meson, tau, and baryons that are mediated by a resonant Majorana neutrino that can test the existence of new heavy neutrinos in a very well motivated extension of the standard model. So that's all. Thank you very much.
Thanks a lot, Gerardo. Five minutes for questions. So who wants to start? I have a question, but we can ask it privately. So anyone before me? Now that I see, okay. Yeah, please. The limits that you have for muon to 3
electron.
Yeah.
Three charge particles. There, I mean, you said that, yeah, yeah. So are there other calculations like
No, actually, there is different for the and the minimalist extension in this minimalist scenario. And that was something very strange because the prediction for this channel, for this particular channel was computed, I don't remember, but I think that was in the 70s. And the prediction was of disorder, very suppressed. But then this author claimed that this channel could be greater than 10 to minus 40, which clearly was in contradiction with the prediction for mu to 3 electron. So we noticed that, and we saw that there was something very suspicious. So that's why motivate us to do again the computation. And actually I have, let me, in the backup. So here I have, actually, I think it's here. So the author claims that this unexpected rate, it was due to the contribution of this loop diagram that involves that involves the contribution of a C boson with a pair of neutrinos. And he said that this contribution is not direct proportional to the mass of the neutrino, but is proportional to the logarithm of this quotient. So when you have that the mass of the neutrino goes to 0, you have here that this goes to infinity, and you have this unexpected prediction. But the point is that he was doing a not a correct approximation to compute the loop integral. He was considering that the momentum transfer, he was neglecting the momentum transfer of the C gauge boson. But you cannot do that because here the lowest scale is the mass of the neutrino, not the momentum transfer. And when you take into account this, you notice that actually this diagram is also proportional to the mass of the neutrino, and you recover the spectrum. So this is very important because experimentalists, they use this reference in order to motivate the search for this transition.
That's
So,
right,
yeah.
Thank you very much, Tom. Other questions? I don't see any. So yes, let me ask you something brief and then maybe.
Yeah.
So can you come back to the what you were discussing related to the Casas-Ibarra parametrization?
Yeah, sure.
Yeah. So the virtue and the beauty of this parametrization, as I understand, is that it splits very nicely low energy from high energy physics with the motivation of doing baryogenesis via leptogenesis, right? So the high scale is for the leptogenesis, and then you have low energy for whatever. So then, what is your high scale here? Is it here or it is the factor out of it?
Yeah, actually, the Casas-Ibarra parametrization was taught in the usual type 1 CISO, but this is a generalization for the inverse CISO. Here in the inverse CISO, you have that the hierarchy between the scales is this one. You have that the scale associated to this mu is less than the scale associated to MD, and this is less than the scale associated to this scale. Yeah, so here you have 3 scales, and this allows you to have heavy states with masses around the electroweak or the TeV scale and mixings that are not suppressed. So in this particular realization, you have that there is no and a strong relationship between masses and mixing of the heavy state. So, but this is based on this, in this hierarchy. So the point is that you can use here the block matrix diagonalization method for the inverse, so you can quantify the non-unitary effects. So that are described by this eta matrix. So,
but then it seems, according to what you discussed, that you are looking to low energy effects, lepton flavor violation and so on.
Yeah.
So are you sure what you are doing will fulfill leptogenesis?
Actually, no, we are not focused on that. No, we are only what the goal of this work was check the correlation that can exist between the limits from Charles-Lepton flavor violation and the non-unitary effects. But we are using a realistic scenario where you can explain the neutrino oscillation data. So you are using here in your scan the neutrino oscillation data, so you can explain the masses of the light neutrinos, and then you can look, you can set limits for this scale consistent with this data.
I understand, but then I wouldn't sell it as a generalization of Casas-Ibarra, because Casas-Ibarra is something that will fulfill leptogenesis. So I mean, it's interesting, what you are doing is interesting, but I wouldn't refer to Casas-Ibarra because Casas-Ibarra is leptogenesis, and then some things are low energy, and you are low energy. That's my point.
No, let me check that, and maybe we can discuss later,
Another question? No? Yes, please.
Related to Pablo's question, are you thinking maybe in the future studying baryogenesis through leptogenesis?
Well, that's something that I would like to explore, but so far I have been very busy doing the computation of these things, but that's one of the things that I would like to do in the future.
Thank you.
Any last question, especially from students, is very welcome. Not perhaps better privately. So thanks a lot, Gerardo, again. Thanks to all the speakers and attendants. We close the session, and I don't know if there is any announcement. No? Okay, so see you tomorrow, be on time. Estuvo muy bien.
Al final el inglés no queda para